Now, let's say that you have performed different algorithms for the same problem, then it will be a good idea that you perform your algorithm with different probability values and check for the accuracy. It would be good if you draw ROC curve also, and then your client would be happy to have better visualization with respect to this ROC curve, right? So more the information which you are providing with respect to your data and the algorithm, better it is for your project. So don't stick with always 0.5. I wanted to cover this sixth session, and that's the reason after completing this sixth session, I wanted to talk about this ROC and AUC. Okay. So this will again come in the advanced course also. But then I wanted to give you about the hint so that after completing even a first course, you should be having the sufficient knowledge. But yes, the more knowledge we have, we can always expect a better opportunity. Okay, so now we have come up with a new classifier which is called as support vector machine. Again, support vector machine, I'll be going through with the classification. You should tell me in the next session whether the support vector machines can be used for regression or not. The reason I always train for classification because there are a lot of projects out there for classification. Now, apart from the other methods what we have looked for classification, there is also one more method which is called as support vector machine, which is SVM. As I already told, support vector machine is also used for regression, but it is widely used for classification projects. Let's say that you have two input features. Let's say that you have two input features which are x1 and x2, which are shown here. And your output has two classes. Those are represented by 1 or zeros, or ones are represented say by square and zeros are represented by circles. So if you remember in the previous session also, I have explained you underfitting and overfitting with the help of this graph, right? By drawing two different classes, something like that. So now, what do you think what I am doing here with different lines? I'm just trying to segregate the classes, right? For example, for this class, for example, this line which is segregating these two classes tells that if x1 is less than this point, if x1 is less than this point, I'm just trying to give you one example, okay? So don't consider in that way, but the whole point what I'm trying to explain here is there are different lines which can separate this two classes, right? There can be infinite number of lines which we can separate these two classes. But why are we trying to separate out these two classes? If we can separate out these two classes, then it will be easy to understand what kind of input features belongs to this class, what kind of input feature belongs to this class, right? Simple. So to understand that, we are using support vector machine. The reason why people generally go with support vector machines is because it's quite simple and it provides good accuracy also with less computational power. So that's the reason people generally go and use this support vector machines. Now, if we have infinite number of lines, if we have infinite number of lines here, which can segregate the two classes, then which could be the one which we should use, guys? What do you think we should use? I can have infinite number of lines here. This is one more line which is separating this out. The line which separates out the two classes with a sufficient tolerance. Sufficient tolerance in the sense, let's say if there are lines here, the line will look for a nearest points and then it will always take a line which has the maximum margin. So now we have a sufficient amount of freedom telling that if there is a new point which comes in, for example, if I am getting a new point here, then we can tell that it belongs to class square, right? So there is a sufficient amount of bandwidth, and that is where margin is helping us. Maximum margin will help us in identifying an optimal line which separates out these two classes, and this optimal line is called as hyperplane. Now you must be thinking, why is this line called as plane? Okay, so this is the only example which we are considering in 2D. Imagine we have three-dimensional. Again, we have two different classes. So in 3D, let's say you have three input features x1, x2 and x3, and you have two different classes in your output y which are 1 and 0, and if you want to segregate that out, then you have to segregate that with the help of plane, right? So that's the reason we call it as hyperplane. Okay, now let's say I had one more class here. Let's say in my output I have 3 different classes. Then how will you differentiate this? How will you come up with the hyperplanes? So you have to come up with the answer for this in the next session. Okay guys, so let's go back to our previous example when you have 2 classes. Okay, so think on this. Okay, I don't want to tell the answer now. So in 2D it's okay, it's a line, but in 3D it's a plane. Okay, that's the reason it is the common name has been provided with hyperplane. Okay, now the nearest point, for example, for this line, let's say these are the nearest most points from this class, and from this class this is the one. So these are called support vectors. Why is it called support vectors? Because from this we calculate the distance margin, which is called as margin in support vector machine language, and this distance has to be maximized, right? So that's the reason the name coming in support vector machines, because this point very near to the line are called as support vectors. So I have again 2 features and I have say 2 classes. Okay, now I have different lines, say 1, say 2, say 3, say 4, say 5. Now tell me which would be your optimal hyperplane in this case. I have given the numberings. I have 2 features, x1 and x2. I have 2 classes. Right, 4, right? Because it has maximum margin. Right? Great. So now let's quickly go with some more examples so that you can understand support vector machines in a better way. I'm just giving you some different example, guys. Okay. Let's call this as 1, this as 2, this as 3. So out of 1, 2 and 3, what do you think which could be depending on distance? By looking at the graph, what do you think? Which one is better? Which would have the maximum margins? 1, 2 or 3? 1, 2 and 3. Which is better? Which has the maximum distance? 3, right? So if you notice, 3 would be having the maximum distance, right? But let's say that you have this kind of, let's say, you have 2 different features, x1 and x2, and these are your classes. Now how to segregate this using hyperplane? Right, so you're right. So this should be the hyperplane, right? If you look into this, by looking at this graph, it's clear that this should be the hyperplane. But then how does support vector machine does it? It would be very difficult for the support vector machines to generate this kind of hyperplanes, right? Okay, I think today we have got a good amount of knowledge about ROC and AUC because that is very important. So support vectors are the ones which are here, okay? These are the support vectors, okay? The ones from which we are calculating the margins. Those are called as support vectors. With the help of support vectors only we are able to come up with the hyperplanes. And support vector machine, it's just an algorithm name because we know what is support vectors. So that's how the name has come in, support vector machines, which is an algorithm. It's an algorithm name like random forest or decision tree. Okay, so I just recollected that I haven't given the puzzle after first week. As I told, in data science, logical thinking is very important. Okay, so from next time, please keep reminding me. Okay, now let's say that you have 10 jars. Okay, so there are 10 jars, and then each jar has 50 toffees. Toffees in the sense candies. Okay, each jar has 50 toffees, and let's say that each toffee weight is 10 grams, each candy. Okay, so each jar weight would be 500 grams, right? Apart from the jar, just if I'm just calculating the weight of the toffees, then it would be 500 grams. So now out of these 10 jars, there is one defective jar which has all the toffees or candies of only 9 grams. Okay, that means the total chocolate weight would be 450 grams. Now you have to identify this defective jar. You have a digital balance. You know digital balance, right? Nowadays people are not using common balance. They are using digital balance for weighing some components, right? Now fruit shop, vegetable shop, everyone uses digital balance, right? It will show you the weight here. You can use this digital balance only one time. That means whatever you want to keep on this digital balance, you can keep. But once the value is shown here, with that value only, you should be able to tell me which is the defective jar. You should tell me that strategy, which is the defective jar. You must be thinking that I'll keep this jar first and then I'll keep this jar. It's not a case. You can use digital balance only once. Once you got this value, once you are visualizing this value over this digital balance, that's it. You cannot use it furthermore. So you have to tell me what could be the strategy that using digital balance only once, we would be able to identify this defective jar. Okay? Did you understand the puzzle, guys? Cool. Great then. So please work on this and I will ask you the answer tomorrow. And please keep reminding me, guys. I want some fun also in the sessions and this will improve your logical thinking. Okay, now this is the example which I was talking about. So you have this kind of classes. Now it's very difficult to classify this, right? But if you try to look it in this directions, let's say this is your x1 and this is your x2. Okay, now let me correct this. So let's say this is x1 square and this is x2 square. So if I come up with an equation z square equal to x1 square plus x2 square, then don't you think I'll be getting the z value something like this? Because the ones which are very near to origin, the value will be lesser, will still remain near to the origin. The stars which are away from the origin will be slightly away from the origin. Now it will be easy to classify this using hyperplane, right? Now using this, it will be easy to find the linear hyperplane for this, right? But then you must be thinking it would be really difficult. We have to do this, we have to come up with this z square manually while doing the project. No, it's not the case, guys. Fortunately, there is something called as kernel tricks. Inside support vector machines, there is something called as kernel, a kernel trick, which transform the data in a way that the classes can be separated out by linear hyperplane. Okay, so this is the inbuilt feature of support vector machines. Okay, and there are different kernels which are inbuilt in support vector machines which you can read over Google, but then there are different kernel tricks. But then this is the one which I'm talking about, the transformation. What does kernel trick? What does kernel do? That is more important. People will not ask you what are the different types of kernels. How does kernel helps in our analysis? Kernel is transforms the data so that it could be easily classified using hyperplane. That's called as kernel trick. And then there are different kernel methods which you can use in Python. Now I'm telling about this different kernels, right? What are these called as? Say the probability value in logistic regression as a threshold value, right? Do you remember the probability value which you are changing? So what are these called as? Note down, guys. These are called as hyperparameters. So every algorithm will have different hyperparameter, and that hyperparameter will decide how fast your algorithm is in terms of computational time and how much accuracy you are getting in. Okay, so because say with different threshold values of probability you might have different results, right? Similarly, there are different kernels in support vector machines. You might have to choose different kernels and check which kernel is giving us a better accuracy. So kernel is our hyperparameter in support vector machine. Similarly, probability was a hyperparameter for logistic regression, probability value, right? So now, can you recollect what could be the hyperparameter for linear regression? See, I'll be talking about different things while discussing different algorithms whenever it is required. So we might have to go front and back, okay? For linear regression, what could be our hyperparameters? Slope. How can slope be an hyperparameter? We are not deciding the slope, right? We are not changing the slope. Slope is the one which would be our output. Beta naught and beta 1. We are getting those beta naught and beta 1 as an optimized value using gradient descent method, right? What we are changing, what values we can change by which our output could be affected or our computational time could be affected. If you remember, in the gradient descent method, I have talked about derivatives, right? Tangents. So when we have taken the tangents, I told you we cannot jump from this point to this point directly. We have to go slowly so that we do not miss our global minimum point, right? So for that, what we have done, we have chosen a learning rate, right? And then we have to choose the learning rate sufficiently small, right? So learning rate was our hyperparameter in linear regression. In logistic regression, you can consider the probability values. Can you tell me what could be the hyperparameter for random forest? See, now you know hyperparameters for linear regression, support vector machines, and then logistic regression. Can you tell for random forest, guys? It's simple, no? Number of trees. If you remember, by increasing the number of trees, the accuracy will increase, and then at one point of time, if you even increase the number of trees, the accuracy will decrease, right? So this is your hyperparameter for random forest. Okay, guys? So similarly, you will notice for support vector machines, there are different hyperparameters. Apart from kernels, there is something called as gamma also. So now this is your homework. You should tell me tomorrow what is the significance of gamma in the next session. And I have given the data section, and then for different weeks they have provided them the different data sets. So they will be providing you the data set, and then you have to implement support vector machines on that, and then you have to come up with a confusion matrix. Okay, so you have to tell me what are the pros and cons of support vector machines, and then you have to tell me the significance of gamma. Okay, so, and guys, now it's high time that you should start working on your assignments. You don't worry about overfitting and underfitting now. You can just tell me what you can do whenever you are trying to implement any algorithm to any data set. Just apply it in Python. First, you have to do a lot of exploratory data analysis. Before that, you have to import the CSV file using pandas. Second step, do a lot of exploratory data analysis. Third step, split into training and test data set with 70-30, with different things you can use. 80-20 you can do, it's up to you. 90-10, and can check whether which answers, which split of the data works better, and then train your model with different algorithm, then test it, and then find the accuracy using confusion matrix. Okay, and then you can tell me whether it is overfitting or underfitting, and if it is overfitting, what all things we can try. If it is underfitting, then what all things we can try. Okay, in general, in the initial phase, this would be sufficient if you can perform the algorithms and tell whether it is overfitting or underfitting. For each algorithm, there are different ways tackling overfitting and underfitting, and there are some common ways also which you can look for. But in general, the generalized methods, what we can do, you can try these things also anyways, this ratio percentage values, or you can use transformations such as z values. If you remember, do you remember z values? X minus mu by sigma, convert all your features in z values, and then you can check. So you can do this also. You can use different hyperparameters. That could be one more example. Use different hyperparameters. But then in general, what we do is, which you will be learning again. So in general, for underfitting, what we do, if the model is going through with underfitting, then what we do, we try to complicate our data. What do I mean by complicating? We try to increase the number of input features. We try to identify if there are any more features, because the features which we already have are not sufficient for predicting our output. So we have to come up with additional input features. This is one of the ways. For overfitting, what you can do is you can increase the training data set, or you can use some regularization techniques that we'll be learning again in the advanced course, but you can use some regularization techniques. But apart from this also, if you can look into these different techniques what I've taught, splitting of data, hyperparameters, z values, we should be able to come up with the optimum results. If the model is underfitted or overfitted, then we have to use different techniques for that. Okay, great. So today we will be running this Python code completely. Okay, I specially have written this code so that we can run this today. Now you have to tell me what each line is doing, guys. First three lines are we are importing our NumPy, Pandas and Matplotlib. And in Skill-Learn, as I told, you will have the machine learning algorithms. It also has the data sets as well. Instead of importing the data set as a CSV file, I'm just directly taking the data set from Skill-Learn itself. So now let's say that I'm running this 5 lines. Let's say that I'm running this. Okay. Okay, it's saying that we have to end this somewhere, triple quotes, because we are commenting it, right? Great. So what I have done here is I've imported the iris. Iris is one of the famous data sets which people generally use it for practicing. You can also use it if you want. So now let's print this iris data set. But before printing, you can also check how does the directory looks like for iris data set. Okay, or also you can print it if you want. So it says that this iris data set has lot of things. It has some DSCR, you can look into that. It has data which we require, okay? And then feature names, the feature names are the sense, these are the columns, okay? Column names. It has file names which are not required for our analysis. It has target and target names. And target names are required for us, okay? Because target names are our outputs, right? So it has some inputs and then it has some output. So let's see how does our input look like. What is the 7th line of code doing? It will tell what kind of data set it is. So if you remember, when you import any CSV file using Pandas, it will tell you that is a data frame. But here it is showing the type is as a sklearn bunch. This has different data frames. As it is a bunch, it has different data frames. But what is required for us is data which has our input features and the target names which has our output features. Okay. Okay, now let's look at the next line. How does it work? Let's create a data set now using Pandas. From this data set iris, I'm just taking data and the column names are iris.feature names because this has the feature names. Now let's look at this and you will understand what I'm trying to tell. Let's print this because until and unless I print this, it will not be printed, right? So what you can do, you can always print few things and then you can understand what is it. Now, if you notice, this is our serial numbers. This is not required though. It will just be printed. Don't worry. These are the sepal length, sepal width, petal length and petal width. What we are trying to do here, by looking the feature names, you can understand that we are trying to classify the flowers based on the sepal length, sepal width, petal length and petal width. So these are our inputs, 4 inputs, right? These are our 4 inputs. Now, let's create a column. These are the 4 columns. Now let's create a 5th column, target, which will take this target. Okay. Now let's print that also. Let's print our target also. Now if you notice, I have a new column target which tells 0, 2, 3 something something. There are a lot of data in between 0, 2 or something, but the challenge is I am not able to understand what are these 0 to mean, right? I'm not able to understand. See, these four I know. Sepal length will be in centimeters or meters, let's say. That's a length dimension. This is sepal width. We know the dimension of width. It should be number. Petal length, petal width. But what is this 0, 1, 2? Where are the names corresponding to this 0, 1, 2? Which are our targets, right? So for that, what we have to do, we can print the target names also. If you want to understand, we can print the target names as well. See, Setosa, Veriscolor, Versicolor and Virginica. So 0 represents Setosa, Versicolor is 1, Virginica is 2. So now we have a kind of bunch, Skill-Lync bunch, as we have already seen, by name Iris, which has different datas. And for our analysis, we are using data, target and target name. Data has all the input features. Target has all the target outputs in terms of numbers. But how to know what are those numbers corresponds to? It's there in target names. Okay. So far so good. Any doubt, guys? Till line number 14, do you have any doubt? And you can also do this, guys. If you want, you can try this also. Describe thing. I'm not sure if it's gonna work, but let's see. So what is it is doing? Our data frame is DF. So I'm running DF. Now DF has sepal length, sepal width, petal width, and the target. So it will tell you the count, the number of records at one shot. It will tell you the mean. It will tell you the standard deviation. It will tell you the minimum value, maximum value, and 25 percentile, 50 percentile, and 75 percentile. Achha, by the way, before going ahead, can you tell me, I know that you all know what is count, what is mean, standard deviation, and min and max. What are the 25%, 50%, and 75%? Let's say that you have a data or the numbers, some simple numbers. Then you know what is the min value, which is 0. Max value, which is 100, right? And then you know what is mean here. Mean is 50. What is median here? Median is also 50. You can calculate it, guys, if you want later on. And then what does median do? And what is the count? 101. So what is the median? Median is a middlemost number which divides the data set into 2. So 50 would be somewhere here. Now this min is also called as Q0, quartile 0. Max is called as quartile 4. So what we are doing is we are trying to divide the data into 4 parts. Okay. And then median would be Q2. So there would be now let's consider this as one series, and then there would be median for this also, that is called as Q1. And then this is as a second series from 50 to 100, and there will be median for this series also, that is called as Q3. So 25th, 1/4 quartile, 1/2 quartile is median, and then 3/4 quartile is Q3, and Q4 is maximum number. So these are the 50 is the median, right? So these are the quartile values. Okay, let's run this line now. And I believe you know what is this. From Skill-Lync we are importing model selection, and from model selection we are importing this function train underscore test underscore split. And then what I am doing is I'm giving all those 4 features in X. Okay, and then the target is in Y. Okay, so let's do that first. Okay, let's do that. Okay, great. Now we know what is X and what is Y. Now if you want, you can print X again and Y again if you want. But then I'm not doing any exploratory data analysis here, guys. You have to do it. Okay, try to understand the data, try to plot different graphs. Okay, so this is how your X looks like, and then Y also you can print if you want. Now what I'm doing here, I'm splitting the data with respect to 70-30 or 80-20, guys. 70-30 or 80-20, right? So now I'm dividing the data, right? And then let's print it. So what I'm doing here, let's say that I have a 150 data sets. I have a data set with 150 records, right? So if I print the length of X test, what could be the length? What could be the length, guys? Can you please tell me? You know what this len function is doing, right? Len is the counting the number of records in that particular data set. So as it is 80-20, 80% would be in X train, 20% would be in X test. Similarly, 80% would be in Y train, 80% would be in Y test. So out of 150 data, if 20% is going in test, that means 30, right? So you're right. 30 records will be in X test. 120 records will be in X train. Let's run this. So as you are right, X test has 30 records and X train has a 120 records. And X has 4 features: sepal length, sepal width, petal length, petal width, and Y has a feature target. Now similarly, this is again that 1 or 2 lines of code which I always talk about. One function from Skill-Lync we are importing SVM. Okay, and then from SVM we are using SVC as a function for support vector machines. So if you remember, we had empty, there were empty, for example, for linear model, if you remember, we have given some, if you remember for linear regression, what we have done, linear model dot linear regression, and then we had empty parenthesis, that means no arguments. But in random forest, if you remember, we have given n estimators, right? Similarly, for support vector machines, we have to tell what kind of kernel we are using, what kind of gamma we are using, and then what is the C value. So yes, you have to tell me in tomorrow's session what is the C value and gamma. I've given you some basics of kernel. There are polynomial kernel, there are linear kernel, there are different types of kernel. Similarly, gamma also helps us in, you know what is this kernel doing, right? Transformations. It helps us in transformations to come up with a better hyperplane. How does this gamma and C value helps? Please let me know by tomorrow. Okay. So now let's run this model, and then if I run this model, you'll not be able to see anything because that's a training model which is stored in variable model, right? Now if I say print model also, let's say I'm printing model. What you will see is just that how this model is built on. It is built on support vector machine with C value equal to 1. Cache size, these are all irrelevant for us. Kernel linear, you can try different kernels. Okay, so this is what it is giving, but we have to fit the model on our training data set, right? So let's fit it on our training data set. Now we have fitted the model on the training data set. It's printing the same thing again. Okay. Now we have to predict the score for our output for our test data set. So what is this 0.9966? This is our accuracy. So if you want to print how to predict the values, guys, let's use this. So what I'm doing, I have 30 data records, right, in our test. So you will see that there are 30 values here. Okay, 2 means Virginica, 0 means Setosa, and 1 means versicolor. So these are the predicted values. How about the real values that we already have in test, right? So this is our predicted value, and these are our test values. 2, if you notice, 2, 0, 2, 2, 1, 1, 2, same values we are getting here. Now you must be wondering what are this, right? On the left side. For our Y test, there are some values on the left side also, 128, 18, 130. What could be those values? Record number, exactly. Those are the observation numbers because we are doing sampling, simple random sampling. It will take any random samples. So if you notice 2 and 2, 0 and 0. So out of 30, if you understand, out of 30, the accuracy is 0.9666 something. 0.04 or 0.033 is a missing accuracy, right? Serial numbers. So we are not able to achieve 100%, we are able to achieve 0.966, right? So can you tell me out of 30, if the accuracy is 0.966, for how many records our classification is working properly out of 30? 29, right? Because the missing accuracy is 0.033. So there is one record which is not matching. The predicted value is not same as actual values. And how do we do that? If you remember in decision trees, where is that decision tree? So let's use this from decision tree. Let's use this and copy it in our SVM. Because as I told, I don't remember the syntaxes. So let's use y predict is equal to model.predict, which is same as this. So let me remove this. And then from Skill-Lync, I'm importing metrics. So what is this metrics has? Metrics has a confusion underscore matrix as a function. For us, it will come up with a y test and y predicted values, and it will be stored in CM. And then we can print CM. Okay, so you can print the CM. CM is a variable, so these are all not required. So now if you notice, this is our confusion matrix. So if suppose the actuals are, let me draw this. Let's remember this table and then analyze it. So our table was something like this: 16, 4, 9, 0, 0, 0, 0, 0, 1. This is what we have, right? Exactly. Now let's say that this is our actual values, this is our predicted values, and these are 0, 1, 2. This is 0, 1, 2. So zeros are setosas, right? So setosa is predicted correctly. We had 16 setosas as our output, and it is predicted correctly. Similarly, if you notice, there is no setosa which is in actual but predicted as some other versicolor or virginica. So it is done. Setosa is correct. Now, versicolor. We had 4 versicolors in actual, okay, and it is predicted also 4. So that's correct. Now going to virginica, if you notice, we had 10 virginicas flowers, but then out of that 9 are correctly predicted, but 1 is incorrectly predicted, right? So that is where we are losing the accuracy. Okay, so that's the important thing. Now you must be thinking we are not able to visualize it in a better way. So how we can visualize it in a better way? So what we can do, I can quickly do a better visualization thing, which you will learn by experience. There is a library by name Seaborn. See, I know that I didn't tell about this library in the initial sessions because it is not important for our analysis. It's important for visualization. Okay. So Seaborn has a library and I'm aliasing that as SN, like we do for NumPy as NP. And then I'm just plotting a graph with a figure size of 10 by 7. You can draw 10 by 8. The bigger the size, the bigger graph you will look in. And then in Seaborn, SN, there is a function by name heat map. In that function, we are allocating this variable CM in which we have confusion matrix. And then annotation equal to true. That means we want to see the annotation, right? Otherwise, we will be confused what is there in x-axis and what is there in y-axis. So we are plotting x as prediction and y as actuals. Now let's run this. And this is the one which tells if I don't do this, no, the plot will not be appeared. If you want to check, you can check it. The plot will not be appeared until unless I uncomment this. So now there is a plot which is coming in. Now if you understand, This looks so better. Let me bring the chat box. Yeah, this looks so good, right? The previous small table was looking good, or this one is looking good, guys? These are the actual values. These are the predicted values. Actuals 0, predicted zeros, same. So there are no false values, or there are no incorrect classifications. Similarly, actuals ones are 4, predicted ones are 4s. Actual 2s are, so actual 2s are 9, predicted are 9, but for 1, there were actual ones which were 5, but predicted were only 4. So when you now understand, when we have done the analysis by looking at only the small table, we have done that one mistake, right? So the table what we were seeing there was not this, it was something like this. This was predicted and this were actuals. Okay, so how nicely when we do a visualization in a better way, we can understand things in a better way, right? So did you understand this confusion matrix or this classifier table? It's so easy to understand now. See, from that small table, I have also committed a mistake, right? We can also commit mistake by looking at that small table because we were not having any labels. Now by this, we can understand in a very easy way. And then this is just a color graph. So higher the numbers, it will different colors. That's it. It's okay. But then you understood, right? This is only misclassification, which is in one number. That's the reason we have an accuracy of 0.966. Now, let's say that I have a 30% test data. Let's do not plot the graph. Let's see what could be the accuracy for us. Okay. We are not able to see that cursor here because it is still open. So we have to close this and then only the Python will appear again, and then let's run it again. So now if you see again, what is the result which you are getting accuracy as? Again, there is one misclassification, guys. Again, there is one misclassification, but the accuracy is slightly increased from 0.9666 to 0.977. How? This is mathematics. There was one misclassification, right? Previously and now again. Then how come the accuracy is increased? Can you tell me, guys? Exactly. So previously we had 29 correct classification divided by total 30 data sets in a test sample. Now we have 44 divided by 45. So the accuracy has increased because the numbers are different, right? So now let's try with 0.1. So with 0.1 also, if you notice, this one thing which is not able to correctly classify. Now you can check which is a record which is incorrectly classified, and then you can try to understand that particular record, what are those values and why it is not correctly getting classified. You can go deeper, dig the holes, and then try to understand what's wrong with that one record. Then you will understand that one record, the input feature values what are there for that record are incorrect values. So you don't have to worry about that. It's just an error. So while recording those values, what they have understood is how to pick that record. What you have to do is you have to make a table of y test and y predict. Okay, create a data frame, or you can create a data frame of y test and y predict. Now you have y test, you have y predict, right? Create a data frame out of it side by side. So you will be seeing the numbers 220022, and one record will be not correctly classified. You can take that one record and then you can try to do the deeper analysis if you want, but it's okay if you don't want to do it, but you can always do that so that you can tell to your client that the actual value what you are writing, for example here, where is that? Let's plot this. The actual value is given as versicolor, okay, but it is not versicolor, it is virginica. So you can ask your client that the table, the data what we have, it's slightly incorrect. If you want to have a better predictions in future, you can change that output, or if you want, you can tell them try to do the experiment one more time and then come up with the actual output for that particular record. Instead of doing the experiment for all the records, you can do it for that particular record which is incorrectly classified. Okay, so you can try different things, guys. I would say please play around with the Python. It's very important. Okay, please keep playing around with the Python so that you can do various things, and then if you want, you can change the kernel also here. As I told, you can use polylinear or like polynomial kernel or anything. So you can do various things. So please try it, guys, I would say. But I would not consider any assignments as correct assignment until unless you do exploratory data analysis. I want you guys to do exploratory data analysis, finding mean, understanding the data, plotting the graphs. Try to look at the graph, and then when you submit the assignment, you can write, for example, if I'm calculating the mean, and then below that you can write in the comments, by looking at the mean value, I've understood this, that this feature is influencing more to the output or something like that. By plotting the graph, I have understood this. So maybe the one record which is incorrectly getting classified, you can capture this record at exploratory data analysis itself. You can do that if you do a lot of exploratory data analysis. So I always tell my students, try to eat the data. When you eat the data, then only you can understand the data in a better way and then digest it. Okay, so that's how first step, try to understand the data using descriptive analytics, and then understand why we are doing this, why we are working on this problem, that is diagnostic analytics. And then using predictive analytics, we are doing the predictions, and then prescriptive analytics is recommending something to your client. So whenever there is a new, in future there is a new sepal length, sepal width, petal length, petal width comes in, you can always tell this could be the prediction with 96.67% accuracy. Okay, so that was all from today's session, guys. Tomorrow we will be looking one more classifier, which is KNN. Right. If you can come up with an example of kurtosis in tomorrow's session, it would be useful. If you try to do your homework at the back end, that would be useful. Otherwise, if you're not able to come up with any example, then tomorrow I will only provide the example for kurtosis and then tell you how does this kurtosis be helpful in tomorrow's session. Thank you, and please work on the puzzle. Tomorrow I'll be asking the answer for that. Okay, thank you, guys.
Good evening, everyone. Welcome to the next session on Introduction to ML and AI for Mechanical Aspirants using Python.
Okay, hello everyone. So in yesterday's class, I told you that to find out the significance of gamma and C. Did you try finding out the different significance of gamma and C, guys? Right, gamma tells how far it influences, right? So if you take low values, that means it is influencing quite far. And if the gamma values are quite high, then the values, it means it is close, right? How does it help us in support vector machines? I also know that what you are trying to tell, but that how does it signify, how does it help us in support vector machines? That is important, right? Right, C, you are exactly right. What you are trying to tell for C is correct. But how does gamma really help us in machine learning or support vector machine? So C tells, what C tries is, a high value of C tries to minimize the misclassification of the training data. Okay. So what does that mean? If you give the value of C quite high, that means then it will try to have less number of misclassifications. You can try that, but if you have a low C value, then it tries to maintain a smooth classification. So, but then how does gamma helps? Please find out these two things. These two things are still pending from your side, guys. Significance of C is quite simple to understand. High values of C will try to help us in minimizing the misclassification rate in the training data. Higher value of C tries to smooth out the classification. Significance of gamma and kurtosis example. I will explain you what is kurtosis again. I want you guys please come up with an example in real life. How does kurtosis help us in our analysis? Let me explain what is kurtosis again. So as we discussed, there are two types of kurtosis. Remember? Let's go back to that. platykurtic and leptokurtic. So it's quite simple. Kurtosis is a measure of peakness. So measure of a peak. So it's quite simple from the figure also. There are more data which are very near to the mean. There are more of data which are lying near to the mean, then it's kind of platykurtic. The data, more of the data are not lying near to the mean, then it means it's a leptokurtic. I'll just take the numbers for example so that you can understand it in a better way. Like say 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So this is one data and the other data is say 1, 3, 5, 7, 9, 7, 5, 3, 1. Can you tell me which would be platykurtic and which would be leptokurtic here? I'm just giving you one simple example, but assume these are the frequency values, okay? These are the frequencies, okay? Not the data, these are the frequencies for a given data. Okay, what do you think which could be platykurtic and which could be leptokurtic? Second one is platykurtic. See, the point is if I have this many data, for example, I have a lot of data and these are the frequency which is shown here. This is the frequency, okay? For example, if I draw the frequency curve, histogram tells us the frequency curve only, right? So for 1, 2, 3, 4 and then 5, 5 and then like this. So for this it will be like this, right? And then this number, these are the frequency number for some data, for example. Now if you notice this, if I draw the frequency curve with this data as a frequency numbers, then this would look like something like this, right? 1, 3, 5, 7, 9 and then 7, 5, 3, 2, 1, something like this. So what do you think now, which could be platykurtic and which could be leptokurtic? Let's say this one is 1, this one is 2. Which series do you think is platykurtic now? Second one is leptokurtic, right? So it's quite simple. It makes sense when we see the frequency curve, right? I think I have given you very simple examples by looking at the numbers. But just think in terms of industrial experience, no? How in industries, how will this be helpful? See, I think I've given you an example for skewness, that never consider this would be a bad data or good data. For example, there might be a lot of phones which are sold in Amazons. So for them, the frequency would be quite high. But there could be a lot of phones as well, such as iPhones. For example, for that, frequency might not be that higher, but we know that iPhones are very costly, and that could be the reason the frequency of selling for iPhone is quite less. But that doesn't mean that it is bad data. It could be a case that there could be a lot of profit people are gaining from iPhone even though there are less sales, right? So that was a simple example which I've given. Similarly, can you please come up with an industrial experience on this? Like, what do you think? Where can this kurtosis be useful? Let's take one more weeks of time and then come up with an example where could this be useful in your real life. And then please come up with the significance of gamma also. C was quite simple. You can try changing the values of C in your data set also, and then you will come to know what is the significance of C. But what is the significance of gamma? Try changing the values of gamma and then try it. There are different values for gamma also, right? There are different arguments for gamma in Python. Please try it, guys. So did you find out what are the pros and cons of SVM? SVM is computationally effective. But then my point was telling by behind that was it was quite effective, or it is quite accurate in high dimensional spaces. High dimensional spaces in the sense when you have lot many input features. In reality, the examples what I'm giving 3 or 4 input features, but in reality there could be 20 to 30 input features also. There could be 100 of input features as well, on which your output would be dependent. In such cases, support vector machine would be quite accurate. Okay, and the one more thing is the support vectors, as you know, it is dependent on support vectors. Support vectors in the sense, yeah, you found that it is not efficient for larger data set. Okay, Naga, I got your point. So there is a reason why it's not suitable, because see, support vector machine, it's actually made for high dimensional spaces. This algorithm is built in such a way that it should be used when there are high dimensional spaces. So while in that scenario, what happens, people generally use this SVM because if they have a lot of high dimensions in their data set. But then if there are high number of records, this SVM would not be useful, because already there are other algorithms which are quite useful when there are high number of data sets. So SVM was meant basically for high dimensional spaces, not for big data when you have more number of input features. Okay. And the other point is, this algorithm is prone to overfitting, because as I told that it's actually meant for high number of features, right? So there could be a chance when we have number of columns more than number of records, there could be a chance. Okay, you might see such kind of data, but those are very less. In those kind of problems, this would actually overfit your model, because you have so many data. And if you remember, I told you the underfitting and overfitting, right, yesterday. So for underfitting, I told you if you can increase the number of features, then you are trying to generalize your model. You're trying to make sure that your model is not underfitted. But then if you keep on increasing your features, that would make your model more prone towards overfitting. Okay. So these are the pros and cons of support vector machines. But then you should always try using support vector machines also when you have small data sets. When you have high dimensional spaces and small data sets, you can always go and use this support vector machines. Okay, there is one more classification algorithm which is KNN, and it is abbreviated for K nearest neighbor. Okay, so it's a very simple algorithm. It's one of the simple algorithms to understand. So for example, tell me about your neighbors, I'll tell about you. Something like this. See, for example, if I have an apartment where a lot of peoples or a lot of your neighbors are doctors, then the prediction what I would make is that you're also coming from a doctor's family, something like that, right? So tell me about your neighbors or about your friends. I'll tell you who you are. For example, if you have a lot of friends who are passionate about, say, singing, okay, then I will predict. I would not say that 100% accuracy, but I would just predict that you are also interested towards singing. That's the reason that you are going along with those friends. So this is very simple. Tell me about your friends, I'll tell you about you. Okay. So now it's very common that when we try to make friendship with someone, we try to make the friendship with those people who has the similar kind of passion or similar kind of habits or similar kind of thinking, right? So based on that, this algorithm has been built in. K nearest neighbor. Let's say again, very simple example. I have two input features. Let's say that I have two input features. Okay. Now, these are the classes. Okay. Blue color indicates one class and orange color indicates the other class. Okay. It's not like support vector machine where we will be creating an hyperplane here. It's not like a support vector machine here. But the K nearest neighbor, what it does, so for example, I am coming up with a new point. Then if I come up with a new point, for example, which has some x1 and some x2, and then I want to predict which class it belongs to, then I would check its neighbors. I would check the neighbors for this new data point. Based on the neighbors, I would be telling which class does this new data point belongs to, this star belongs to. Okay. For example, if I am considering only 3 neighbors, okay, Now, using these three neighbors, as you can see in the figure also, this star would indicate that this belongs to the class orange, class B, right? Now, how do you decide the value of k? How many neighbors should I check? So this is again your hyperparameter. Okay, this is your hyperparameter. So the value of k is hyperparameter. So if you keep on changing this, your model accuracy will be changing. Okay, so it's quite clear that, for example, if I take 7 model, k equal to 7, for let's assume that the value of k is 7, then the nearest 7 values are this, for example. I'm just taking an example, okay? In this circle, then these are the 7 points. Then based on that, the classification for this star would change from class B to class A, right? It's quite simple. And then how do you decide this nearest point? It's very simple mathematics behind this. For example, if I have some x1, x2 point, for all the data points, I have an x1 and x2, and based on that, the output has been decided, right? So if I come up with a new point, exactly distance between points, that is how we calculate the nearest neighbor. Okay. So what it does, it calculates the distances from the new point to the all the points, and then based on the value of k, it will form a nearest neighbor, and then based on that, it will decide what would be the prediction for that value. This is very simple. You can also write your own algorithm. As I told, in linear regression, you can write your own algorithm for linear regression instead of using Python's algorithm. How? Using gradient descent. Similarly, in KNN also you can do it by yourself. Just writing the distance formula, and the ones which has the minimum distance formula, that would be useful for the prediction. And then you can test the Python's library also for KNN. In Skill-Lync, there is one more function for KNN. You can test that using your own algorithm. I'm not sure if I have that for KNN, but let's see. So there are a lot of names for k nearest neighbors, and those names are memory based reasoning, example based reasoning, instance based learning, lazy learning. So one of the common interview questions is why KNN is called as lazy learning. Why KNN is called as lazy learning algorithm? The answer is very straightforward. See, whenever you give the value of k, it will calculate the distances from the nearest neighbors. So it will calculate it on a fly. For example, there will not be any training phase here. You don't have to. So what I meant is there will not be a separate training phase for KNN algorithm. If it is trying to predict something for some data points, it will directly train at that point and test it directly. Okay. There is no kind of training data set here. There is no separate training given. There is no such training for KNN like we do for different algorithms. So there is no training phase for KNN. That's the reason it is called as lazy learning algorithm. So it's a very common interview question. You can expect that. Okay. Now how to choose the value of k, that is important. Okay, that is very important. Say for example, say how do you decide which value of k should be chosen? That's an important question. Okay, how to decide the value of k? Okay, and this point I will not take it because this we have already discussed, and Naga has rightly mentioned it's based on the distance between points. Okay, so the rule of thumb for value of k is, for example, if you have 100 records in your data sets, then the value should be less than root 100, which is less than 10. So you can try with 5, 6, 7, 8, and then the one you will notice again with the increasing value of k, something like random forest, if you remember, you will notice that with different values of k, your accuracy will be changing, okay? And for the one you have highest accuracy, then you can use that, okay? You can use that method. Great. So that is your KNN. accuracy versus k value, and then similar to a random forest, you can try changing the values of k the way we have done in random forest, changing the values of number of trees, right? Right. So how to decide this value of k? That is very important. Okay. For example, let's say that I have a new point here. I have a new point here. Okay. Now if I take a very low value of k, let's say instead of knn, I'm writing 1 nn. That means the value of k is 1. So if you notice, all other are of yellow classes, but the one which is very near to this data point, it belongs to a blue class. Like it could be problem with the data, or it could be a altogether very peculiar data here for this data point. But whatever it may be the reason, but this point, this new point would be influenced by this blue point. So this is called as noisy sample. Okay. Because if you take the value as 3, you will notice that it will be classified as yellow, which makes more sense, right? So now, can we keep on increasing the value of k? No, you can't. Then in short, you will be considering all the samples as your value of k, and then you will be taking all the output classes. So it's very important to decide the value of k. So the good practice is to draw a graph between accuracy and value of k, and then notice where you will get the highest amount of accuracy. So this is a very important parameter. So if you notice, how do you calculate this distance? In our school days, we have calculated the distance between 2 points, right? If these points are in 2-dimensional, x1, y1, x2, y2, then we remember this formula, right? It's very simple formula. Okay. So this distance formula we used to call in our school days as 2-point distance formula, right? 2-point distance formula. But in reality, this is called as Euclidean distance formula. So when your data points which are given as numerical data, then you can always go ahead and use Euclidean distance formula. Okay. And then there is something called as Manhattan distance formula also. But most of the people uses Euclidean distance formula only whenever they have numerical data. But you can go ahead and use Manhattan distance formula also, which tells that instead of this, the formula would change like this. Now, x2 minus x1 plus y2 minus y1. Simple. So based on the number of points, it will be calculated. Now, for example, if you have high dimension, right? So in this case, you have understood, right? What is x and what is y? So it will calculate the distance formula from that new data point to the existing data points. Okay. So it will keep on calculating from the new data point to all the existing points, and then it will decide what are the nearest neighbors for this data point, new data point, and based on that it will calculate the output class for the new data point. But if it is a high dimensional, say you have input features as say x1, x2 and x3, and then your output is y, then how do you calculate the distance formula? So here when I meant y, this is a second feature here. Okay, so let me write that as okay, let me not confuse you with y, because y is always considered as output. It would be good if I give some other notations here. So here this y means not your machine learning output, not your data output. So but first understand how this distance calculated. If you have x1, x2 and x3 for some of the data points, you'll have these data points. Now there is a new data point which is coming in, right? For that also you will have x1, x2 and x3. Let's say dash. Okay, these are the new data points. Now it will calculate either using Euclidean distance formula x1 dash minus x1 whole square plus x2 dash minus x2 whole square plus x3 dash minus x3 whole square. So either it will be calculated using this or it will be calculated based on this x1 hash minus x1 plus x2 dash minus x2 plus x3 dash minus x3. So this is how the distance will be calculated. Okay. If k is equal to 3, should we calculate the distance from 3 points? How would we know what are the 3 points from where we have to calculate the distance? We would not be able to know, right? Yeah, but then how would you know those are the nearest points? By calculating the distance, right? We are forming loop inside loop now. So see, the point is we know that these are the nearest point, but how we know that these are the nearest point? We are looking visually, but how would the code understand? By calculating the distances. So until unless it calculates the distances, how would it come to know that these are the nearest point? So for that, code has to calculate the distances first. For example, there is a new data point coming in, then it will calculate the distances for this new data point from all the points. Okay, from all the points, it will calculate the distances, and based on the distances, it will identify, it will check the value for k. If k is equal to 3, then it will take the nearest 3 values based on the distances. Without calculating distances, how would code understand that these are the nearest values? So first, internally code will calculate the distances. So that's the reason this is a very simple algorithm similar to your linear regression. This is also one of the simple algorithms, k nearest neighbors. So I would suggest that you write your own algorithm for KNN using your Python. Okay, use the distance formula whichever you want to, and based on that, whenever there is a new point coming in, then based on those 3 points or based on those distance values and the k value, decide what could be the output. So it's like a you're understanding the algorithm, right?
So my doubt is in the example given here, like x1 dash minus x1 whole square plus x2 dash minus x2 whole square. What distance does the formula is giving to us? It is not any distance formula between points, right? Euclidean one, sir. What distance is it giving? A linear distance between 2 points, or what distance is it giving for us?
See, there are different ways of calculating the distances. For example, okay, let me create a new slide here. Let's imagine that you are into space now. Okay, now let's see that you have a data set, say x1, x2, x3, and let's say your output is y. You can have multiple inputs, x4, x5 also, but let's say that your x1 is mileage, x2 say torque, x3 say volume of your fuel tank. I'm just taking some examples. Okay, so these are the 3 input features, and based on that, let's say whether the car brand is BMW or not BMW. Okay, so for us, let's say that based on certain values of x1 and x2, these are all points where the BMW is lying. Okay, these are the, depending on the different x1, x2, x3 values. Okay, these are the output for these points are BMW. Okay, and now let's say I'm just giving you some random example. Okay, so that you can understand in a better way. So there are different data points. So first understand that we have a different data points which has 3 different input features, and based on that we are deciding whether a brand of a car is BMW or not. Okay, now by looking at this data you can also make it out. I am telling that black colors are BMW and the red colors are not BMW. So 1 and zeros. Okay, basically 1 and 0. So this is my output class. Okay, now it is pretty clear that by looking at this data I can tell that if say x2 is very less or very high, if x2 is very less or very high, then the output would not be BMW. If x1 is very high, that means mileage are very high, and we all know that for the higher versions of the vehicles the mileage will not be that high, right? So if the mileage is that high, we know that this is not a BMW car. It could be some other car, the ones which provides high mileage, right? So by looking at this data we can understand that. But assume that you are coming up with a new point. Let's say that you have come up with a new data point which is lying somewhere here. Okay, now see, visually I can tell whether this point is very near to your BMW class. This should be predicted as BMW, but for algorithm to predict that, it has to calculate the distances first, right? That you have already understood. But how does it calculate? That's your question, right? So what it does, now we know that every data point has 3 input features, right? So let's say that every input point has their own x1, x2 and x3, right? Now this point, using the distance formula, will calculate the distances between from this point to this point, from this point to this point, from this point to this point, from this point to this point. And how does it calculate the distance? It can be Euclidean or Manhattan or anything, but the formula would be, say, x1 dash is a x1 for new data point, okay, minus the corresponding x1 for this point, let's say, whole square, plus the second coordinate. Let's say the second coordinate is x2 dash for the new data point, and for the existing data point is x2. Similarly for x3. Now this is a distance formula. This is a distance formula between new point and old one. Let's say old one. This is your old one point. Okay. Now let's say this is your old point, or this is the existing point. Say let's say 2. Then it will calculate the distance from the new point for which we have to make the prediction. From there it will calculate from the new point for which we have to predict, and then the old point, other point, second old point. Then again it will calculate the distance. Then it will keep on calculating the distances. And once it calculates the distance, it will check for the value of k. Say the distance for this is, say, let's say 10 units. Say for the distance for this is, say, 11 units. Let's say from here to here it is 12 units. From here to here it is 9 units. So if you are giving the value of k equal to 3, then it will take those 3 points which are very near to this new point. And by looking at the distance, we know that this 9 units, 10 units and 11 units are the ones corresponding points with 9 unit distance, 10 unit distance, 11 unit distance would be the very near to this new data point. Now you would consider those 3 points for predicting the output for the new data point. So you are thinking in terms of 2-dimensional. That's the reason you are thinking whether the distance would be calculated as a linear or how. But just think in these terms, that you have number of features which are, the number of input features may be 5, it can be 6, it can be 7. Okay. But at one point of time, distance can be calculated between only 2 points. And then we are deciding what are those 2 points. Then one is the new point, the other point would be the old point. Similarly, again, we will calculate the distance between the new point and the old point, which is already there. So we'll keep on calculating the distances from the new point for which we have to predict the output. Once we have calculated the distances, then we will check for the value of k, and then based on the value of k, we'll see what are the nearest data points for this new point. If the value of k is 3 and all the nearest 3 points says the output is 1, that means BMW, then for this point the predicted output would be 1. Okay. In case if it is 1 1 0, then what would be the output? See, it's because that we have learned in our school days that distance formula can be used for only two-dimensional Cartesian geometry. It doesn't mean that it can be only used for 2 dimension. It's just that we never gone ahead and then work for 3 dimension at then. It can be used for 3 dimension, it can be used for 4 dimension, it can be used for any number of input features until you have all the input features and all the numbers, not the categorical data type. If it is a numerical data type, then you can use it. Now, can you tell me if the nearest data points outputs are 1 1 0, then what could be the output for the new data point? 0 or 1? 1, right. So it will check for the majority value. Okay. Now k is the one which tells how many points should be considered for predicting the output for a new data point. So k tells you how many nearest neighbors should be considered. K is the value which tells how many nearest neighbors or how many nearest points should be considered. Now, let's say that this is my new data point. Let's say that with 3, tell me this data point will belongs to which class, circle or cross? Circle, right? With k equal to 5, to which category it belongs? Circle. Great. Now I have an interesting question for you. For k equal to 4, tell me which category it belongs to. You understood my question, right? For k equal to 4, does it belong to circle or cross? And we already know the distances values. Let me write the distances values also here. Let's say that this is a new point. Say this distance is, say, 1.1 unit. This distance is, say, 2 units. This distance is 2 unit. This distance, say, 1.5 units. And now the value of k is 4. And this distance is 3 units. So with k equal to 4, we know that it will take these 4 values. Right? Now, right. So whether it will take cross or it will take circle, right? It would take cross. So now you can try this in Python also by writing this code of your own and then your inbuilt Python. Okay. You can try that if you want. Okay. But then see, these are all okay, but how would we calculate the distance when we have categoricals? For example, say that this is my x1, this is my, say, x1, and let's say this is my x2. Okay, now how would you calculate the distance here? So let's not take this x1 and x2 here, because this x and y would make confusion. Okay, let me take some other example in the new slide, because this x and y would always create a confusion. Okay, before going into the category list, how to calculate the distance. So how to calculate distance when we have categorical data type. So for this, how should it work? That's the whole point. So I'll take the same example, but I'll just try to change the terminologies, because that would be quite confusing because it has x and y. Let's take x1 and x2 again. Okay, before going to this, so if I have 10 boxes, let's name it as first box, second box, 10th jar, and then take chocolate from first jar, take one chocolate, from second jar take two chocolates, from third jar take three chocolates, and so on. So how many toffees I have taken in total? Can you tell me? 55, right? Now, if all the jars are correct, that means there is no defective piece, then total should have been 550. If I place this 55 chocolates on a digital balance, then it should show 550 grams. But if it shows 549 grams, that means the first jar is defective. So if it is 548, then it is second jar is the one which is defective. If it shows 540 grams, that means 10th jar is defective. Now before going ahead, I want to give you one difficult puzzle so that you can try it over the week, and then in the next weekend you can tell me the answer. You have a racetrack on which maximum of 5 horses can, at one point of time only 5 horses can participate in a race. So when these 5 horses are participating in a race, okay, then if there is a one race happening, that would be the first race. Okay, now we need to identify out of these 25 horses who are the fastest 3. We need to identify the fastest 3 horses out of these 25 horses. You have a racetrack. On that racetrack, only 5 horses can participate at one point of time. So first you have to arrange this race. After this race, then you have to come up with another 5 horses standing on this racetrack, and then there should be a second race, and so on, right? At maximum 5 horses can stand racetrack or can participate in a race. So now assume you don't have a stopwatch or watch or anything. You don't have anything. It's just that you need to identify the fastest 3 horses by looking them visually. Okay. So tell me how many races would be required to identify the fastest 3 horses. So now how many races would be required? It can be 10, it can be 20, it can be anything. Okay. But I want how many minimum races are required to identify the top 3 horses. So how many minimum races? That's the whole question. Okay. And I have a coding challenge also for you guys today. See, apart from challenges, I have some puzzles which I always keep giving to my students so that they can improve on coding and they can improve on logical thinking. So the coding challenge is, say I have 5, 7, 9, 13, 3, 2, 0. Let's say I have these 6 numbers and I have to identify the second maximum number in this series. Okay, please code this. How to find the second maximum number from the given series. The series is not necessary would be ascending or descending series. It can be, it's not necessary that the series is sorted. So you have to come up with a second maximum number in this series. Okay, so Please try to code this in Python. Take any random numbers by yourself and then you should submit the code. I'll be looking at this code and then I'll be telling you whether the code which you have written is correct or not. Because the code, whenever you write the code should be optimized once. Okay, this is important. See, you can achieve the answer by any coding. Like you can do any style of coding and then you can get the answer. But it should be optimized. Okay, when you write the code for this, identifying the second maximum number, the code should be optimized. Okay, going back to how to calculate the distance formula when you have categorical variable. Let's say that you have x1. Anyways, so how do you calculate the distance? First of all, so this y is your output. Let's keep it aside. Let's say that you have a categorical variables. These are the categorical variables. Okay. Now you want to calculate the distance. Let's say you want to calculate the distance. Say this is your first record. Say this is your second record. So on, and then you got a new data point for which you want to calculate the output. But before predicting the output, we have to calculate the distance, right? That is the whole thing about KNN. So let's say that you have whether it is a male or female. Let's take it is a male or female, and then let's consider male as 1 and female as 0. Here let's consider whether a person is married or unmarried. Let's consider this 1 and 0, married and unmarried. Now it's always important in machine learning that you always give some dummy variables to your categorical variables. That's the reason I'm giving 1 and 0. See, this 1 and 0 are not your outputs. Okay, these are not outputs. Now let's say for the second record it is male and this is married, and say this is female, this is married. Say this is male, this is unmarried. Now you got a new data point where it is female and unmarried. Okay. Now if you want to calculate the distance will be calculated in such a way that, for example, from this new data point to your first point, what could be the distance? When your x1 for new data point is equal to x1 for the existing record, the distance would be 0. When the new data point, say x2, or new data point is not equal to your existing point, then the distance would be 1. So that is what it is mentioned here. If anything is equal, then the distance is 0. If it is not equal, then the distance is 1. So now the distance, what happened? So the distance between this new point and this existing point, first point, is 1. Okay, making sense? So you can have multiple input features. I've just given 2 for simplicity. What could be the distance between this and this second record and this? 2, right? Because male and female are not equal. So 1 plus married and unmarried are not equal. So 1 plus 1, which is 2. So for third point, 1, right? So this is how you calculate the distance. You can have multiple input features again. Okay. So this is how you calculate the distances when you have categorical inputs. And one more thing, this KNN can also be used for regression, for prediction. But again, as I told, in the industry, you would see most of the applications for classification problems. We are looking at this algorithm for classification. So it's not that if I'm teaching only for classification, then it can be only used for classification. It can also be used for regression. So you should try to explore these things. When I'm not teaching those things, you should try to explore and check where and how it can be used for prediction, for regressions. So now let's do one quick simple exercise so that I can make sure that we all are on the same page. So let's say that you have 5 input features. So this is your first record and second record, and the values are say this is a binary input, so it can have only 0 or 1. So let's say this is for first record it is 0, for second record it is 1. This is a nominal categorical data type. Nominal in the sense it can have multiple, more than 2, right? So 1, 3. These are categorical data type which are converted into 1 and 3. Okay. Similarly, let's say x3 is binary again. So let me write what could be the values it can have for all this. Now there is a new record for which we have to make the prediction. Okay. Can you quickly calculate the distance between this point and this point? So 0, 0 equals, so 0. 1 and 2 are unequal, so the distance would be 1. 1 and 1 are equal, distance would be 0. 0 and 1 unequal, so the distance would be 1. 2 and 2 are equal, so the distance would be 0. So the answer is 2. Now let's calculate the distance between this point and this point. 4, right? Because only this is the one which is matching. So the distance is 4. Okay. Now this is so far so good. Now let's say that you have one more variable. Let's say that you have one more variable. Okay. Binary and other categorical be compared like that. See, x1 can have only binary values. So that's the reason I have binary values here. For x2, it can take 1, 2 or 3. For example, x1 is whether a person is male or female. So it can take only 1 or 0, right? x2 is, let's say, whether the person is married, unmarried or divorcee. So it can take 1, 2, 3. Let's say x5 is whether the person's age is less than 10 years or less than 20 years or less than 30 years or less than 40 years. So like 0 to 10 years, 10 to 20 years, 20 to 30 years, 30 to 40 years. So for those categories, we are changing 1, 2, 3, 4. So it's straightforward, right? Now, the challenge is, for example, x6 is a sales. Let's say x6 is say some sales. So this is a numerical data for which this is say 10 units. Say this is 20 units. And now if I have a new data for which I have say 8 units. So this is a new data. What would be the distance between first record and the new data? For these things, we already know what could be the distance. For these things, we already know what could be the distance. The distance was 2, right? From the first record. For this x6, what could be that distance value? Plus, so this would be modulus of, if you are using Manhattan, then it would be 10 minus 8. So 2 plus 2 would be 4, right? So this is how you have to calculate the distances when you have a mixture of categorical data type and numerical data type. Okay, now for this, the distance can be either 0 or 1 for categorical variables, right? It can be either 0 or 1. But here, the distance can be more, right? The distance can be quite more here. So there is a scaling difference. So there is a scaling problem here, right? How do you tackle this problem? Convert your x6 variable to your z-scores. You remember mean equal to 0, standard deviation equal to 1. Try to bring that to the smaller scale. Or if you want, you can all convert all this x1, x2, x4, x5, x6 to your z-scores. You can do that also. So how do you calculate z-score? X minus mu by sigma. Right. Now, if you notice, this z-scores can also be greater than 1. Can be, right? It can be greater than 1 also, right? It can be lesser than -1 also. So there is one more normalizing method or standardization method to change the scales. Apart from z-scores, there are a lot of different methods, but these are the two common methods which people will ask in your interview. X minus X minimum divided by X max minus X minimum. So now could you please tell me what could be the range for these values? So for example, if I convert this X6 using this formula, so it will look for this feature only. It will look for this column and then it will look for the minimum value that would be substituted as that minimum value, and that maximum value, for example, say 20, and the minimum value is say 5, that would be substituted here. And then for particular records, it will keep changing the values. For say first record, the value would be now 10 minus 5 by 20 minus 5, so it will be 5 by 15. For second record, it will be 20 minus 5 divided by 20 minus 5, so it will be 1, right? So we are just trying to convert x6 using this formula x minus x minimum by x max minus x minimum. So you can do this for all the features, okay? But then the advantage of this formula x minus x minimum divided by x max minus x minimum, there is a particular advantage of this. Can you tell me what is that? It will be always less than or equal to 1. That is one thing, right? There is one more thing. Can this value ever go beyond 0, like in the negatives? Can it ever give negative value? No, right? So this value will always lie between 0 and 1. That's the advantage. Acha, that's the advantage of writing this as using this formula. Okay, now tell me why I have written this closed brackets for 0 and 1 as for the range. This has reminded me something of maths. It's important because as I always tell, to become a data science, right, when I write 0 comma 1 in closed brackets, it's including 0 and 1. When I write in open bracket 0 and 1, then not included, excluding. So in the number line, if this is 0, this is 1, this is 2, this is -1. From 0 and 1 for open bracket, it will be like excluding 0 and 1, everything else between 0 and 1 will be included. For close brackets, both 0 and 1 would be included, and all the points in between, that would be also included. Now tell me, flower bracket 0 and 1 means this is a set, right? So it has only two values, which has 0 and 1. Nothing apart from 0 and 1, right? Very simple, right? So these differences you should know, guys. It's a simple math. So because people can test on your basic mathematics also when you go for an interview. because everyone knows that to become a data scientist, your maths should be good enough. Okay, and there would be a separate course on maths which would include permutations and combinations, probability, statistics, derivatives, okay, and then functions also, functions and limits. So there would be a separate course on this, because this all 5 topics, I know people will forget this. All this, our school maths, we will forget. After started working or after doing engineering, we'll forget all this. But these are required to become a data scientist, because you will notice, you have already might have noticed where we have used probability, statistics, and permutations and combinations. And functions and limits also you might have noticed to some extent. And derivatives also, for gradient descent, we have used derivatives, right? So all these topics would be covered in a separate course, so that we are good on this chapters also. Okay, then it will be easy for us to understand the advanced data science or advanced machine learning. So you apply KNN algorithm to a data set, in which the one Word document which in that the data set name will also given, okay, and then you can apply KNN to that data set, and then you can tell me what are the pros and cons for KNN also. But then also try to implement KNN to the same data set, for which what you can do is, by now you have learned logistic regression, decision tree, random forest, SVM, and KNN, right? You can take the same data set and apply all these algorithms to the same data set and check which provides you the best accuracy. Okay. So let's proceed with the coding. I'm not sure if I have anything on KNN. Let me check. Yes, I do have something on KNN, but if you notice, this is the one which is a combination of all the classifiers which I'm using here. See, if you notice, I'm using logistic regression, random forest. I can also use decision tree also. I'm using the same data set from Skill-Lync, from one of the data sets, and then I'm using support vector machines, and then I'm using KNN also. So let's do one thing. Let's take this SVM, the one data set which we have used yesterday, and on that let's apply KNN. Okay, so for KNN we have to take import neighbors in sklearn. From neighbors we have to import k neighbors classifier. So let's do that quickly. Okay, this is for SVM. Let's build a model for KNN. Let's start with the neighbors value of 3. Okay, so what we are doing, we are just assigning our k nearest neighbor to the variable KNN. Okay, and then let's print our KNN variable and fit this on X train and Y train. So let me comment this. Okay, now we have commented all this. Now let's work only on KNN. So let's run this now. And then let's print the score value as well. So by now you must have noticed that all the syntaxes would be same. It's just that we have to import different functions from Skill-Lync. So what's wrong with this? Let me hide this first. Line number 51. What's wrong with this? This is already commented, right? Let's build the model and then check what's happening here. Okay, this is correct. Then once I open this, what's wrong here? As soon as I uncomment this, it says there is something wrong here. Okay. Why is it so? Import k neighbors classifiers. Let's print KNN. Oh, so there is one close bracket which was missing. Right. So now it has fit the model on the training data set. Now let's do it on the test data set and check for the accuracy. Again, I am missing this close bracket. Okay. Open bracket. Okay. So now the accuracy is again 0.9667. Okay. So now again we know that with the 20% of going into test data, there would be one data point for which we have a misclassification, right? It's quite clear. Now let's change the value of k to 5 and let's check what's happening here. You're still getting same value. But because of this is a very small data set, your values are not changing much. So this is the same data set which we have used yesterday, iris data set. So the results are not changing. That means the data is very simple, and then it is very good data set what we are having as of now. Let's try with this 0.3. We are getting the same results what we have seen yesterday with SVM, right? Let's use only one point there in nearest neighbor. So now if you notice with k equal to 1, our accuracy has decreased. What does this mean? What does this mean? As I told, when the value of k is less, it will create a noise level. It will be impacted by the noise, right? That means, if you remember this, yes, noise, exactly. So there is a noisy sample which would influence the prediction for the new data sets, what we are looking at. So k equal to 1 is not at all a good value to take, because smaller the value of k, more it will be impacted by noisy sample, right? Great. So now if you see, I have created for today's session, what I have done, I have created a new code where I have imported all the classifiers: logistic regression, random forest, support vector machines, k nearest neighbor. So there is also one more classifier which is nav bias. Okay, but that's not in scope of this course, because anyways that is being used very less nowadays, so you don't have to worry about that. But if you notice, what I have done here is I have created the variables for all the models, for logistic regression, support vector machines, random forest, k nearest neighbor. Okay, and you can also create for decision tree. And then I fit the model for those particular statistical methods or machine learning algorithms. For linear regression, I fit the model, I've come out with a score. For SVM also, similarly, for KNN also, and for nav based method, which is not there anyways. So these are all not required below this. You don't have to worry about that. But what I'm trying to explain here is, this is the one way by which you can write the code, right? And then you can come up with the accuracy for all the different models on the given data set. I've splitted the model, I've splitted the data set, I've applied all the algorithms which I know for classifiers, I've implemented, got the scores, and then I'll keep a note of that. Does it make sense? Great. Now there is one more way, guys, to do this, which I want to explain here. So what you can do is, for example, you can define your own new function. This is called as user defined function. You can create your own function like this, in which you can pass 5 arguments. In that 5 arguments, first is the model, second is your training data set for input features, third one is input features for test data set, and then fourth one is output of your training data set, fifth one is output for your test data set. And then in this function you can define all the operations which you want to perform. So what operations we in general perform? We write model.fit. When we have created a model, we just write model.fit between training data set, and then we return the score what we are achieving it on test data set. So what you can do is just write like this: get score, because that's a function name, and instead of model I'm using logistic regression, support vector machines, random forest. And then if you notice, x train x test, y train y test, we already have it from this model selection train test split. So from here we already have these 4 variables. So once we have that, it's a matter of only one line. It's a matter of only one line to get the scores for all your different algorithms if you create your own user defined function. Similarly, you can write for KNN also. It's up to you. Okay. So the ones which I've highlighted, you have to notice only those lines. Don't worry about other lines. Other things will come to you while you practice. You will only understand how these things will come in. But the ones which I'm highlighting, I want you to practice these points at least. So what I am doing, I'm trying to consolidate all the different models in the one coding language in one Python file itself, so that I can understand which model should I choose for my prediction. So did you understand this from 45 to 51 line, what I am doing here? Now, you must have noticed that till now you must have noticed that I write random state equal to 4 or some random values here, 1, 2, 3 or 4 something, right? So based on this, you will be dividing your data set into train or test data set. So this value will also be influencing your output, right? Because if I change this value for random state, I will have different samples in training data set and different samples in test data set. Okay. For example, by this I will have only, I'm making sure 30% of the data should go in test data set, but what 30% we are not making sure. This is making sure what 30% of the data should go into the model, right? In the test data set. So this will also be influencing your output in your accuracy. Okay. So there is something called as cross validation, or people also call it as k-fold cross validation. Okay. So you can try that also, k-fold cross validation. So what it does is, I'll tell you what it does. For example, I'll not be telling you the code for k-fold cross validation because that is out of scope of this course, but then I'll just tell you what it does so that you can also try that. So for example, let's say that you have 10 data sets. Sorry, you have 10 data points. What happened to this? Okay. Okay, now this looks better. Let's say that you have 10 data points in a data set. Okay. Now, first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Now, if you're choosing 70% and 30%, that means 70% in training data set and 30% in test data set. Now, if you remember that random state is the one which decides your what sample should go under training and test data set. But there is something called as k-fold cross validation. So what it does, let's say if you're taking the value of k as 3. So it's like a cross validation. Okay. So let's say if you're taking the value as say 3, then what it does, it will create 3 different, based on the 70-30% ratio, it will create 3 sets of training and test data sets. The first, for example, if say first, let's say that first set, let's say that there is a first set in this 3 sets, k-fold, first set, second set and third set. Let's say these are the sets. Okay. So what it does, it will consider these three as your test data set in your first set. In the second set, it will consider these three. In the third set, it might consider other three. So this is how it will work. So in short, it will try to make sure that in three, it's actually trying to cross-validate your model. And then on these three different models, your three different data sets of training and test partitioning, your model will be running. Okay. So similarly, for example, ideally, let's say that you have 100 data sets. Now let's say that if you have 100 data sets and if you're using 10-fold cross validation, 10-fold cross validation. So out of 100 data sets, if you're using say 10-fold cross validation, then what it does, for example, if you're choosing 90 by 10 ratio, then what it does, from first to second, first it will take 1 to 10. Let's imagine as it is 10-fold cross validation, from 1 to 10 it will make it as test and the remaining 90 as training data set. From 11 to 20 in the second fold, it will take 11 to 20 as test and the remaining as training. In the third fold, it will take 21st to 30th and then it will take the remaining as training data set. Okay. Now, yes, you have a right question. Finally, on which data set will it show the result? Right? So for this, I would say that please try this because I don't want you to give the answer ready-made for all the questions. So please try this and tell me for what data set it will give you the answer. Okay. So you can try this. Anyways, it is not included in this syllabus for this course, but please try this and tell me in the next session for which will be the final result which will be considering. Okay. Yeah. So the point which I was mentioning, yes, finally it will what data set it will for which it will show the result, right? So that you can find it out. Yeah, but I think I slightly told something wrong here. So for the k-fold cross validation, it will not consider the ratios. It will calculate the ratios by itself. So you can cross verify it. It will identify. It will split the data by itself. For example, if I have 100 data set and I am using 10-fold cross validation, then it will split the data into 10 groups. And then it will automatically consider one group as test and the remaining as training. And then in second fold, it will take the second group as test and the remaining as training data set. Similarly, for example, if I have 100 data points and I'm using 5-fold cross validation, then it will divide into 5 groups. So each group will have 20 data points. So this k-fold cross validation will supersede your this partitioning, training and test data set partitioning. Okay. So now each group has 20 data points. So now in first fold, it will consider the first 20 data points as your test and the remaining as training. Similarly, for the second fold, it will consider the second group as test and the remaining 4 as training data set. So this process will be repeated when you use k-fold cross validation method. Now, what accuracy of finally for which model it will show the result? That's an important question which you have to ask and tell me the answer in the next class, because I want you to try this and understand how does this k-fold cross validation works and tell me, does it give the averages of all the results of all the folds, or does it give the maximum, the best result as the final result, or does it give the averages of all the results, or does it give the maximum accuracy which we have achieved in different 5 folds, and then it will showcase the final result as the maximum result. So whether it will give the average, or it will use majority, or it will give the best result. See, these are the only 3 options which we can get, right? or we can get some other options. See, for example, for 5-fold cross validation, the result could be either average or based on the majority ones or based on the best result, right? Is there any other possibility which we can get in? So please try to find how does this k-fold cross validation works in Python, and then tell me in next class what output will it consider, whether it considers the average or the majority one or the best result. Okay, so please tell me the answer in the next class. And this k-fold cross validation is very useful when people tell that our algorithm is biased based on our test results or the test sample or the training by test split what we are doing, right? So that we can make sure that our algorithm is not biased based on this partitioning on particular samples, we use this k-fold cross validation. So now these are the simple examples which we have taken. So this thing you have to remember, the k-fold supersedes your partitioning what you are mentioning. Okay, that's the first thing. Second thing, k-fold divides the data set into groups and then it will evaluate each group separately. First group would be test and the remaining would be training. In the second fold, second group would be test, remaining would be training, so on. So for example, if you have say 10 data sets and you have 10 data points in a data set and you're using 5-fold, then in first fold this would be your test, in second fold these two would be your test, in third this would be your test, in fourth fold this would be your test, in fifth fold this would be the test. So if this is the test here, this would be the training. If this is the test, then this would be the training. So this is how it will evaluate. And then tell me what will be the final result. Okay. So based on the fold, it will choose how many samples should go in the test data set. So for example, if I have 10,000 data points and I am using 10-fold, then how many data points will go in the test data set? 1000, right? So basically it is a 90/10 ratio, but then we will not explicitly mention that. K-fold will take it implicitly. Okay, so example on kurtosis. Puzzle and then coding challenge. See, I know you can write the code, but the code should be optimized one. And then fourth one is final result in k-fold cross validation. So these are the 4 points which I'll be asking you in next session. Okay, and next week we'll be seeing some technique how to, if you have very high number of columns of features, say 100 or 200 or 20, 30, then how to reduce those number of columns. In the next session, we will be looking at those. So that was all from today's session, and then let's catch up in the next week.
Welcome to the next session on Introduction to AI and ML using Python.
Now, few things which I wanted to discuss before going ahead. I want in SVM you guys to come up with the significance of gamma, and kurtosis I will only explain now. Okay, now let's assume that what is kurtosis try to tell us. Okay, now let's take that we are studying the height of a different individuals in India. Let's take India as a country where we are looking for height. Okay, so it was pending from long time, so I just thought I'll clear this first. What is kurtosis? Okay, now let's say that this is 3, this is 4, this is 5, this is 6, and this is 7. Let's assume that. Okay, now in India, if we notice, and okay, let's take 8 also here. Okay, and we are studying for the country India with the individuals of age, say 15 years to 35 years. Okay, now if I draw the frequency curve here, you would notice that at the height of 3, we will have very less people, very less, right? At the height of 4 also, we will have very less people. But there will be a lot of people who will be near to the height of 5.5 in India, right? So let's assume this is a distribution in our case. Okay, now if I want to draw a distribution over this itself, if I want to draw a distribution of Americans, so how will this distribution look like? There will be very less people with height 5 if I'm not wrong. There will be a lot of people with height near to 6 feet, right? So this is negative skewed for Americans. If you look into this with this chart, if you look into this, the long tail is on the left side, right? But if you look for the India, it looks like a symmetrical one with this graph. But what happens now is, how to understand the kurtosis behavior here is, let's say that I am looking for the salary now. Okay, let's say if I want to draw a salary chart here, salary distribution. So in our India, if you notice, let's say that there are a lot of people who are actually at the mean, okay, somewhere here, 5 to 6 lakhs. So let's say this is a perfect normal distribution. Now, as kurtosis tells the measure of peakness, this one would be negative kurtosis. Okay, and then if I want to draw a distribution over this, let's say that for a developed country, let's imagine that for a developed country, if I'm trying to draw a chart on this for the salary distribution, or not a developed country, let's say underdeveloped country. So then what happens? Okay, so far so good, right? So this is normal distribution. This is negative skewed. Okay. Now let's take an example where we have people very less in the vicinity of mean also. Let's take in some country where we have the salaries, there are very less people which are in the vicinity of the mean. So for us, the mean is somewhere around 5 to 6, right? So if I'm taking a salary distribution for that, okay, now if I notice, this would be called as positive kurtosis. Okay, now there are different examples which we can always take here. Again, if I want to take an example, let's say the countries where we have highly paid opportunities, then the graph would be again negative skewed. That means there will be a lot of people who will be earning in the vicinity of 7 to 8 lakhs. Okay, now the point is why kurtosis has different formulas. So I have also looked into different articles and found that people have actually written the formula for kurtosis in a different way. So observations minus mean divided by sigma whole power 4 expected value of this, okay, minus, this is the right formula, right? If I'm not wrong, expected value of x minus mu by sigma whole power 4 minus 3. Okay, so what people generally do, there are different people has a different terminology for calling kurtosis. They generally call this as absolute kurtosis. Okay, there are a lot of people in world who call this formula as absolute kurtosis, and they call this as relative kurtosis. Okay, the reason why it is called as relative kurtosis because the absolute kurtosis value, it cannot be less than 0. As you can see, it is a power of 4. It cannot be less than 0, right? It is quite simple. Now, if you want to take a perfectly normal distribution curve, you can take it some data, and if you take a perfect normal distribution, you would notice the kurtosis value, absolute kurtosis value for absolute normal distribution would be equal to 3. You can try to calculate that, and this we generally use for comparison, and then we substitute that value here. So we generally do that -3. So that's the reason people call this relative kurtosis. But I generally call this as a normal kurtosis formula, okay? But then it doesn't matter if you call it as absolute kurtosis or relative kurtosis. What importance is, if the kurtosis value is negative, that means the measure of peakedness or the peak would be below normal distribution. For the positive ones, the peak would be above normal distribution. Okay, so that is one thing which we should understand for kurtosis, because kurtosis tells us the measure of peakedness. Okay, and now it's pretty clear that, for example, if I draw normal distribution, let's say this is normal distribution. Okay, let's say that this is normal distribution. Now it's clear that this is leptokurtic, right? Positive skew kurtosis. This is platykurtic, negative kurtosis. So when we have positive kurtosis, the thickness of the peak would be very small in comparison to normal distribution. But here in platykurtic, the thickness would be more in comparison with normal distribution. What does that mean is, lot of data will be in the vicinity of their mean. Okay, in platykurtic. In leptokurtic, there will be very less data in the vicinity of the mean. Okay, making sense? Now, if I'm not wrong, there was some more points which I wanted to discuss. The other one was, what would be the final result in k-fold cross validation? Did you identify the solution for this, guys? So do one thing, because it is very interesting. I want you guys to work on it and tell me the solution in next session. Okay, this and gamma, significance of gamma in SVM. Now the last one is coding challenge. So let's discuss this before we go into the next session, because I want you to work on this. When you work on this coding challenges, you will get familiar more with Python. For example, if I have some data like this, and now you want to find the second maximum number here. Now you have to keep comparing your numbers. For example, if you think that I will use the maximum function and then take the maximum of this series, which is 27, and then I will remove 27 from the series, and then I will find the maximum again, then what you are trying to do is you are using this maximum function 2 times. And this maximum function, how does it work at the back end? It will use a for loop, and then it will compare 2 numbers at a time. So what does that mean is, you are actually trying to, for one maximum function, if you notice, you are trying to compare the numbers how many times. You have to keep comparing your numbers, and then you have to find the maximum number for every 2 numbers. So what I'm trying to tell here is, in short, at the back end, you are running the same operation many times. But if you want to optimize your code, you should think in this way. First, try to compare these 2 numbers. The bigger number would be max. The smaller number would be second max. Okay. And then you have to compare with the new number which is coming in with the max and then second max. Okay. If you try to do in this way, you will notice that the number of operations which you are working would be quite less, and that would optimize your result, the code. So please try to do in this way. So you have to assign the maximum. So every time you are comparing, once the number which is max, that assign that number to say max variable, and the second max number to second max variable. Let's assume that you have a variable with 2nd underscores max and max. But in general, you should not assign the variables in this way, because we already have a function max, right? So you can just say highest and then second highest. So you can assign this kind of variables in Python, and then you can do this coding, and then you can have for loops, and then you can find the second highest number in this series. So in this way you are trying to optimize the number of for loops which you are running here. Okay, so what happens, for example, if you have a number 3 here before 7, then this 3 would be compared directly with the smallest number of these two, and then we know that 3 is nowhere in the scope for second maximum, so we don't have to compare this 3 with 10 now. So these kind of things we have to think for. Okay, so we have to analyze a lot of things, and then we have to write this code. I have already given you the logic. Now try to write this code to identify the second maximum number. Okay, so you will find it very interesting. Okay, so before going into the next session, let's revise what we have learned in the earlier sessions. Okay, so in the earlier sessions we have looked into regression for predictions, and then we have looked into classification algorithms, which can also be used for prediction, but I am not teaching that in the session because in general these algorithms will be used for classification. But of course you can learn the logic how to use this for prediction as well. Okay, so the last session, if I'm not wrong, we have completed k nearest neighbor, and I told you that that was the simple most algorithm, so that you can write your own KNN algorithm in Python using for loops or if else. So you can write your own algorithms. It is always important when you write the code from the scratch, you will understand the coding in a better way, and then you will also understand the machine learning concept in a more depth. You will get a lot of doubts, and you will get a lot of questions in your mind, for which you will explore a lot of things, and while exploring you will learn a lot of things. So it's important that try to write the code from the scratch. If the algorithm is very simple, I recommend you to write the code from the scratch. If not, you can always use the functions in Python which are already there for scalar. Great. Okay, in this 9th week, we were supposed to discuss artificial neural network, but I am planning to keep this at the end now because this is quite complicated, and the next course would be continuation of this. So I have a plan to keep it at the end, because once we complete with this course, the next course will start from this. So let's go to week 11 now. So remember this, this is our 9th session, and we are starting with k-means. Okay, so this is slightly different from supervised learning. Okay, the first thing which you need to understand the difference between supervised learning and unsupervised learning is, see, it's very simple. Let's assume that there is a small baby at your home. You are trying to train them, okay, not to touch the fire, not to touch the hot things, okay, and you're not supposed to eat this, you're supposed to eat this. So now you're training the baby, right? So that is something related to supervised learning. You're supervising your baby, right? But when it comes to unsupervised learning, it's something like you're not supervising it. Okay, now the baby has grown up, he will learn things by itself. Okay, or he already know what needs to be done. He will try to identify the patterns in his learning phase. He have already find the patterns in that. So there is no training, I would say not training phase, but there is no supervision here. Okay, there is no supervision in the sense, how would be the data look like now? In the supervised learning, the data was always supervised by output data, right? X1, X2, X3, so on, and then you will have output variable which is Y. But in unsupervised learning, there is no such supervision here, so there is no output variable Y. It's everything about X1, X2, X3, X4, so on. Okay, now for example, let's take in this way. I'm just giving some examples. I'm not sure about the values, but just consider this some examples. Okay, let's assume that you have this kind of data, and now you are trying to identify there is no output here. Okay, the output is not like there is no explicitly mentioned output here, such as y, which we used to do in supervised learning. What we are trying to do here is we are trying to identify the patterns. Okay, just think in this way. In this case, if you notice, these are some data which are very close to each other. These are the data which are very close to each other. Okay, whenever there is a data which will be here, we can identify that these kind of data are very similar, these kind of data are very similar. And then, for example, these are the data of the dimensions of different components of a vehicle. Then I can understand that, like the domain knowledge what I have with respect to automobiles, I can tell that this looks something similar to brake disc, that this could be the radius of the brake disc, and this could be the thickness of the brake disc, and then this could be the volume, for example. But this doesn't look like a radius of a brake disc. What could this be? I'm just giving an example. This could be the length of heat exchangers, this could be the thickness of heat exchangers, and this could be the volume of heat exchangers in the car, right? So what we are trying to do is, by looking at the data, we are trying to identify the patterns. Okay, and how we are trying to identify the patterns here is by based on their similarity. Okay, so this is one example. What we are trying to do here is we are trying to find the patterns here. Okay, there is no such output y here. So this is one example. The other example, for example, I'm not sure, but if you have noticed in Amazon, whenever you try to buy a mobile, they always try to tell you that people who have bought the mobile, they have also bought this kind of earphones, this kind of chargers or something like that. Have you ever noticed it, guys? Right. So this kind of things are called as recommendation system. Okay, the example which I've given, and this example what I'm given, these are called as clustering, that we are trying to make a subgroups of it using similarity between the data. Here we are trying to find the pattern, here also we are trying to find the pattern. So by looking at the pattern, we are trying to use this data, and then we are trying to do our analysis. So this unsupervised learning has different kind of problems. One is clustering, the other one is recommendation system. The other one could be, just think in this direction, like if you notice, whenever you go to grocery store, you must have noticed that bread is always kept near to milk. Bread is kept near to the milk, or jam is kept near to the bread, or what else can I come with? Again, one is clustering, the other one is recommendation system, and then this one which I was talking about, you must have noticed that people keeping product next to each other in your malls also. If you go to any grocery store or any big malls, and then you're going into, like, you're buying some grocery stuff, you will notice that cold drinks and ice creams are kept next to each other, because it's just that it's a frequent, like whenever someone buys bread, they will either buy milk or they will either buy jam, right? So it's very frequent that people will be buying this kind of items in pairs, right? So this is called as association rule. Okay, but in our course we will be looking at clustering. Okay, because a lot of in interviews and a lot of opportunities outside world, like outside in this world, we would notice that people would be hiring for clustering. And for recommendation system, we generally, people will train you in like working itself, but there will be very less opportunities in recommendation system, because like Amazon, Flipkart, there are some big shots who will be looking for recommendation system, but there will be a lot of companies who will be looking only at the candidates having clustering knowledge. So based on that, we have designed the course. So this is different types of unsupervised learning examples which I have given you here, and we'll go with clustering example. Okay, now to give you one more example on clustering, so this is a mechanical example which I have given. Now let's take a different example here. In this case, if you notice, okay, let's say that you have the data for SAT scores, or let's say CAT scores, their work experience and their domain of for their work X. let's say that you have these three features for different records, and then you have some data here. Okay, and you would notice that, let's assume that there are a lot of IAMs, right? Let's take only IAM A, B and C. Okay, now if you notice, there will be a lot of different data here, and let's say that very high CAT score, okay, very high CAT score and less work experience with any domain would be clustered in one group. Let's say that all these candidates would go into IIM Calcutta. Now, let's say that low CAT score but very high work experience. So this kind of data would be clustered into one group. This kind of would go into IIM Bangalore. And then very high work experience and very high CAT score, this kind of data would go into IIM Ahmedabad. So what I'm trying to tell here is, you will try to find a similarity between the data and then you cluster them. How do you find the similarity? If you remember the KNN algorithm which I've talked about, which was K nearest neighbor. So it's more about calculation, right? Sorry, distance calculation. Here also we will calculate distance between different records. Okay. Now once we calculate the distance, but here the distance calculation would be different. The calculation formula might be same, but the points for calculating the distance would be different in this algorithm in comparison to KNN. Okay, so you don't have to worry about that much. We'll go into that details also, but the basic funda is distance formula again. Okay, now let's go there to the presentation. If you see that we have some data set here, okay, and let's say this is our x1 first feature and then second feature. We have plotted our points, all our data which we have based on the x1 and x2 value. Okay, and now if you notice, these are clustered into one group, these are clustered into second group, and these are clustered into third group. Now the challenge for us is how to cluster this data. That's the first challenge. That is based on distance formula, right? That is one thing. Second challenge is how to decide how many clusters or how many groups we want. That's the second challenge. Okay, so if you notice, clustering is one of the most common exploratory data analysis technique used to get an intuition about the pattern of the data. Okay, so this is also can be used as exploratory data analysis, but most like this is a machine learning algorithm. You can either use it as an exploratory data analysis, or you can use it as a machine learning algorithm, and then you can find the insights out of it. But anyways, whenever you're trying to find insights, anything which you are playing around with the data would be exploratory data analysis, right? So you can perform at the beginning also if you want. But then before doing this, you should always find mean, median, and then 4 business movements, try to draw the graphs and try to understand the data in a better way. Now the second point what we are trying to tell is, it is a task to create subgroups within the dataset, which we have already understand based on the similarities. And then homogeneous subgroups within the data are created in such a way that data points in each cluster are as similar possible to each other, okay, based on the similarity measure. And this similarity measure could be based on Euclidean distance formula or some other measure. And then here in clustering, we are not training any input data with output data, as there is no output, which we have already discussed. Clustering is a method to find patterns without any output feature that we have already discussed. So let's go into the details. So in clustering, there are a lot of different methods for clustering. The first one is k-means clustering, and the second one is hierarchy clustering. There are 3 more which are fuzzy clustering, density based clustering, which is DB clustering, and then model based clustering, MB clustering. But those are advanced type of clustering. You don't have to get into much details, because people generally use k-means and hierarchical clustering only. But most of the people and most of the organization uses k-means, so don't worry. So in today's session, we will be looking for k-means, and in the next session, we will be looking for hierarchical clustering. Okay. Now, k-means is an iterative method, guys. Okay, it's an iterative method which we need to understand here, and how it decides the cluster. It's based on certain rules, and if we can understand these rules, it would be very simple. Okay. First point in this iterative algorithm is define the number of clusters required for the dataset with n data points in a dataset. For example, you have this many n data points here, right? And then let's start with k equal to 3. Okay, we are starting with, let's say, k equal to 3, or let's say k equal to 2. It's up to you, but let's start with some random number for the k value. K means algorithm. Okay, let's start with a random k value. And then the next point is, for example, for this kind of data points, now the first step is define the k value randomly. Okay, in this case, let's take the value of k equal to 3, because by looking at the graph, it is quite simple that the value of k would be 3. But let's anyway start with k value equal to 3. Okay, we can start with 2 also. K is equal to 3, then we have to randomly allocate 3 centroids here. Okay, let's say that for me, this is one centroid C1. Let's say this is C2 and this is C3. So far so good, guys. C1, C2 and C3. Now what happens is all the data points here would try to calculate the distance from C1, C2 and C3. Okay, all the data points would try to calculate the distance from this C1, C2 and C3. Now the points which are near to C1 would come under C1, let's assume. The point which are near to C2 comes under C2. The point which are near to C3, that comes under C3. Okay, now what happens once we have decided that, let's say that for a second step would be, let's say based on the second step, or based on this centroid C1, C2, C3, let's say that this is one cluster. Let's say this is one cluster and this is one cluster. Okay, so this is what we are getting the clusters now. Okay, based on the randomly C1, C2, C3 centroid values. Okay, now once we get these 3 different clusters, we do not have to stop here. We have to keep on doing this process. Okay, now the second iterative process here would be to calculate C1, C2 and C3 again. So now for this cluster, what would be C1? You all know what is C1, what is the formula of centroid? If you have only x1 and x2 features, and then let's say you have 5 records under this cluster. Now let's calculate the centroid based on these clusters. You understood how we got these clusters, right? Based on the distance formula. These all points were very near to C1. These all points were very near to C2 in comparison to C1 and C3. And these points were very near to C3 in comparison to C1 and C2. So that's how we have come up with the 3 clusters. Now, again, we will calculate the centroid. How would be the centroid calculated? Let's say that, for example, we have 5 records for in first cluster. Let's say, and so on. Okay, then sigma of x1s divided by number of observation, comma sigma of x2s divided by number of observations. So that's a simple centroid formula which you can use it. Now again, you will get a new centroid value. Let's say that centroid 1 is now here, centroid 2 is here, centroid 3 is here. Okay, let's assume. Now again, these points, all the data points will calculate the distance from C1, C2 and C3. Okay, and then the points which are near to C1 will come under C1, points which are near to C2 comes under C2, points which are near to C3 comes under C3. Say for example, now we are in third iterative process. Once it calculates the distance, now let's say that these points are coming under C1 based on the C1 location. These points are say coming under C2 and these points are coming under C3. Now what would be the next step? Again, calculate the centroids for the new clusters and then calculate the distance. Again, form the new clusters. Right, exactly. So it's an iterative process. Calculate the centroids and then based on the distance again form a new cluster and for the new cluster again form a centroids. So you have to keep on doing this until unless your solution is converged. What do I mean by solution converged? If you have to keep on doing this until unless your cluster, the data points in clusters are not changing. For example, if this is one cluster, this is one cluster, this is one cluster, and then again if you calculate the centroids and then distances and then again form the clusters, you will notice that these data points are still remaining under this cluster, these data points are still remaining under this cluster, these data points are still remaining under this cluster, and the positions of C1, C2, C3 are not changing with iterations. And then we call it as converge. Something like in our mechanical also, right? If we want to tell that our simulations are converged, we look at the continuity equations and Navier-Stokes equation, right? I'm not sure if you're coming from the thermal background, but let's take a very simple example. Temperature. If you want to say that for one particular component, the temperature has achieved its converged state, then what do we mean by that? The temperature is not changing with iteration, right? Similar to that, your data points under clusters are not changing now, and the centroid positions are also not changing. So this is how we conclude our k-means 3 clusters. So now this was done by 3. Now the second task is how to decide the value of this k. In general, what we do is we'll calculate the values of this. We come up with the clusters of k-means with 3, 4, 5, 6, 7. Let's say we are trying from 3 to 10. Is there any way to reduce the number of iterations? It's a good question, but yes, there is a way. For that, you have to do very good exploratory data analysis. For example, if you have done a very good exploratory data analysis, you would come to know that these points are very near to each other by itself. By looking at the graph, by doing the lot of exploratory data analysis, you would come to know that these points are very similar. These points are very similar. These points are very similar. Then what you can do is you can randomly assign your C1, C2, C3 in such a way that instead of assigning this as C1, you can assign the C1 point as taking all these points and then calculate its centroid, and then you will assign that as C1. Instead of taking one of the points as C1, if you have done a very good exploratory data analysis, you can identify those points visually, and then you can tell that this could be the centroid would be for this would be the mathematical centroid calculation formula. Use that and then take that as C1 and assign all these points to that cluster. Okay, of course you can reduce the number of iterations, but then this is very simple to visualize when you have 3 features. But what if you have 4, 5 features? Okay, at that point of time you have to do a lot of exploratory data analysis to understand the data. If you are able to understand data, no, believe me, this machine learning algorithms will be very simple for you, because what this is telling is the same thing what you will be doing in exploratory data analysis. It's just that the theory or the insights which you will come up with in exploratory data analysis, that will be validated by machine learning algorithms. Simple. Okay, so what I was telling is instead of 3, now you have formed 4 clusters with the same data points. Let's assume with the same data points you have formed 4 clusters. We have formed a 5 cluster, 6 cluster, 7 cluster, 8 cluster, 9 cluster, 10 cluster, or so on. It's up to you. But I generally do it from 3 to 10 or 2 to 10. Okay. There is no sense of making one cluster, because for one cluster, all the points will be coming under one big cluster. So there is no point of making a one cluster. Okay. It's like a data set itself. So do it from 2 to 10. And then once your solutions are converged, calculate the sum of the squares. Sum of the squares in the sense, sum of the squares of the distances. For example, now your final graph would be something like this. K value 2, 3, 4, 5, 6, let's say. And then sum of squares, okay, of the distances. Okay, now let's see that with this data point, let's say with this data point, if I had 2 clusters, and I have finally converged my solution and I got C1 and C2, the distance sum of square, if you calculate the distance between all the points and its corresponding centroid for the given cluster, and then square that, because in the formula of distance you will have a square root, right? You can have a square root if you are using Euclidean. If you are using absolute distance formula, then you will have modulus. So just take a square of that and then add all the distances and then plot here for corresponding to, let's say, your sum of the squares of the distance is somewhere here. Okay. Now, can you tell me if I have 3 clusters? So let's take a new graph here. Let's say that instead of 2 clusters, say that you have a 3 cluster like this. Okay. Now, can you tell me with 3 clusters, the distances would be decreased or increased? Exactly, because we are trying to form high number of clusters, so the distances, the homogeneity would be more within the cluster, so the distances would come down. So let's say for 3 the sum of squares is somewhere here, for 4 it is somewhere here, but as you keep on decreasing, no, you will notice the sum of squares would not decrease that much. It decreases, but it will not decrease that much. So say for example, let's say that this is the trend looks like for some of the squares distances with respect to k value. Let's say that after 5 you notice that the distances are not decreasing much. Then we say that the value of k equal to 5 is an optimal value for clustering. So this is called as elbow curve or scree plot. But why is it called as elbow curve? If you notice, this looks like our elbow. Okay, from here to here and then from here to here, like an elbow. So initially it will decrease rapidly and then it will not decrease that. It will decrease the value of sum of squares gradually. Okay, so what's the point? What I'm trying to make it here is this would be the optimal value of k. Okay, because after this the distances values are not decreasing much. Making sense, guys? Okay, so this is what it is mentioned here. The same point which I've talked, that is the same thing which is mentioned here. I don't want to read this. You can read it if you want. So the same steps are mentioned here. Okay, let's say that there are 5 data points and then you are randomly assigning some 2 centroids, but you can assign these two centroids as the data points itself. For example, A is 1 centroid, D is 2nd centroid. It's up to you. You can randomly assign these 2 centroids and then calculate the distances, come up with a new centroid. With the new centroid, calculate the distances. Again, with this new distances value, come up with a new centroid. So keep on doing this until your centroid position or the data points within the cluster are not changing. Okay, right. So this is all which we need to understand. So you can also write this algorithm from the scratch. Okay, very important thing. If you want, you can write it from the scratch also. Now, as I told, my applications of clustering. So clustering has a large number of application across various domains. So as I told, recommendation system, market segmentation, social network analysis, search result grouping. So you can do a lot of different applications using this clustering. Okay, so now this is the kind of elbow curve. If you notice, sum of squares is denoted as distortion and this is the value of k. Ideally, we should not compute the distance sum of squares with k equal to 1 because it doesn't make that much difference, because when k is equal to 1, it says that you are considering all the data points as one cluster. Then there is no use of using cluster, right? Because when we are using cluster, we have to come up with at least 2 clusters so that we can understand the data in a better way. So from here, the graph goes from the value of k and then it will look something like this. This is called an elbow curve. So by looking this graph, can you tell me what could be the value of k, which could be the optimal value? Okay, if this is the graph, I would choose k equal to 3 because after 3, if you notice, the distortion is not decreasing rapidly. Okay, consider this as your elbow. Okay, and this is where your joint. Okay, so this joint would be your optimal value. Okay, so this is how you can do it. Okay, now I want to tell you something else also here. Very important thing, you can have a lot of input features, x1, x2 and so on. Let's say you have different features such as the price of a car, mileage of a given car, and let's say the dimensions of the car. Using clusters, you're segregating this data, you're forming the clusters. Let's say that you have formed 3 clusters. Okay, and in that 3 clusters, you notice that In one cluster, you have all the data points with very high price. In other cluster, you have all the data points with less price, and you have a third cluster which has a moderate price. And you know that you are reading the data from three vehicles, say Porsche, okay, Mercedes, or say Maruti. Now you understand that I'm just giving an example. So very high price would be for Porsche, right? So this belongs to Porsche. This belongs to Maruti. This belongs to Mercedes. Now what you can do by this is you have X1, X2 and so on. You can create your own output data saying that this data belongs to Porsche, this data belongs to Mercedes, this data belongs to Mercedes, this data belongs to Maruti and so on, and you can come up with your own output. And then once you come up with your own output here, imagine that till here it is your unsupervised learning. Okay, you have come up with your own output using unsupervised learning. So this is from unsupervised learning. And your y is 0, 1, 2. 0 belongs to Porsche, 1 belongs to Mercedes, 2 belongs to Maruti. Now, what we have to do here is, now if there is a new data which is coming in, now think in this direction. Whenever there is a new data coming in, you can consider this data as for your training data and then can be used for your prediction analysis. You can split this data into training and test data set, use this data for your prediction analysis, and then whenever there is a new data which is coming in, predict what could be the y, whether it is 0, 1 or 2. So your final project will be based on this. You will be having a data, you will not be knowing what is your output. You have to do your unsupervised learning, try to understand the data, and then you will identify what is your output. And once you got the output, now there you will be doing your prediction analysis. Okay. So your final project would be based out a combination of unsupervised learning and supervised learning. Okay, let me explain it one more time then. See what happens. Let's say that you have X1, X2 and X3, X4 price, it could be price, torque, mileage, something, I'm not sure. And then you have a lot of data here. Let's say you have 10,000 records. And then using elbow curve, you have used different values of K. And then you have identified that K equal to 3 would be the optimum value. Once you have done the K equal to 3 as an optimum value, you will come up with the final clusters. And you will notice that in this cluster, all the data has very high price value. X1s are very high. Let's say X1 is price. Then you will understand that in this cluster, you have all those cars which are very costly. So these are premium cars. In these cars, you will have the cars which are very low price. So low budgeted cars. In this, you will have all the cars with price and mileage very economical. So these are economical cars. You can actually tell that using unsupervised learning, you have got 3 classes. And now these 3 classes can be used for supervised learning, saying that this would be a Y. This data belongs to premium. Say this is premium 1, 2, 3. So premium 1, 1, maybe 2, 3, 1, so on. So now what you're trying to do is you have using unsupervised learning, you have found the patterns. From those patterns, you have deciding your output, how many classes you can have. And then on this, you can run your predictive analytics for training your model. And whenever there is a new data which comes in, you can decide that this data goes under which cluster or which class. So this is how what we are trying to do is we are trying to improvise our model by combining unsupervised learning and supervised learning both. Okay, so it will go with the older values. See, once you have used this clustering analysis, what you are trying to do is using this clustering analysis, you have coming up with the outputs. And then I'm just telling, it's not necessary that you have to do it. You can use this outputs as for use for supervised learning, and then on this data itself you can split the data again into training and test data set. Okay, and then you can check whether the data is overfitting or underfitting. If it is neither underfitting nor overfitting, then you can use this supervised machine learning algorithm for predicting the output for a new data. So for example, you have coming up with very new raw data, say different values of x1, x2 and x3, x4, and you want to predict that this data belongs to which class of vehicle. Then you can predict. Okay, great. So I want you to come up with the answer for this first question. How does the similarity would be calculated for the if the data is categorical in nature? I think we have discussed this. The answer would be in the similar lines. If you remember the discussion what we had in KNN, the answer would be lying over there only. So you can think on the similar lines and you can come up with the answer. How do you calculate the similarity if the data is categorical in nature? The only difference is KNN would be having the output also, but while calculating the distances, output would not be considered, right? Here also you can think on the same lines. Anyways, there is no output in this unsupervised learning data set. How do you calculate the similarity? See, there are different ways of calculating the similarity. I have just told you about Euclidean distance or absolute distance formulas, but there are a lot of different ways. What you can do is you can also use cosine formulas. If you remember the dot product, A dot B is equal to modulus of A modulus of B into cos theta. So for example, let's say that vector product A dot B is equal to cos theta. And what is cos 0? 1, right? So what does this cos 0 means? That A and B are lying very near to each other or overlapping each other, A and B vectors, right? So the angle between vector A and vector B, if it is 0, then the value of cos 0 would be 1. So based on this cos theta values, you can actually come up with a similarity score also based on this cos theta values also. Lower the theta values, that means there is a very high similarity between A and B. Higher the value of theta, that means very low similarity between A and B. For a value of theta to be higher, this value has to be lower, right? Because we know cos 0 is 1, cos 90 is 0. So higher the value of theta, low similarity, low value here. Lower the value of theta, high similarity and high value here. I'm not sure if you're able to recollect this, guys, this formula, vector product, dot product. So you can use cos theta of this cosine rule also for calculating the similarity score. It's up to you which formula you want to use, but there are a lot of formulas. Okay, now implement this k-means for the given data set and come up with the business insights. So I think you will get the data set also from the team. Okay, so this was all about k-means. In the next session, we'll be looking for hierarchical clustering, and before going into next session, we will look for the Python coding here. Okay, how does the Python coding looks like? So again, I will not be running anything here. If you want to note down, you can note down few points here. So same thing, NumPy, Pandas, Matplotlib, again I don't have to tell all those things. NumPy is used for doing exploratory data analysis. Pandas is used for playing around with the data frames. Matplotlib is used for visualization. Skill-Lync is used for machine learning inbuilt algorithms. Okay. Now just imagine that this Skill-Lync, what we are looking, it has all the functions for which are used for machine learning, right? So in this Skill-Lync, if you remember, we had linear regression, logistic regression, what all things we had in this. Now unsupervised learning is also in under Skill-Lync itself. So let's say this. Under Skill-Lync, we have a function by name cluster, and in cluster we have a function k-means. So we have imported k-means here. Okay. So most of the steps are repeated, guys. Okay. But you have to always keep in mind that you're doing exploratory data analysis. So data frame has been created using pandas, and then you have imported some CSV file. I already had a CSV file by name k-means. And then, so let's run this later on, but first let's understand this. Using this describe function, you know that we will get the value of q1, q2, q3, q4, min, max, count, min, mean, mid, everything. Like a lot of different parameters we will get from here. And then again, we are assigning this k-means to a particular variable with number of clusters equal to 3. Okay. Now I'm printing km, and then I'm using Y as for predict between age and income, because okay, let's run this. So what you would notice that this CSV file, had three features by name, age, and income. So what I have done, I have built my k-means on with three cluster, and that too only on age and income. Okay, because this name would be like not useful for our analysis, so I'm not using name in our analysis. I'm just using age and income. And here y is not our output, y is number of clusters. Now if you notice, I have done a clustering analysis and then I predicted the y. What do I mean by predicting y? I'm predicting that in which cluster this data point would go. For example, the first data point is going under cluster 2. Second data point is going under the cluster. So how many data points we have? 22. 0 to 21, right? So 22 data points we have. And these 22 data points now, some of them are going under cluster 2, some of them are going under cluster 0, and some of them are going under cluster 1. Because we are using 3 clusters, we have only 3 clusters here, 0, 1, 2. Okay, now let's assign these clusters to our data frame so that we can visualize it in a better way. So what do you notice here? This and this and all other ones, there are no ones apart. Yeah, this. So all goes under 1. And if you notice, very high income people are going under cluster 0, and with very low income are going under 2. So what you are trying to make it here is, you are trying to segregate the people or make a cluster out of these people based on their age and income. Now it's very clear that in cluster 0, we have all the people with very high income. In cluster 2, we have people with very low income. In cluster 1, we have people with moderate income. Okay. Now, let's create 3 data frames here. Let's try to create 3 data frames out of this. And what are those 3 data frames? Do we have any measure to assign an output class? What do you mean by that?
Hi sir, I mean we are saying that output 2 is having higher income, output 1 is having mid-level income, output 0 is having low income. That is based on our visual decision, right?
Yes.
Can we have some measure which can just say output 2 is higher, output 1 is mid-level, output 0 is low?
Yes, you can actually, you can find the mean of the income based on this by filtering the values of cluster. Okay, for example, if you're finding the mean of income, say with cluster equal to 0, then you will notice the mean of the income would be very high. And then you can calculate the mean with cluster equal to 1. You can find mean of income for cluster equal to 2. Okay, but yes, you can also visualize that in the plot.
Okay.
Yeah. So now what I'm doing is I'm just trying to create 3 data frames here, because we know that this data frame has all the 3 clusters. So I'm just trying to segregate this data frame into 3 data frames. Okay. Now you would notice something important. So what I'm trying to plot here is when the clusters are equal to 1, I'm just trying to plot the graph here, okay? So by plotting this graph, you come to know that this cluster has all the data points with ages of around 35 to 40 and with very high income. Okay. Similarly, you can plot for other two data frames and then you can understand in a better way to visualize it. Okay. But then there are few things which we need to understand apart from this. Okay. For example, okay, now the first thing which we need to understand is the scale of age is different from scale of income. So when you try to draw the cluster plot, you can do at your end, but when you try to draw the cluster plot, you would notice that there would be some inconsistency. Okay, you would notice that when you draw the plot with this data. Why? Because the scales are different for age and income. And if you remember, when your k-means and knn, this kind of algorithms are based on distance formula, right? And your distance would be completely based on the scales. So for example, if you're calculating the distances, your distance would be highly influenced by the income values rather than age value, because your incomes are very high scale value. So if you remember, I told you to, in these cases, we have to scale down your columns to a values 0 to 1 or using z-scores, it's up to you. So what I'm doing here, I am coming up with a new definition on new function. And what I'm doing is, let's say value, observation value minus the minimum of this divided by maximum minus minimum. Do you remember that formula which I've told you? X minus X min divided by X max minus X min, so that you can scale the values of a feature. So that is what I'm doing here. So I've defined a function, min max function, and that min max function, I'll be using that for both age and income. Okay, I'll be implementing that function on both age and income. Okay, and then I will come up with the new age values and income values. So let's do that. So it's important, guys, whenever you are trying to use this distance formulas, no, it will be good if we scale your all the features in a consistency manner. Okay, let me remove this. So what you notice here is age, income, and the clusters, and then you have come up with a new two features which are based on the formula this. Now all the values of age and income would be between 0 and 1. So now once your features are consistent, now if you do clustering, you will get better results. What I meant is, let's again implement k-means on this and then come up with your new y. Okay, and then assign that new y. Okay. Now, these are your serial numbers. These are your names. This is your old age, like this is your age and income. And this is the cluster which you have created based on this age and income. Now, these are new columns or new features based on age and income, converting these numbers into the range of 0 to 1, and once you have a consistency range for both the features, I'm coming up with a clustering onto this new two features. Now if you notice, this would actually give a better result for us. Okay, how I am telling that? Now I'm coming up again with new 3 data frames. Okay, and then I'm assigning that into plots. Okay, and then I'm creating the cluster centers algorithm, and then I'm plotting it at the end. You don't have to worry so much. What I'm trying to do is I'm trying to segregate this data frame into 3 data frames based on this cluster values, new cluster values what we have. Now if you notice, there are some values which are here. Okay, there is something wrong here while plotting. This income should have not come here. Anyways, so all the 3 clusters are lying here. It's because of this income value we are not able to understand the graph in a better way. Let's remove that income. I don't know why is it coming. This is here. I have to comment this also. Okay, now let's remove this and now run this again. Yes, now if you notice, all the values are between 0 to 1, right? All the income values and age values are 0 to 1, and if you notice, this is one cluster, this is second cluster, and this is third cluster. Okay, and then this is the stars are centroids. Okay, now it looks very good that for this star these are the data points for this cluster, these are the data points, and this is a centroid, which looks very consistent. Now what you have to do is, at home, try to do the same thing for the old data. Okay, you don't have to print all this. It is just telling when we are printing this, that means we are getting the centroid location. You don't have to do all that. If you want to know the centroid location, you can do in this way. Variable dot cluster underscore centers underscore cluster. Okay, you don't have to worry that much. If you want to look at the center coordinates, then you can. Otherwise, you can, if you want to plot, just plot it in this way. Okay, so plot dot scatter. What I'm trying to do here is, here I have plotted those 3 data frames, and here I am plotting those centroid values. Okay, that's the only thing which I'm doing here. And this, by this I'm coming up with the legends, and this show command shows the graph to us. Okay, it looks very good, right? Now let's try to do the same thing, or maybe what you can do is, let's try to do the same thing here with this clustering analysis. When we are not scaling your data, let's try to do the same thing. Okay, let's see what happens. Okay, now what I'm trying to do is, I'm trying to create the cluster with old data without scaling the data. okay, in consistent format. Because if you remember, this age underscores min max and income underscores min max are the new features for us to scale down your data in the range of 0 to 1. Let's not scale down the data. Let's see what happens. There is something wrong, it seems. The feature name is this. Right, the feature name is this. Okay, now if you notice that your clusters are not looking very consistent and your data points are also not very good. These red points belong to one cluster, but this green points are here, these green data points are here also, and the cluster is somewhere else, somewhere here, and then the red data points are here, red data points are here. So what I'm trying to tell here is you will not get the results efficient when you have a scaling issue. So that's the reason first you have to scale down your all the features to a particular range 0 to 1 whenever you are dealing with such algorithms which deals with distance formula. Okay, so now comment this and then run the previous one. So now if you see, it looks so consistent. This makes sense, right? So did you understand the difference, guys? What happens if you do not scale your features to a particular scale? How can you go wrong? Because your distance formula would be influenced by the income value, right? So did you understand this, the difference between the earlier old results and the new results without scaling and with scaling? Great. Now let's look into elbow curve. So I am giving the value of k which ranges from 1 to 10, but anyways, as I told, 10 would not be included from your Python basics and 1 doesn't make any sense, but I'm just using it for the based of calculation, and then I am making a new empty list for sum of squares of errors. Okay, and then I'm using for loop with different number of clusters. I'm trying to fit this k-means algorithm on age and income, that too on the scaled values. Okay, and then I'm printing it and then plotting the values between k and sum of square errors, and then I'm displaying that plot. So this is the one plot of clustering and this is the other plot. So now can you tell me what could be the optimal value of k by looking at this plot? So the value of k would be 3. So this is what I wanted to tell you guys. And k-means is highly, like most of the people use k-means in the organization. So I always tell this, if you're going for an interview, you should be proficient in at least 2 algorithms in and out. And then you should have the knowledge of all the algorithms, but you should be perfect in at least 2 algorithms, because in interview people might ask you what 2 algorithms you have used the most. So, and if you tell k-means and linear regression, then they might ask very in-depth questions in k-means and linear regression, then you should be able to tell all the answers. So my recommendation for you guys would be understand all the algorithms, but before going for an interview, be proficient in at least 2 algorithms, so that in the interview you can tell that these 2 algorithms are the ones which I have used at most of the times. And then when they ask questions on those 2 algorithms, you should be able to tell the answers. Okay. Making sense? So today I have one of my favorite puzzles. Please, I would request you, please try the puzzles as much as possible because this will improve your analytical skills. You have a 10-digit number. Okay, you have to come up with a 10-digit number such that understand this question. This could actually lead you into loops under loops. Okay, so you might have to try really hard, and you might have to come up with a new number, and then you will think this number is wrong answer. Then you will come up with a new number, and then you will think this is also wrong. You will be stuck in a loop. So you will have to do a lot of analysis here. The first digit of this number indicates number of zeros in this number. The second digit indicates number of ones in this number. Third digit indicates number of twos. And then last digit would indicate number of nines in this number. So you have to come up with a 10-digit number in such a way that its first digit should be a count of number of zeros in this big number. The second digit should indicate number of ones, the count of ones in this number. And similarly, last digit should indicate number of nines in this number. Did you understand the question? It's a very highly analytical question, and I would be really appreciating if you can solve this puzzle, guys. So I always recommend try this puzzle. This puzzle is very close to my heart, and then I would say please do not look at the Google. Always try the puzzle at your end and then come up with the answer, because that will improve your analytical skills. Okay.
Welcome to the next session on Introduction to AI and ML using Python.
So I hope all the puzzle. Maybe if your answer is correct, then you can explain this puzzle. Could you please explain your puzzle?
Yeah, so for this, it was not a direct or any method to solve it. What I did was there was a 10-digit number.
Okay.
So initially I put 9 on the first place and put every other number as 0.
Right.
And then I checked. So since 9 is coming in the first place, the last cannot be 0.
Right.
So the last I would cut 0 and put 1. So it was an iterative process. After some time, you get a hang of it. And I reached this number.
Right. I really appreciate it. The puzzle was, we want to come up with a 10-digit number such that first digit tells number of zeros in this number. Second digit tells number of ones in this number. This third digit tells number of twos in this number, and so on. And the last digit tells number of nines in this number. So it's pretty clear that, let's say that there is no right or wrong method for this puzzle, but the approach what he has suggested is amazing. Start with 9 on the units digit, assuming that the number of zeros are 9. That means this all has to be 0. And now if you notice, it is correctly counting all the number of zeros in this number, which are 9, but there is one flaw in this, that here it is 9. So the last digit tells the count of number of nines, right? So it has to be ideally 1. And then if it is ideally 1, then it has to be 8. And then if it is 8, then this has to be 1 and this has to be 0. And then if we have 1 here, this number is a number of, it's a count of number of ones, right? So then it has to be 1. And now if it is 1, now there are 2 ones, so it has to be ideally 2. So you're getting my point, right? So you are actually you will be stuck within loop under loop and loop. And then you have to keep on trying this, and you will come to know that with 8 you won't get the solution. We have already discussed about 9. For 9 there is no solution. Similarly for 8 also there will not be a solution. Similarly, if you try with 7, you will understand that there is no solution. And then when you come to 6, and then if you go under loop, what do I mean loop under loop? You try to analyze a lot, dig as much as you can with the starting digit as 6, and then you will notice when there is a 6, that means there has to be 6 zeros. And now you can place those 6 zeros anywhere, and then you can try, because 6 number of zeros, so number of zeros are 6, which is correct. Number of ones is 2, as you can see number of ones are 2. Here number of twos are 1, so number of twos is 1. And then number of 3 is 0, number of 4 0, number of 5s are 0, number of 6 is 1, number of 7s is 0, number of 8s is 0, number of 9s is 0. So I really appreciate, because this is one of the difficult puzzles which I have ever seen in terms of mathematics. We wanted to discuss few things, right? So the first thing which we wanted to discuss was k-fold cross validation. I'm not sure if you guys have come up with the answer. And then second was gamma. I'm not sure why you're not able to come up with the significance of gamma, because you will, if you explore it on Google, you will get the answer for this. I'm not sure if you're not finding time. So let me explain that now. I'm giving you, every time I'm giving you some amount of time so that you can go back and then you can surf on internet and then you can identify the answer by yourself. By that you will learn a lot of things. But never mind. I'm not sure if you guys have found the answer for gamma or not. Please try to come up with the answer by next session. Okay. So let's discuss this k-fold cross validation. Okay. Now let's take a very simple data set which has 10 data points. Okay. Now what are these 10 data points which I am pointing by circles? Are these features or records? So it can have as many features as it can. So these are records. If you draw a data frame or table, these are records, 10 data points. And then there can be multiple features, x1, x2, and so on. But that's not a concern here, because when we are talking about k-fold cross validation with 10 data points, and let's say that I'm choosing two-fold cross validation. When I choose two-fold cross validation, what does it mean? That I have to solve this 2 times. I have to sample this 2 times. What does that mean? That means this would be training in the first set. This would be training and this would be test. Apply your algorithm, solve it, get the solution. And this would be your first fold. The second fold would be, this would be your test. This would be your training. Now solve it, get the solution. But what should be the final solution in this case? So it's very important to understand what is this k-fold cross validation. See, this k-fold cross validation is not kind of algorithm. It's kind of validating. It's like for cross-checking. Okay. It is used for cross-checking. Okay. So for example, let's say that, see, what people generally do is they get, for example, we are using linear regression. Okay. Let's say we are using linear regression. They will find the R square here. They will find the R square here. And they will take the average of that. And that would be the final R square. But that's fine. We got the final average R square value. But what will be the final predicted value? See, you can average out your R square. Similarly, for example, if I'm using logistic regression, you will get the accuracy score from here. In Python, you can use that score function, right? Get the score from confusion matrix, get the score from here, and then you can average it out. Okay. So for averaging your accuracy or evaluation parameter, that should not be a problem. The problem is how to come up with a final prediction. And that was the question. Now let's assume in this case, same thing, 10 data points. I have not given the answer yet. Please hold on for that. Let's assume that I have a 10 data point now. I am using 5-fold cross validation. What does that mean? It has to be divided into 5 groups, right? In first fold, this would be my test, remaining would be train. In second, this would be my test, remaining would be train. Third, these two would be my test, remaining would be train. So here, as you can notice, with 5-fold here, what we are doing it is 80-20% ratio. With 2-fold, we were using 50-50, right? And then in 4th fold and then 5th fold, as go on, okay? So far so good. Now there are 2 things for me to discuss. How to finalize the value of k. Again, this value of k is not with knn or k-means, okay? Please do not get confused. We have already discussed about knn and k-means. This is k-fold cross-validation, okay? And the second thing which we need to discuss is how to come up with a final prediction. Think in this direction. How would you come up with a final prediction in this scenario? For example, if I want to come up with a final prediction of this point, how would I come up with a final prediction? It was here, it is in test case, test data set. So I am able to find the prediction for this. But in the second fold, it is in train, right? So I have to use the actual values of it, and then I have to build my machine learning model. So in general, what I always tell to my students is k-fold cross validation should not be used for predictions. K-fold cross validation should be used for cross-checking your model. What do I mean by cross-checking your model? For example, let's say that, let's take in this scenario in 5-fold cross validation. Let's say with this sample, I got 70% of accuracy. Let's say you have built the model and you got the accuracy for this using this, okay? First fold. Assume that you are not using anything. Assume that you have already directly built the model and then you got the 70% of the accuracy. And now you want to dig further. When you dig further, you will notice that these 2 points were chosen as test and the remaining were train. Now, for better understanding, what we should do is we should convert this test from here to here. We should replace our test data set. And then you would notice the accuracy somewhere around 71%. And then you can notice here I'm getting the accuracy, say for example with this, say 75% of accuracy. Say here I'm getting, say for example, 74% of accuracy. Say here I'm getting 77% of accuracy. Now it is just for checking your scores and comparing. This is used for cross validation. Okay, you are validating your model with other folds. Whether the model which I have developed by taking this as a test data set has been a right thing or not. For example, if I'm proceeding with this 70% is my final model, and you have already noticed that this is a 77%, which is giving a very high accuracy, then it's pretty straightforward. The final accuracy, what I am getting here, it is overfitted, right? It is overfitted because in this model, the accuracy what we are getting is around 70%. And let's say in all the cases, your training accuracy is around 80%. Let's say that the training accuracy is around 80%. Now it's giving us a hint that if we are using this model, then what we are getting is overfitted result. Okay, so what does this mean? That the sampling is very important. Okay, so this is where sometimes what happens, say for example, you have a set of data points, say 10 in this case also, I'm just giving examples. Okay, and this remaining 8 points have the same criteria, like 1 and remaining 8, so total 9 points have some characteristics. This point altogether has a different characteristic. So it will be very difficult for machine learning model to predict the right output for this data point. And that's the reason that you might be seeing the accuracy very low. But what if you convert this point itself into training data set? So this all analysis should be done with the help of k-fold cross-validation. You should not use these models, all the 5 models for your output. It's not the case. It is just used for analyzing your output. See, I'm not sure people might use it as a final solution, but for me, I always tell this is not a way, this is not an algorithm to predict something. It tells that what different samples have a different characteristic, or it is just used for analyzing your outputs. Okay. So to understand whether the model is overfitted or underfitted, take one more example here. Say I have 10 data points. Okay. Now how to choose this value of k? Now let's say I am choosing the value of k equal to 10. What does this mean? How many data points will a test data set will have? What will be the ratio of training and test data set in this case, guys? 1 and 9. So this would be test in first fold, this would be test in second fold, so on up to this would be the test for 10th fold. Now it's pretty straightforward. When you have very high value of k, you would notice that in the training data set you will have a lot of data points where you are actually building the model, but then it would be very difficult to generalize this onto this single point. Okay, so what I'm trying to tell here is, higher the value of k, you will have very less data points in your test data set. So by this, what you are trying to do is, you are trying to overfit your model. Okay, that is one thing. Now, can k be very less? Now you have already noticed what happens when k is very less. With 10 data points, if k is equal to 2, you have noticed that test and train will have exactly 50-50%. Right? So is it the right thing to do? Now, this would lead to underfitting of your problem. Okay? So you have to choose the right value of k. Okay? But in general, you should understand why the sample is giving 77% and why the other sample is giving 70%. So you should try to analyze that. That is more important. But yes, you can go ahead with that sample. Okay. So today's session, we will discuss about hierarchical clustering. Okay. And then we will do some Python coding for today's session. And today we will be having a lot of time for Python. So we'll 6 of Python also today, some more simple examples, some coding challenges. Okay. Because hierarchical clustering will not take more time now, as you have already learned what is k means. I hope you guys have already got the solution for first question. How does the similarity is calculated if the data is categorical in nature? It is something similar to the way we have looked in KNN. You can check that. Okay, so let's start with unsupervised learning, which we have already started in the earlier session. Let's continue with that. So we were discussing about clustering. So in clustering, I told there are different methods of clustering, but we'll be looking for two methods, which is k-means and hierarchical clustering, because these are the two methods which are in general used majority of the times in the organizations. So what happens is, if you remember in k-means, the records or the data points were compared with the centroid and we have calculated the distances, right? Here the nodes or the data points are compared with each other. Okay, so that to identify the similarities. Okay, now what happens in this, to explain it in a better way, let's say that you have 10 records again. Okay, now those are somewhere in space depending on how many features or what dimensional it is. Say we have only 4 features, so it is a 4-dimensional, right? So let's say that these are the data points in space, assume that. Now what happens in this case, the only difference between k-means and in hierarchical clustering is, in k-means we have calculated the distances from the data points and its corresponding centroid, right? But here the distances would be calculated from one point to another, from one point to another, and so on. Like for example, I have 10 records, and if I want to calculate the distance between all the points among each other, okay, every point will have 4 features, okay, x1, x2, x3, x4. Let's say that all the 4 features are numerical, okay, or continuous. Now you know that you can use Euclidean distance formula for calculating the distances. But I have a question before going ahead. It's very important for me to always check your mathematical knowledge here. For example, I have 10 records, then how many times I should be calculating the distance formula? How many times distance formula should be evaluated if I have 10 records? See, I have to calculate the distance between this point to this point, 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 this point to this point. I have to calculate the distances between all the 2 points, right? The distances can be calculated 2 points at one point of time. If you want to calculate the distance, you have to select 2 points, right? And then you have to calculate the distance. I know how did you get the answer 10 into 9. Okay, got it. So ideally when we calculate the distance, say from this point to this point, we should not calculate from this point to this point distance, right? Because we have already calculated that. So for example, let's take in IPL. In IPL, there will be generally 8 teams, right? So if you want to conduct round robin, there will be 8C2 matches. Of course, they play twice with every team, but that's a different story. But if they want everyone to play among themselves in a round robin, that would be 8C2, right? So here also it would be 10C2. So which is 10 into 9 by 2, which is 45. Okay. So this is your right answer. But then yes, it's understood that this should not be repeated. Okay. So we have to calculate the distances, and based on the distances, so this distance, what is this distance doing for us? This is a similarity measure. Similarity measure, this distance formula. And based on the similarity, you would come up with the clusters here. Okay, for example, let's say that these are the 9 data points you have. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. These are the 9 data points which you have. Okay. Now, See, the only advantage of hierarchical clustering is it gives you a better visualization of clusters. Okay, but then there is a disadvantage also. I'll just tell you. So this figure, what you are looking at, it is called as dendrogram. So hierarchical clustering will always be represented by a dendrogram. Okay, so for example, there are 9 data points in the space, and then you calculate the distances from all the data points. Okay, let's say you have already calculated the distance. Now you have noticed that these 2 points are very near to each other. Okay, so don't compare the distance by looking at this in this space in the horizontal line. Okay, don't assume that these 2 points are near to each other in space. Okay, these 2 points are near to each other in the space. So if you consider that in the horizontal direction, then you might assume that this point is also very near to these data points. So these are not the location of the data points in the space. These are just, there are 9 data points randomly in the space. These 9 data points are randomly placed in the space. Okay, so I've calculated the distance. I've noticed that the 2 points here are near to each other. Okay, so let's say that those 2 points are near to each other, and then those 2 will form a kind of this 2 point will lead to a single branch now. So now what is this vertical direction is giving you is the distance between these 2 points. This is how the dendrogram is created. Try to understand this. Okay, it's very important. The distance between these 2 points is denoted by these vertical lines in the dendrogram, and then it will place these 2 points next to each other in the dendrogram figure, and then it will check which could be the next point which is very near to this. They will notice, the algorithm will notice that this point is very near to these 2 points. Then it will create a third node, and then it will be calculated from here. Okay, so this point will be joined to this branch, and then distance would be this. Distance would be given by this. If you're not able to understand the distance, that's okay, don't worry about that. But what I'm trying to tell here is this 2 point can be formed a cluster based on this distance value. But if this is the distance value, maximum distance value which we are looking for, then these 3 points can be formed as a cluster. Similarly, here in the space, these 2 points are very near to each other. And then this is the distance between them. And then there will be third point which will be slightly far away from these 2 points, and that would be also forming a cluster here like this. And similarly, there would be some more 2 points which are very near to each other, and then somewhere like this. And then this is how your dendrogram is formed. Okay, so you're getting my point, right? There will be a third point which might be very near to these 2 points then. So there will be a third point which will be coming and appending to this branch. So that is how the dendrogram has been created. But what is important here is we need to understand how many clusters are we looking for. For example, if I am looking for one cluster, ideally we will not have one cluster, right? Then there is no use of using clustering then. Then I will cut the branch here. Then what happens? All the data points will be in one cluster. Okay. If I cut the branch here, you will have one cluster like this, and the other cluster would be this. All these data points. Now, if I cut the branch somewhere here by this blue line, then can you tell me how many cluster will I have? So when I cut the cluster here with this blue dotted line, can you tell how many clusters I am forming? 4. Just check how many branches we are cutting here. 1, 2, 3, and 4. So there are 4 branches which we are cutting. So there will be 4 clusters. So the first cluster has 3 points, data points. Second cluster has 3 data points. Third cluster has only 1 point. That means this point should be really far. Okay, and that point would not be very near to any other point. So that point would form a separate cluster. Okay. And then there will be these 2 points in this fourth cluster. So in this case, you have to study the data and then you have to decide how many clusters do you need. Okay, you have to decide in hierarchical clustering. But in k-means, you can always come up with an optimal value of k, number of clusters. But that's a disadvantage in hierarchical clustering. And then the one more point is, if you notice, for 9 data points, we have so many branches. Assume I have 10,000 data points. Then how many lines you will be seeing on this? It will be very clumsy and it will be really difficult to understand the data points, right? To understand this and to read the data or to read the dendrogram. So it will look really clumsy. So one more disadvantage is of hierarchical clustering is it cannot be properly visualized when you have many data points. So for those cases, we generally go with k-means. Okay, great. And then disadvantage of k-means would be you already know. You won't be able to visualize the data in a better way in k-means. Okay, so that was the thing which I wanted to discuss. But before going ahead, I want to tell you that in hierarchical clustering, there are 2 approaches. Okay, one is agglomerative approach and the other one is divisive approach. Agglomerative approach is a bottom-up approach. Okay, so what happens in this method is each node represents a single cluster at the beginning. Eventually, node starts merging based on their similarity and all the nodes belong to same cluster. So the figure what I'm showing here is kind of agglomerative hierarchical clustering. That means bottom-up approach. That means all the points will initially be each one cluster separately. And then based on the similarity score, they will try to merge. Now this can be one cluster. And then based on this similarity, this is also coming and merging here. So now if you want to cut our branch here, and if, for example, if you want 4 clusters, then this will form one cluster, right? So that is what bottom-up approach means. The other method is divisive approach, which is called as top-down approach. In this, initially all the nodes belongs to the same cluster. Okay. In this, what happens? All the nodes will belong to the same cluster. That means that first cluster. And then eventually each node forms its own cluster. So for example, what happens initially, all the data points will be forming one cluster, and then based on the similarity score, there will be some nodes which will be coming out from that cluster and it will form their own cluster. But then if you notice, divisive approach is less widely used because the complexity would be more here. But in bottom-up approach, it is very simple because every point is represented as single cluster initially, and then they will merge based on the number of clusters and or based on their similarity score. So here, as you have seen in k-means clustering, we had final optimal k value. In hierarchical clustering, you can always change the value of number of clusters which you need, and then based on that you can cut the branch. And then, which I've already told, hierarchical clustering works especially well with a smaller data set, because for the higher data sets the visualization would be quite complicated. Okay, so in this case you have to predict the output by using all the supervised. So this is our final project, guys. Okay, let's not go into this, but I'll just try to explain you what I'm trying to tell in my final project, which you guys have to work on it. So predict the output by using all the supervised machine learning algorithms and identify the differences in the result obtained using these algorithms. So the first project would be, which I've already told you last time, you can implement all the supervised learning at one shot by creating a user-defined function. Remember, guys? Yes or no? Right. So you can use that on the same data set which we will be providing to you, and then you can run that. But I would be happy if you work on second challenge or second project here, because that would be slightly complicated. What happens here, you will be having the data sets and you don't know which is your output here. There will be x1, x2 and x3 and so on. Okay, so there is no y, assuming that there is no y because it's an unsupervised learning. So first you have to perform clustering, and then you have to come up with your new feature, which is your clustering number, right? Remember cluster number 0, 1, 2, 3, what we have done yesterday in k-means. So that would be your output. Let's assume that would be your output feature, that the data point belongs to which cluster. So that is your output feature. And then try to understand the differences between these clusters. Okay, and then try to check that, try to split your data into 70-30 or 80-20 and use the predictive algorithm, that is supervised algorithm, and check whether your algorithm is also giving you the same cluster or not. Did you understand this, or shall I repeat it? I think I have to repeat this. So let's say you have some x1, x2 and so on, say xn. You have first record, say second record, and then say so up to 10,000 records. First, perform clustering analysis. Say you are working on vehicle data set, and then you will find the output, say, and you have found the optimal number of clusterings are 3. Say 1, 2, 1, 3, 1, 1, 2, so on. So these are the cluster numbers. Okay. Say these are the cluster numbers. Okay. Now let's say this is your output. Now we have used the unsupervised learning, you have found the output. Consider this as your output, and then you will understand the differences when you read the data. That one, all the data points cluster 1 has their own characteristics. All the data points with cluster 2 will have different characteristics. And all the data points which are going under third cluster will have different characteristics. So what you can do is, what I'm trying to tell is, once you are done with this clustering, unsupervised learning, split the data, say 80-20, then 8,000 would be in training data set and 2,000 would be in test data set. And then train your model on 8,000 and then consider y is your output, and then predict the output for this 2,000 data sets and check what is the accuracy which you are getting for predictive algorithm or classification algorithm. Check what is the accuracy which you are achieving. So by this, what you are trying to do here is, you are trying to define the outputs first by your own using unsupervised learning, and then you are also trying to predict your output, what you have got in unsupervised learning, by supervised learning. I think it's very intensive what I've told just now, but yes, I've already repeated. Okay, now this is the thing what we have to do. And now if you notice, we have completed the concept for all the 10 weeks. Those 2 weeks will not be having any influence on your final project. But it's important to know those 2 topics also, because when we go into advanced machine learning, because if I'm not wrong, the second course, there will be another course which will be starting. In that, we'll be looking into complete mathematics of machine learning. Okay, so in that, and then the third course would be purely advanced machine learning, which will be deep learning. So for that, we would require those 2 weeks of agenda and the content. But for this course, the final project, it's in front of you, and this will not be influenced by your next weekend course. So the remaining 2 topics will not be influencing your final project. Okay, great. Now, before going into the Python coding, I want to ask a puzzle for today's session. The puzzle is very simple and very straightforward. It could be quite simple for you guys. I have a chessboard, and you know that chessboard would be of 8 by 8, right? Now in this chessboard, what we need to understand here is, you know how does rook moves in chessboard, how does queen moves, how does horse moves. You know how does queen moves, right? Queen moves diagonally or straight. So I know that in real time there will be only two queens on the board, one from the black side, one from the white sides. But what I'm try to understand my puzzle here. So there will be 8 by 8 chessboard, and now in this 8 by 8 chessboard you have to place the queens as many as you can. Understand this, you have to place the queens as many as you can so that they are not killing each other. Did you understand this? That you have to place the queens as many as you can. For example, if there is one queen here and the second queen is here, the first and second queen can kill each other, right? Because queen moves in straight direction or diagonal direction. So you have to place you have to place as many queens as you can in this chessboard so that they do not kill each other. And you have to tell me what is the maximum number of queens that you can place. What is the maximum? If I don't tell maximum, you will tell that I can place 2 queens, 3 queens, but I want what is the maximum number of queens that can be placed on this 8 by 8 chessboard such that they are not killing each other. Okay, and then what is the strategy to place this maximum number of queens? So that please, as we are completed 10 weeks of course, which would influence your final project. So please start working on your challenges and complete the challenges, because then it would be helpful for us so that we can understand, are you able to understand the course or not in a better way or in a right way. Like first you are trying to understand the thing by yourself. For example, if you're stuck somewhere in while working on your challenge, rather than asking for a support, you are directly looking for your own help by looking at all the different things. For example, textbooks, or if you have bought one, or for example internet, you are trying to explore a lot of things, then also you're not able to get the answer, then please contact us for the solution or for the support. But then what I'm trying to tell here, when you explore by yourself, you will understand a lot of things, you will understand a lot of other things as well. Okay, and once you complete this course, challenges, project, then you should be able to apply, you should start applying for the jobs as well. Okay, and that it's so at if you are looking for a opportunity right away, then you should start working on this right away. Okay, great. Okay, so if you remember, this is a yesterday's data set, what we have done for k-means algorithm. And what we have done in k-means algorithm was we have imported the data using pandas, and then we have built a k-means algorithm, and then we have found the what data points will go under which cluster. Sorry, and then we have divided our cluster based on the numbering of the cluster, and then we have noticed that the visualization or the results were not good, but the reason was the scaling of the features. So because one of the features is having only 2 digits and others feature has around 5 or 6 digits, so your distance formula will be highly influenced by income. So what we have done was we have actually brought down both the features into a same scale using this user defined function which we have created, min max. Okay, and then again we have implemented k-means on that, on the new features, and then we have separated our data frames based on the cluster numbers, and then we have plotted that into a scatter plot, and then we have visualized that, and we have noticed that it was looking quite good. That means with very high efficiency. Okay, so now and then we have looked into elbow curve also in the k-means algorithm. Now in hierarchical clustering, same thing from scikit-learn or from SciPy. So you have to find the difference between this SciPy and sklearn. Okay, note down this. What is the difference between sklearn and SciPy? Okay, and tell me the answer in the next session. So from SciPy, what I'm doing, I'm importing clusters. From clusters, I'm importing hierarchy. And from hierarchy, I'm importing dendrogram and linkages. Okay. Now, before going into this linkages thing, now you must be thinking, what is this linkages, right? So in hierarchical clustering, so linkages, there are three different linkages: simple, and then complete, and the last one is average. Okay, simple, complete, and average. So I'll tell you what happens with all the three linkages. So sorry, my bad, this is not simple. That's what I was not able to recollect. Yes, single, complete, and average. Okay, so single, what happens in singles, for example, you have formed a data points. Okay, and you have formed a first level of clustering. So what happens, and then you have to calculate the distances again and again, right? Because you will calculate the distance and then you will form the first level of clustering, and then you will calculate the distance again between the clusters. So now, for example, like the way we have done here, for example, this is one cluster and this is one cluster, right? And then we have to calculate the distance between this cluster and this cluster, right? So you must be noticing, how do we calculate the distance between this cluster and this cluster? So it's not a way that we calculate the distance from this point to all 3 points and this point to all 3 points. Initially, it will calculate the distances between the points, because every point is considered to be as a cluster in a bottom-up approach. But as we move up from bottom, as we are moving up, that means we are actually making some clusters, right? So once we form some clusters, then we have to calculate the distances and we have to keep on moving towards from bottom to up, right? So for that, there are three different ways of calculating this distance. How do we do that? What we do, we use single linkage. What does it mean? We calculate the distance between the nearest point of two clusters. Okay. And do you know how to calculate the distance between these 2 points now, right? That is a single linkage. Okay. And then based on that, we form a next level of clustering. This is one single linkage. In complete linkage, what happens? Of course, then the distance should be minimum, right? Then only we'll form the cluster. The second way, or the second linkage, which is complete linkage, it's up to you which linkage you are choosing. Okay. In second linkage, what happens? You will choose the farthest most points from these two clusters, and then you will calculate the distance. And based on this distance, again, there will be a lot of clusters, right? Again, there will be a lot of initially there will be a lot of clusters, right? So based on this farthest point distances, the one which has minimum will be combined to one cluster, right? If you notice this, always refer to dendrogram when you are confused. Okay. So that is complete linkage. In average linkage, what happens? If I'm not wrong, you can correct me, but it's been a while that I've used average linkage. You can correct me if I'm wrong. Like maybe you can also check what is average linkage at your side, and then you can tell me in the next session. But I've used single and complete linkage most of the times. So in average linkage, what happens? You will calculate the distance from all the points to all the points here, and then you will take the averages of the distances. Okay. Okay, what is its function? It's quite simple. For example, see, initially we are dealing with bottom-up approach, that you have to remember. Okay. Now all these points are single clusters, right? Now when you calculate the distance between the points, then you know that you can directly go and calculate Euclidean distance formula. Based on the distance, you know that these 2 points are very near and this will form a cluster. Now there would be a lot of points in the space, right? So for example, let's say that there are 3 points. Let's assume that there are only 3 points, 1, 2 and 3. Okay, let's take some other color here, not to confuse you. Let's say there are 3 points, 1, 2, let's say 3. Now we know 2 and 3 are very near to each other, so it will quickly form a cluster. By calculating the distances, these two will form a cluster. Now, as it is a bottom-up approach, what does it tell? Initially all the points will be its own cluster, and then slowly points will come and merge on it based on the similarity score. So now one also should calculate the distance from one to this cluster, right? See, between the points it's easy to calculate the distance, but how will you calculate the distance between point, say point which is 1 and the cluster which is forming by 2 and 3? How do you calculate the distance? Will you calculate 1 and 2 and 1 and 3? But in the dendrogram, if you notice, the distance would be represented by only single value. This is a distance, right? This is the distance between this point and these 2 points. It's not the actual distance between this point and these 2 points. What it is trying to tell is, this is the distance, this distance is a distance between this point and to its corresponding cluster, because then there will be 2 distance values, right? So not to confuse that, the simplest way how to find a distance between a point and a cluster. So for that, there are 3 different linkages which people use. One is single linkage, complete linkage, and the third one is average linkage. Okay, in single linkage, what happens? The distance between 1 and this cluster will be calculated based on the nearest point. For example, 1 is near to 3, right? So this would be the distance which would be calculated and will be represented in the dendrogram. So that is called as single linkage. In complete linkage, this, for example, let's say that there is one more cluster here with 4 and 5. So now one has to go with 2 and 3 or 4 or 5. That is important, right? So when we are using single linkage, one would calculate the distance from 3 and one would calculate the distance from 5. And then based on the minimum distance, it will get associated with that cluster, like the way it is shown here. That is a single linkage. But if it had to be a complete linkage, then what it does is, it will calculate the distance from 1 to the farthest point, which is 2. And it will calculate the distance between point 1 and the farthest point in this cluster, which is 4. And then based on the minimum distance, this one will be associated with either this cluster or this cluster. Now, in average linkage, what it does, it will calculate the distance. One will calculate the distance between 2. The distance will be calculated between 1 and 2 and 1 and 3. And then the average value will be taken. Similarly, the distance will be calculated between 1 and 4 and 1 and 5. The average of those 2 distance will be taken. Now the one which is minimum between these 2 averages value, one will get associated with that cluster. So calculating the distances between points is pretty straightforward. Calculating the distances between clusters is a difficult thing, because if you notice, at this point of time, if I cut my branch here, you would notice that these 2 would be a one cluster. This point would be a separate cluster, right? Now if I cut my branch at a top level, then will this point get associated with this cluster or with some other cluster? which is here. For that, it has to calculate the distance, right? And then how does it calculate? At the first level, it's pretty straightforward. All the points are considered as individual clusters, and then it will calculate the distances among themselves. But at second level, it has to how will it calculate the distance? At the second level, in the sense when some of the data points already formed a cluster like this, then it has to calculate the distance based on this linkages. Okay, so it's good that Python has reminded me these linkages, and then otherwise I would have forgotten to explain this. Yeah, so same thing, import dendrogram and linkages. Okay, and then you're putting all the points here X, and then you are using this linkage function, and you're telling that implement single linkage. You can use complete or average, it's up to you. Okay, and then you can actually put the label list, whatever you want, like how many clusters you want based on that, and then you can try working on this. So I have not written this code completely for hierarchical clustering because I want you guys to work on it, and then you have to come back and tell me whether you are able to write a code or not. It will be very similar to k-means. It's just that you will be seeing dendrogram with different linkages. That's it. In k-means, it was k value and elbow curve. Here it is dendrogram and linkages. Okay. Now, so far so good. Before proceeding, I want to tell you one more thing, guys. Okay. Now, if you remember the sampling techniques in the first session which I've talked about, simple random sampling and stratified sampling, right? This would be an interview question. Okay. This has nothing to do with unsupervised learning. This has to do with supervised learning. I forgot to tell you this while teaching supervised learning. Say you have n features. Say you have 10 records. Ideally, you will not have 10 records. There will be a lot, but I'm just giving an example. And then it's a binary classification. You would notice that say you have 9 zeros, that means 9 records are going into data point or class 0, and the 10th record is going into the class 1. Then how would you solve this problem? How would you predict it? I think I've already given you examples for this in k-fold, right? So this one cannot be there in test data set. You have to remember that. Ideally, this one cannot be there in test data set, right? So your simple random sampling, if you're using say 80 by 20, and then say randomly it has taken 8 records of 0 going into train, and then 2 records, one with 0 and one with 1 going into test. Then just imagine how will your algorithm predict the output 1 when you have not trained your model on this? Did you understand this? So this is very difficult to solve this kind of problems. If this a single record going into the test data set, okay, then it will be really difficult. But imagine that you have 2 classes or 2 records which goes into class 1, and then there are 8 records which goes into class 0, and now you're doing training, you're splitting your data training and test data set using 80 by 80 20%, and then assume that all this 8 records going into training and this going under test. Then how would you solve this? Then again it would be really difficult, right? So in this case, instead of using simple random sampling, you have to use stratified sampling, guys. So you have to use stratified sampling. What stratified sampling tells is you have to make sure when you're sampling, you get the right proportions of 0 and 1s. What does that mean? Say you want to split your data into test and train data set, and the proportions should be equal. The proportions of 0 and 1s in test, 0 and 1 in train should be same. What does that mean? Ideally, you should try for that. For example, if I'm doing 80-20%, then seven zeros and one should go here. 1 0 and 1 should go here. You're getting my point? What I'm trying to tell is you have to split this. You have to make sure that this one is going into both test and train. Yes, equal diversity, exactly. So this one is going into both test and train. Okay. So what in general people does it, for example, say you have 8 zeros and 2 ones, then ideally, okay, you are taking 80% into training, right? So 8 into 8, that means 6.4 zeros, or let's not take this as an example. It will give you fractions. So let's do one thing. Let's say you have 100 records, 80 zeros and 20 ones. Okay. And then you want to split your data into 80/20 as train and test data set. Then we know that there should be 80 records in training and 20 records in test, but we have to make sure that the proportion should be same in training and test. So what do I mean by that? Then 80% of 80 would be 64 zeros, and 80% of 20 would be 80% of 20 would be 16 ones. So ideally in your training data set, you should have 64 zeros and 16 ones. Then how many zeros will be there in test data set? How many zeros and how many ones? Right, 16 zeros and 4 ones. That tells that what we are trying to do is, by stratified sampling, we are trying to make sure that the proportions of zeros and 1 in training data set should be same as test data set. So it was very difficult to explain that with the same example of 10 records. That's why I have chosen 100 records. So in test data set, you will have 16 zeros and 4 ones. Finally, you will have only 20 records because you have splitted your data set in 80/20. Okay. In Python, there is a separate syntax for this, for stratified sampling. You can look into that, but I wanted to explain this. So people will ask you in the interview what kind of sampling analysis which you will be using for splitting the data when you have imbalanced data set. No, there is a new term which is coming in, imbalanced data set. What does this imbalanced data set means? Imbalanced data set means your output, if your output has a binary classification, then one lot of records are with one classification, and then there are very few records with other classification. This is called as imbalanced data set. Did you understand this? So this is a very famous interview question. People will ask you, how will you tackle your splitting the data into training and test data set when you have imbalanced data set? Okay, so you can take this 100 data points example and then you can explain them. Okay, so before we proceed, let's do one coding challenge, guys. Okay, because I have to make sure that you guys are working on Python also. So it's very important for me. So do you all understand what is Fibonacci numbers? Everyone, do you all understand what is Fibonacci numbers? Just quickly brief you what this Fibonacci number means. For example, I'm starting the series with 0 and 1. Then the Fibonacci series will be formed by these two numbers only. The third number would be adding up this. The fourth number would be adding up this two. The fifth number would be adding this two. And then so on. 5, 8, 13, 21 and so on. So this is something which we have not learned in mechanical, but I just want to have this coding challenge. Fibonacci series. So what we are doing is my first number is 0, my second number is 1, and then see, if I want to generate a series, I have to use for loop, right? So let's use for loop for I in how many numbers we want. Let's say we want only 100, for example. Okay, now my third number would be first num plus second num, and then I'm printing this x. For example, let's say that I'm printing this x. I'm also printing. Whenever you don't know, you can write individual syntaxes in individual lines, but I'm also writing in individual lines because I don't want you to confuse. So now your first number would be equal to second num and second number would be equal to x. Now what happens here? For I equal to 0, it will go on to the loop. It will calculate the value of x and then it will print x. That will be a third number. Now we are changing our first number with second number and second number with x. Then it will take I equal to 1. It checks whether it is in range of this or not, and then it will go into this loop again. And then again it will calculate new x with new first num and second number. Okay. And then it will print that x, and then again it will replace first number and second number, and it will keep on doing this. Did you understand this logic? Are you able to identify any flaw in this logic, guys? So 0, 1, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, 3 plus 5 is equal to 8, and so on. Now, for example, if I want to stop this series, if I'm getting a number which is greater than 1 crore and I want to stop this series, so how should I do that? I have to write if loop, right? If x is less than or equal to, say, 1 crore, then only this should be printed. Else print number is greater than a crore, rather than counting number of zeros. I don't want to do that now. Okay, so now what happens, guys? Now if I run this syntax, run this code, you would see that it has run the code till we get less than 1 crore. As soon as we reaches greater than 1 crore, it is printing that else syntax again and again, right? It is printing this else syntax again and again, and it is not a good habit to do that, right? So what should I do? I don't want that to be printed again and again, because I know after this, once this sentence has been printed by number is greater than a crore, then we have to stop it, right? Because we know that. So what should we do? There is something called as break, if I'm not wrong. It's been a long while. Yes, exactly. Break the program. There is something called as break. It's been a while I've used this. So let's see if it works. So now let's run this. So it's working. So as soon as it reaches greater than 1 crore, it says the number is greater than a crore. And then once we are breaking it, that means it is coming out of this loop. So by this, what we are trying to do? By this, what we have done is, for example, let's say that so by this, what we are doing, instead of running our for loop again and again, it has stopped as soon as it goes into else loop. What we are doing here is we are limiting the number of operations. We are limiting the loop. So this is called as performance. So when you go into the industry, people will ask you to write optimized code, right? You cannot just keep the code like this. It will be wrong, because then your loop will be running 100 times, and it's not useful, right? So it will actually create an operational issue, performance issue. So that's the reason we have to always write the code which is the optimized code. Okay, now I will write few things. I want you guys to tell me what will be the output. I want to make sure that, because when you go for an interview, there will be a coding challenge in the interview. Sometimes they will be having a written test where they will be giving some code and they will be asking you what will be the output for this. Okay, so you have to tell me what could be the output for this. What will be the output for this? You have noticed that I have changed the code slightly by putting one more asterisk, right? So 0, 4, 9, so on up to 9 square. How did you get 324? Oh, I think you have taken, oh, okay. I think what you have done is you have taken this. You have taken this, if I'm not wrong. You have done this. 2 square, 2 cube, 2, 3, 2 power 4, 2 power 5, so on. Okay, no problem. Okay, great. So now what will be the output? Very simple, right? What will be the output now? So this is important. People will ask a lot of questions like this to confuse us. See, whenever I put a quotation, single quotation or double quotation, that means now this number has been converted from number to a string. Now if you hover your mouse here, you will notice that 22 is a string now. So it will take it as a string and it will concatenate that 2 times. If I write 3 here, it will concatenate that 3 times. Okay, great. Okay, now you guys have one coding challenge from my side, guys. Okay, you have to put some number, say x equal to 1 2 3 4 5. Let's say that this is a number, and then you have to tell whether this number is a palindrome or not. You guys understand what is palindrome? See, the reason why I'm going into this few small things of coding, because in the written test, this kind of codes you will notice in your multiple choice questions when you go for an interview. So 1 2 3 4, which number is palindrome here? 1 2 3 4 5 or 1 2 3 2 1? Out of these two, which number is palindrome? 1 2 3 2 1. Okay, cool. So I want to tell you one important thing here. Instead of writing a number, I want to input the number. Enter a 5-digit number. So what happens by this is, if you notice, I'm trying to show you a few things. See, instead of putting the static number here at x equal to something, I'm giving some dynamic number when I run the code. So it will ask enter a 5-digit number. I should have given a colon here. Okay, let's give a colon here and then run it again. Enter a 5-digit number. Let's say that I'm running 1 2 3 4 5, and then I got a square of that. Okay, right? So you have to use this. Instead of using a static number, use this dynamic way by using input. Okay, and always remember, now one thing which you have to remember, if I write this, what will I get? For example, enter a 5-digit number. This is 10,000. So what we will get? Let's see what we will get. 20,000. Okay, so you can try this few things. Okay, but my main intention to work on this is you have to use this syntax from now on. Okay, whenever you are doing simple coding, and then you have to use for loop and if loop here, and then check whether this number is palindrome or not. And you, like, I don't know how you will do it, but I think if I'm not wrong, you have to check the remainder and then divisor, remainder, divisor, so on, and then you have to understand whether this number is palindrome or not, right? So you can do that, guys, and then if you're not able to get the answer, please let me know in next session so that we can do it in a class. But I think you would be able to get it. Python is very simple. Okay, so from now on, please use this input function. One more thing which I want to just tell you is, if instead of entering a 5-digit number, let's say if I enter A, B, C, D, E, what will I get in this X asterisk? Instead of writing a number 1 2 3 4 5, I'm just writing A, B, C, D, E. You would notice that name ABCD is not defined. Okay, great, no problem. You can think why is it happening on this, and then you can try. You should play around with this few things. Okay, whenever you have any doubt, please write this and then you can check. So for example, instead of this, when it will concatenate or when will it multiply, if you have any doubts, you should always check the type. What type is it? It's type int. That's the reason I'm not getting for A, B, C, D, E. Now if you see, if I'm writing A, B, C, D, E, it's not taking because it is giving int type. Okay, so does this input always give you by default int? If yes, how to convert that into string? Okay, if no, then why? Please tell me the answer in tomorrow's session. Does input always gives the by default type as int or string? Okay, so please tell me the answer in next session. What could be the answer for this? And yes, to convert any number into a string, you have to put str of that. Seems like you have done a lot of Python coding. But then the important thing which I'm trying to explain here is from now on, you should try writing some simple codes apart from writing machine learning codes also. Okay, because I've seen that people writing a lot of machine learning codes and then they forgot this few basic things, and then when it comes to written test they won't be able to qualify itself in the written test. So please start working on the simple course also, so that you should be able to qualify your written test. Okay, in some interviews you will have written test, in some interviews you don't. So when there is a written test, you should be very confident that you would be able to understand the code, and then you can tell what could be the output. Okay, so that's an important thing which I wanted to tell. And in the next session, should we practice simple Python and ML codes together? So please start practicing on simple codes also, because I've noticed that several people start working on machine learning, then they forget the simple basics. And then they will know everything about machine learning, but they forget this basics, and then they won't be able to clear the written test. So please start doing this, guys, everyone. And if you're not able to understand any simple codes, then you can ask me in the next session. I will be there to help you guys. So please work on this coding challenge to identify whether whenever I give a new input, whenever I enter a number, 5-digit number, then your code should tell us whether this number is a palindrome or not. Okay. So to conclude today's session, I would say that we have learned sufficient amount of supervised learning algorithms and couple of unsupervised learning algorithms, and most of the job opportunities will be based on supervised learning. So please start practicing. In the next week or in the next session, we will look into some more algorithms. But if you are good with all these algorithms which I've taught till now, I would say that would be sufficient for you to fetch a job if you are practicing in Python daily, and if you are working on your challenges, and if you're doing your homework properly. Okay, so you should be able to fetch a good job, as a fresher, of course, as a fresher, because by this you would be having a basic and intermediate knowledge of machine learning. So you can fetch a job of fresher or 1 year or 2 years of experience in machine learning. But then we can discuss that later in our final week. But I just wanted to make sure that now you are very good. You should be able to just start practicing, complete your challenges, and then I don't see any reason that anyone stopping you from fetching a job in data science field. Okay, and one last thing, when you are trying to look for a simple data sets and you are implement the same thing on the same data set, try to implement hierarchical clustering also. Okay, always try to experiment. Okay, because there is no harm in doing experimenting. Just try to implement hierarchical clustering with different linkages, try to analyze the solutions, just check which is more accurate, whether it is k-means or hierarchical. If it is hierarchical, then which linkage it is better. We have completed 10 sessions in 5 weeks. Okay, please start looking at the videos. Everyone who are not there on the online sessions, please start looking all the videos. If you have any questions, please get back to me or Skill-Lync. We are here to help you guys. Okay, thank you everyone. Bye bye. Welcome back on the introduction to ML and AI using Python for mechanical aspirants. So to continue with the session, as I told, we had this final project, predict the output by using all supervised learning machine learning algorithm and identify the differences in the results obtained using this algorithm. So what you have to do, as I already told, you can use a user-defined function and you can predict using all the different supervised machine learning algorithms for the classification. Once you get the data, you will come to know. And then over there, you have to implement all this machine learning algorithms. Okay. And then you have to see which algorithm is performing better. And that would be great if you can identify the reason behind that. Okay. And then second would be quite complicated, as I told. It's performing the clustering for the same data and then use predictive algorithms and identify the differences obtained in the results in performing prediction with and without clustering. So what I meant is, in this case, so you would be having the data x1, x2, x3 and so on. I'm not sure how many x, and then y. Okay, so first you have to consider that there is no y in this case. Okay, and then implement your clustering. After clustering, you will come to know, based on this y, you would be knowing that how many outputs should be there. For example, if this y has 3 outputs, then try to divide this into 3 clustering techniques. Okay, try to divide this using any clustering techniques into 3 clusters, and then what y you will be getting, make that as a new column as a cluster one, that this record goes under which cluster, this record goes under this cluster, and based on this cluster try to predict. Now you can consider this as your y output, you can consider this as your y output and then do predictive modeling. That's a one way. And then the other way is use this as your y output, like in a second method, and then implement predictive modeling or like classifiers. Whether it's a, I think it would be a classifier model. So implement classifier on that. Okay, so now you got my point, right? You have to perform the same thing 2 times. One, by considering this given output in the data set. Second, do not consider this as an output and just do a clustering technique. And you should take the value, the number of clusters should be same as the number of outputs given in the actual data. And you should notice that ideally both should be having the same output, because clustering also tells us works in a similar direction, right? Because when we are classifying something, the classification would have done or in the original data based on some similarity between the records, right? So something like that, that is what we are doing on clustering analysis. So for example, if you see some of the features for x1, x2 and x3, and you have some torque value, speed value, number of like the design of the brake, something so on, and then based on that in the original output you might be having that as a BMW, then and the other record might be having Porsche, and the other record might be having say Alto. Now when you do the clustering analysis, it's quite logical that all the records with BMW should have some similarity, all the records with Porsche should have some similarity, all the records with Alto should have some similarity, and then you will come up with different clusters. Once you get different clusters, this you have to check whether, of course, the original output would be better in comparison to a clustering. But then when you do predictive analytics, like once you have this data, complete data set now, just do the predictive analytics or the classifier algorithm, implement the classifier algorithm, assuming this is as your original y in the first case, and in the second case, use this as your original output and then perform the classifier algorithm for any one test record, and then identify this predictive modeling is working, this classifier algorithm is working good on actual output or on clustered output, what we are getting. So this would be the final project, and this would take a lot of efforts from you guys. It's not very straightforward. So as in the first method, this would be considered as your y output as a target variable, and then you will do the predictive analytics. You will do complete training and test analysis, what we do, split the data and do all the analysis, and then try to predict for any one test record what would be the y output from the test data set, and just try to identify, try to compare this y predicted output value with y actual output in your given data set. Now in the second method, remove this feature from your analysis. Consider this as your new actual outputs, the cluster numbers. Okay, by now when you do clustering analysis, you would know that we have taken only 3 clusters, and then you would easily be able to identify one signifies what, whether it is BMW or Porsche or Alto. 2 signifies what, So when you do analysis, you will come to know what data set does 1 have, what data set 2 has, and what kind of data set does 3 have, right? And then you have to read that data and you have to analyze. It's quite logical when you have very high price that belongs to Porsche, and then quite high mileage might go with Alto, something like that. And then you have to neglect this, as I told, and then consider this as your actual outputs, and then do the same predictive analytics. And now compare your predicted output with this Y clustered output. And notice this predicted output or the classified output matches well with whether the actual output which was there in the original data set, or whether it matches quite well with the clustered output. Okay, cool. So that was the thing which I had, and start with a new topic, which is principal component analysis. And this is very interesting. Try to understand this. It will be useful, and a lot of people will ask you this question in your interview also. So what is this principal component analysis in first place? We have to understand that this is not a classifier algorithm. This is neither classifier nor predictive algorithm, or like this is neither classifier nor regression algorithm. So what it does is, suppose you have in real life, you can have n number of input features, right? For example, say you have 500 input features. Then how would you tackle with this 500 input features? And how would you say that these 5 input features are really significant in terms of determining your output? Are they really influencing your output in predicting your output? No, maybe yes, maybe no. And if it is no, then we have to make sure that we have to reduce the number of features, because if we have 500 features, then what we are doing is we are making our computational quite slow. And as we all are mechanical engineers, we know what does computation means. Computation in the sense, when you run any simulation in your mechanical projects, you must have noticed that if you have the mesh quite high, if you have a large number of meshes, or if you have number of cells quite high, then the simulation time would be quite high. Or if the physics is quite complicated, then the computational time would be quite high. Simple. Similarly, in maths or in machine learning, if you have high number of features, then the computational time would be quite high. It's quite natural, right? Just imagine that you have a matrix of say 3 by 3 and you have a matrix of 10 by 10, and say you want to multiply this 3 by 3 matrix with 3 by 3, let's say, and then 10 by 10 matrix with 10 by 10. Straightforward, that 10 by 10 matrix would take a lot of time, right? Similarly, when we have high number of features, it will take a lot of time. And of course, if you have the good amount of domain knowledge, then you would be able to find out what features are significant in terms of determining your output and what features are insignificant. Or you can do some lot of exploratory data analysis and try to find out if there is any multicollinearity problem. Then you can try reducing that also. Sometimes it would be really difficult when you have very high number of features and then you try to understand each feature and then identifying, then implementing the prediction model. It would be really difficult. So there is something called as principal component analysis. Okay, as the name suggests, it is an analysis which is done on the components. Okay, so what this technique does is it brings out the variation and the patterns in a data set. That means it tries to convert your original features into new features such that, so first of all, principal component analysis will not reduce your input features. That is your analysis by which you have to reduce your input features. But what principal component analysis does for you is it converts your input features into some other features. Okay. And now how does that do? That we learn in an advanced course. But here, what we need to understand is it converts all, say if you have 10 input features, it will come up with new 10 input features. Simple. That is how it works. But when it converts 10 input features into 10 new features, it makes sure that that lot of information should be carried by only 2 or 3 input features, or maybe 4 or 5 input features. So by that, what you're trying to do, for example, if you have 10 input features which have 100% of information of the data, and now once we implement principal component analysis, what it does, it will come with new 10 input features such that 3 features would have 95% of the information, and then remaining 7 converted features would have only 5% of the information about the data set. That means what you are doing here is you are trying to assume, or you're trying to do some approximation, but then you're trying to reduce your number of features for your analysis so that you can reduce the computational time. Just imagine something similar to mechanical analysis. Okay, what we do in mechanical, when we have a lot of physics and we are working with, say, conjugate heat transfer, where we have to work on both solids and fluids at the same time. As we know, if you want to solve any equations in the fluid, we have to use Navier-Stokes equation. And then if you are working on transient analysis, you have to perform Navier-Stokes equation every time on the fluids, right? So there is something called as co-simulation. If you try to explore this, because I know that most of you are mechanical engineer, that's the reason I'm giving you an analogy with respect to mechanical engineer. So now if you go with respect to mechanical engineer example, which is, say, co-simulation. In co-simulation, you segregate solids into one simulation file, fluids into one simulation file. Okay. And then you are trying to approximate. So what you will do now here is you will make solids as transient and fluids as steady. So by this, you don't have to run your Navier-Stokes equation for every iteration. Okay. So what I'm trying to do here is I'm doing some approximation, assuming that my fluid would be steady and my solids would be transient, because in solid we have to just solve for energy equation. But in fluids, if you notice, we have to solve for continuity equation, and then we have to solve for all the 3 momentum equation, x, y, z, and then we have to solve for energy equation also. So it takes a lot of time if I try to solve these equations for every iteration. So now I'm segregating that. So by this, yes, I'm doing some approximation. I have to compromise with the accuracy, but then we will reduce the computational time. Okay. And also there are a few other things. If you try to understand, if you try to explore, there are some more advantages of co-simulation that you can look at that you can already explore it. Okay. I don't have to explain that in this course. Anyways, for example, just say that you are working on component analysis. And for that component, you have to use complete vehicle for doing the analysis, which takes a lot of computational time, because you have to solve the simulation for all the XYZ direction. Now just assume that if you're considering the body as bulk in the sense that the parameters such as temperature and the heat transfer coefficient or some other parameters, say example, but mainly which is temperature, right? Because we always try to evaluate temperatures in our thermal simulations. So if the temperatures are not changing in XYZ direction, it's changing only with time, then we can always go with 0D analysis. And what is that? Lump capacitance method, which I've already explained in one of the previous sessions. So something like that. We have to compromise with the accuracy, but then with how much we need to compromise, that it depends on the problem definition. And then with this accuracy compromising what we are doing, how much time we are saving, that we have to check for. Okay, so it's just not that we are compromising with accuracy. We have to make sure if we are compromising with something, there has to be some advantage, right? So we have to check for the computational time, and that's the main advantage of PC. Okay, so how does it work? That's important now. Now if you see, we have an original data set here, say x and y, and let's say that rather than taking x and y, let's take this as x1 and x2. Okay, then please remember that this y is not your output feature. Okay, this is one random features which we are talking about here.
to explain it to you on a graphical representation, because we always consider this as horizontal axis as x and vertical axis as y from our school days. That's the reason that representation has been taken. But please remember that this x and y here are some input features. Say 2 input features we are working on. Now, see, this is how your data points are represented. In this data point, if you notice, each input feature is contributing something to your this data point, right? Now, just imagine if I convert my new xy axis, instead of like this, if I convert it like this using some transformations. I'm just telling you to assume it, okay? Real mathematics will come in the advanced course. How do we do that? So if you notice now, it's quite straight here that the value for this new axis, all these data points value for this coordinate, the new coordinate would be 0. And for this new coordinate, it would be some positive values and some negative values, right? So that is how, by using some analysis of mathematical representation, using linear algebra, what we are doing, we are making sure that the variance or the variation of these data points are with only this coordinate system, but not with this coordinate system. Okay. Now, to represent that again, let's take this example and convert this into 1D diagram of x and y. Say this is x. This is, say, somewhere near 2 and 4 on this number line. This point is also somewhere near 2 and 4. This point is located between 4 and 6. This point is located between 4 and 6. This point is located at 8, near to 8. Now, take the same thing for y. Do these projections on x. Do the projections of data points on y. And you would notice that this y here, between 2 and 4, there are 2 points again. Between 4 and 6, there are 2 points again. And near to 6 and 8, near to 7, there is one more point, right? Now, PCA, it does internal calculation of linear algebra, and then what it does, it comes up with the new input features. It converts x and y into PC1 and PC2, okay? And then what it does, it will take this axis, which is quite simple to imagine, right? Because that's quite simple to understand here. But when it goes in multi-dimension, it will be very difficult to analyze, okay, and to visualize. But here it's okay. That's the reason I've taken an example of 2 input features. So here, if you notice, now we have taken this transformation or linear algebra analysis. We have done some linear algebra, and then we have come up with PC1 and PC2. And here, the same points are represented here, okay? Now, if you notice, if you project these points on PC1, the points are represented on this number line for PC1. And if you project these points on PC2, that will be projected at 0. Now, it's quite simple to understand that the variation of these data points across PC2 is almost 0. Let's say 1 or 2%. But the variation is more on PC1. So what we are trying to tell here is, rather than using this data point for our analysis, whether we are doing supervised or unsupervised, that's a different thing. Whether doing clustering or predictive modeling, that's a different story. But let's say that instead of doing your predictive model on 2 features, now we have converted this into new 2 features, and then by looking at these 2 input features, PC1 and PC2, it's quite straightforward that the variations in PC2 is negligible. That means the information carried by PC2 is almost negligible. But the variation in PC1 is more, so the information carried by PC1 is quite more. That means, in this case, I can say that because the data was so organized with single coordinate, I was able to get all the variations. That means might be 99% of the information is carried by PC1 and 1% of information is carried by PC2 with this new PC1 and PC2 features. But if you see this original input features, you already know that both of them are actually carrying in equal amount of information, right? But by converting that into new features, PC1 and PC2, it's quite straightforward that PC2 is carrying very less amount of information. Now there could be a case, so this is important. Say this point might be lying somewhere here. Say this point might be lying somewhere here. Okay, this point is slightly above now. Let's assume this point is slightly below. Now, when you do PCA with this coordinate, now you would notice that this point will be slightly above, this point would be slightly below. Okay, and then when you project these points in X and Y, the X might be looking at here only, might be here only, but Y values will be, might go somewhere around here. This one point might go somewhere here, and one point might go somewhere here. Making sense? So with this, what we are trying to tell here is, again, the information carried by PC2 might be there. It might be quite significant. Maybe instead of now, with this example, which I have taken, the new example which I have taken, it had quite a variation, but still this variation is very less in comparison to PC1. Say the variation previously, like for previous PC1 and PC2, it was 99% and 1% with this exact example, what is showing on the slide. With the new example which I have told just now, say the variation with PC1 is 95% and PC2 is 5%. So then again, it's up to us whether we have to choose PC2 or not, okay, for our analysis. If we want to come up with a model with 5% of error, then we can neglect PC2 in this second example. But if we want to be very accurate and then the error percentage would be, say, with 1%, then we have to account PC2 also in our analysis. But when we are accounting PC2 in our analysis, then the whole essence of PC1 and the PC2 is gone, because originally we have two inputs. Now again, I'm converting that into PC1 and PC2, and then I'm using PC1 and PC2. So there is no advantage, right? It's like I'm doing some extra work here. So this principal component analysis can only be used when you have very large number of features. So this is just an example which I'm trying to show you in two-dimensional. Okay. Of course, it will have some approximations, because now also if you see, these values are like very near to 0, but there are some values which are at 0.1, 0.2, right? So maybe 0.2 or 0.5% of variation of the information is being carried by PC2. Okay, so you are compromising with the accuracy, but then you are reducing the computational time. Okay, now let's take this three-dimensional example. Okay, let's say that when you projected these points here, these points in XYZ direction, let's say that this were the data points somewhere here, and for Y somewhere here, and for Z somewhere here. And when you convert this, again I'm telling you, if you have originally 3 input features, principal component will come with 3 features only. It will not reduce the features. It is your analysis based on which you have to decide whether I have to reduce the features or not. So it will convert this into 3 new input features, PC1, PC2 and PC3. Now it's quite straightforward that most of the information is being carried by PC1. Yes, PC2 also have some amount of information, and PC3 is also having some amount of information. Now it depends on you. Let's say that PC1 carries 90% of information, PC2 carries 5% based on this deviation and the variance what I'm seeing here, and say PC3 has again 5% of information. Okay, so for example, if you can live with 10% of accuracy or approximation, then you can only use PC1 for your analysis, and then you can predict whatever you want to predict the output based on. But if you want to predict, say 91% with you cannot adjust with 10% of approximation. You have to, you want like, I can only live with 5% of approximation. So this approximation, what I'm telling, is actually in mathematical language called as confidence. So this you will notice in again in other course, in the second course you will notice, because that's a mathematical part again, which will be taken care in the next course. So this confidence what I'm talking, it's very simple to your English language also. How confident are you that your results are correct? So if you take only PC1 and you got some prediction, then you would tell, before performing the analysis and all, you can tell that with 90% of confidence, I can only go with PC1 and then do the analysis. But if you want to be more confident, then it's important that, and what is that confidence value? For example, say you want to be 95% confident. You have to take both PC1 and PC2 or both PC1 and PC3. It's up to you whether you take PC2 or PC3, because now I've taken an equal example for PC2 and PC3, right? Say PC2 has 6% of variation and PC3 has 4% of information, and PC1 has 90% again. Now if I want to be 95% confident for my results, then shall I select PC1 and PC2 or PC1 and PC3? It should be 1 and 2, because there is no harm in having more information, but you cannot take PC1 and PC3, because if your client is telling that he wants to be 95% confident, then you cannot be 94% confident and do the analysis. Okay, I will just try to give some basic knowledge about the confidence. But if in multiple features are there, so we will do PCA of each feature with every other feature. No, so you don't have to do PCA of each feature with every other feature. What we have to do is the PCA itself does analysis internally, and it will convert all the, say, 10 input features into new 10 input features. In this 10 input features, there will be one feature which will be having largest information. Then there will be, say, example, 70% information will be carried by, say, first new input feature PC1. 20% of the information will be carried by second feature, say PC2. And the remaining 10% of the information will be carried by 8 features, PC3, PC4, and so on up to PC10. But if you want to be 90% confident for your analysis, then you don't have to select all the remaining 8 features for your analysis, for your prediction. You can only live with PC1 and PC2. Say, for example, when I explain this confidence, you will come to know what I'm trying to tell. Okay, let me take that. Say you are a weather reporter, and say that by looking at the historical temperatures for, like, you might have seen the temperatures for all the historical day, right? The weather reports. Say you have predicted that the average temperature for tomorrow is 30 degrees centigrade. But have you ever noticed that weather reports this value, or they report min, comma, max? What do they report? Have you ever seen that news reporter or weather reporter, it's only displaying one value? No, right? They always report min and max. So this is called as confidence interval. And now how is it decided? It's decided based on the confidence value. Now, for example, say I am a weather reporter and today I am 90%, say I am predicting for tomorrow's temperature. Say with 90% confidence, 95% confidence, 99% confidence, and say 100% confidence. Okay. Now try to understand this. When you look at the historical data, you cannot look at the population data, right? Population in the sense you should have all the historical data, right? For complete population or for all the cities and for all the different areas, or like for a particular area, if you want to predict the temperature, then you should have all the historical data, right? But we never do that. What we do, we always try to take a sample and then we try to do the analysis. So based on that sample analysis, we will come with min and max. So now if I am 90% confident, say I got an average temperature for tomorrow, say 31 degrees centigrade. So just assume this, that for tomorrow I'm getting a prediction of 31 degrees centigrade, the predicted value. Okay, this is a single value. But then if you tell this single value to your audience, there are very high chances that you would go wrong. That's the reason we come up with interval values. With 90% confidence, you are telling that, say my temperature is, min is 30 and maximum is 32 degrees centigrade. Now just assume that if you want to tell the same thing with quite high confident level, okay, it's quite simple. When a student writes an exam, and if his parents ask what could be the range of your marks in your final exam, he would tell that my range could be like I might get 70 to 80 marks, 70 to 80 between. But if your parents ask Are you sure? Then he would be like, oh, he will get conscious, and then he would tell, no, I might get between 65 to 85. So that the words which he is telling, he should be able to live with those words, right? Something similar, but the mathematics will look into next course. Don't worry about that. So if I'm 95% confident now, then what could be the range? Whether it will be greater than the range of this or it will be lesser than range of this. The question is, for giving the range of the temperature for tomorrow with 90% confidence, say 30 and 32, because your average predicted value is 31 degrees centigrade, but you're giving the range as 30 to 32 degrees centigrade, 30 to English 2, 32 degrees centigrade. If you want to be 95% confidence, then what will you do? Will you increase the range or reduce the range and display the news? What will you do? You have to increase the range, right? Because see, it's very simple, guys. If you are telling I am 95% confident, that means the probability that you would go wrong is quite less. And if you want to make sure that the probability that you're going wrong would be quite less, you would become more conscious, and then you would tell the range would be now 28 to 34 or 35, so that you would not go wrong. So you're trying to be on the safer side. Now, if you will be 99% confidence, then the range will be even bigger, say 25 degrees to 38 degrees centigrade. Now, is it really possible to come up with 100% confidence results? You can do that in next course, but you can always imagine when you don't have the data for population, how would you be 100% confident? If you want to make sure that you are 100% confident, then the range should be very big for that, so that you don't go wrong. Because if you're 100% confident, that means the probability that you're going wrong is 0%, right? So on the same lines, it's up to us how much confident we want to be while predicting the results. So it's our client who will tell us how confident you have to be while predicting the results. If he tells that he wants to be 100% confident, then it's quite straightforward that you don't have to implement PCA. You cannot implement PCA then. You have to take all the features, and then you have to do feature analysis or feature selection, or with domain knowledge, you have to remove some of the features. It might take a lot of time, but you have to do that. Because if you do PCA, you have to compromise with some percent of confidence. Okay, you have to lose some amount of confidence. Otherwise, there is no use of PCA, right? It's a dimension reduction technique. So people will ask you in interview, do you know any dimensional reduction technique? You can say PCA. Okay. There are some more methods. You can always explore that by yourself. But if you know this, that would be highly sufficient to fetch a job. Okay. Great. And someone will also ask how to do feature selection and feature engineering maybe. Then you have to tell that feature selection can be done using domain knowledge, or I can reduce the dimension using PCA. So your question is, this confidence is similar to confidence level when we do regression in Excel data analysis. What do you mean by, have you ever done this? And it would be dependent on R2 value. See, the point is R2 value. Okay, now it's very important to differentiate these two things. I think you have performed this on Excel regression. Okay, but I'm not sure. By looking at your statement, I feel so that you have performed linear regression or some regression on Excel sheet. Okay, no problem. So there are two things here. Say you have X1, X2, X3, X4, and then Y. Say, let's say that you have converted into PCA. So now PC1, PC2, PC3, PC4. So the first thing is, when you do mathematical calculation for PCA, you would notice in the next course that PCA would try to convert these 4 features into new 4 features in such a way that one feature consists of high amount of information, and then it will gradually decrease across these new features, PC2, PC3, and PC4. So the one feature would be having very high value, and it will adjust this PC1, PC2, PC3, and PC4 in the decreasing order. The algorithm does that. Okay. So PC1 might say 80% of information is carried by, say, PC1. Say this carries 12% of information. Say this carries 5% of information. Then it has to carry 3% of the information of the original data set, x1, x2, x3, and x4. Right? If I'm not wrong, this will sum up to 100. Okay, now when you do your linear regression with this, and when you do with linear regression with this, now say you want to be 95% confident, then what you would do is you would take this 3, or you can take this 3 also, this, and this. But then it's up to you whether you choose this 3 or this 3. I would go with this 3 because anyways at the end we have to take 3 features. So it's better that we have more confidence in our results. So let's say that you are taking this 3. PC1, PC2 and PC3. After performing this principal component analysis, you got this data set. Now this is important here, okay? When you calculate R square value, this R square, first of all, did I talk about coefficient of determination and did I talk about other coefficient which is adjusted R square in my previous session? Yes, so you remember that, great. So now it's quite obvious that in R square, as I told, if you increase the number of features, if I put one more feature, my value might increase. So I would not check for R square. I will check for adjusted R square always. For multilinear regression, you should always look for adjusted R square. That's one thing. Now, this R square value would be dependent on these features, guys. Okay. And here you are not having any approximations in terms of reducing the features. But here, the adjusted R square, what you will get will be based out of these 3 input features and this output. Right? Here it will be on this 4 and this y. Here it will be on these 3 features and this y. So it would be really difficult to compare or tell which R square is better, because this is your post analysis which you are doing. Okay. But I'm not sure, I've never together, or you can also check that and you can let me know for any one data set. You can do this analysis and tell me know what is the adjusted R square for this and for this. I have never checked that, but anyways, with my mathematical knowledge, I can tell that ideally this R square value should be more than this R square value, adjusted R square value. But then it's always very difficult to compare, because this R square is an evaluation parameter of your predictive model. What we are talking about something which is pre-implementation of your machine learning, pre-implementation of your classifier or prediction model. So here we are trying to be how much percentage confident we are with our results. This is the evaluation parameter of the predicted model or the classifier model. So ideally we do not compare, but we can always check that. With respect to the mass, what I am thinking, this R square should be better than this. But then imagine, say you have this input features, say x1, x2, x3 and x4. And when you convert into PC1, PC2 and PC3 and PC4, say that you have PC3 with 8% of information and PC4 with 0%. Then if I am taking now this 3, let's assume that because there is a multilinearity problem with x4, say x4 is say x1 plus x2 plus x3. That means x4 is highly dependent on x1, x2 and x3, right? So it's quite obvious that there is no need of x4, right? So in this cases, there could be a chance that this R square might be equal to this R square value. Okay, if you forget to remove this feature while doing the analysis, while implementing the linear regression, as I told, we should always make sure that there is no multi-collinearity problem while doing regression. Then I'm not sure, maybe your values might be, you might have some surprises as well. So what you can do is you can perform such analysis in one of the data set and you can always come up with the solution. But ideally, mathematically, when you are performing this PCA analysis, you are just trying to be how much confident with the results. That's what we are trying to tell here. So with 95% confident, okay, or with 95% of the information, I'm getting this R square value. With 100% of the information, I'm getting this R square value. Okay, that's the whole story here. Okay, so now meanwhile, you guys please think for a new puzzle how to solve this again with respect to chessboard, because remember that I'm asking a lot of mathematical puzzles so that you start thinking on mathematical lines, and then it will be helpful in the next course. So in the chessboard, as you know, there will be the chessboards will be something like this, right? So there will be some vertices, the corner points. So let's consider this intersection points are some vertices. Okay, some corners or some intersection points are as some vertices. So these are some points. So you can always calculate how many points are there on a chessboard. Corner points and the intersection points. This point, this point, this point. So with this point, you have to tell me how many triangles can be formed. You know that, right? For triangle, how many points are required? 3 points. First, you have to calculate how many points are there on a chessboard, including all the points of the perimeter and the intersecting points. Count that. You know what is the logic for forming a triangle. For every triangle, you need 3 points. And then you can come up with the answer. Again, to repeat this, your R square value would be, adjusted R square value would be highly dependent on the features what you are taking. So if you are taking them redundant features, then as assumptions of linear regression says that if there is a multi-collinearity problem, then the results what you get would be not accurate. Okay, so it's very difficult to comment on the R square value with respect to your PCA. So it depends on the data, it depends on the confidence level, it depends also on the features which you are choosing. Great. Okay, so please think on the lines of puzzle, and we'll go with the Python coding. Before going into the Python coding, let's revise few points. When to use principal component analysis. Okay, it's important. Want to reduce your features in a data set, but you're not sure which features to be retained or which features to be removed. So as I told, you have 10 features and you don't have the domain knowledge. Say you're working as a mechanical engineer, you would be having enough amount of knowledge of mechanical projects. Say if you get some project on insurance, you don't know what features should be retained and what features should be removed. But you're pretty sure that if I retain all the features, my computational time would be quite high. In that cases, you can go with principal component analysis. So for example, it is important that PCA should not be used randomly for reducing the features. Okay, it should not be used randomly. And then focus should be more to feature engineering if we have sufficient amount of domain knowledge. So as I have been keep telling you, so for example, if you know the dimensions, say you have the feature say x, y, z, and you also have one dimension with volume, then do I need volume as a separate feature? No, because volume is already dependent on x, y, z. With feature engineering, I can always remove the value of volume from my data set. So that's a domain knowledge, right? So first preference should always be given to feature engineering. And then the third point is, if there is not enough domain knowledge, then it's better to understand the domain first and then try to do feature engineering using descriptive analytics. What is descriptive analytics? All the exploratory data analysis, try to understand if there is any multi-collinearity problem, if there are any features which are duplicates, try to understand that and remove those features. And at the end, you should use PCA if you're not able to do anything. Third point is, if you want to ensure that the variables are independent of one another. So for example, if you have 100 features and you don't know if there is any multi-collinearity problem exist. So first thing is you have to do descriptive analytics and try to find out. And if you're not able to do that, then the PCA only can decide. PCA will come up with a lot of many features, and based on the information values, you can understand that the high information variables are independent of each other. If you are comfortable making the independent variables less interpretable. Now this point I forgot to tell you. Let me tell what does this point tells. Let's say that you have original data set and then you have come up with an equation. Okay, let's say you're using linear regression. Okay, now let's say you have converted this into principal components, and then say this too has say 95% of information, and then you would get a linear regression equation something like this. Okay. Now, the most important thing which you need to understand here, in this case, you can always interpret your results. That means if x1 is increased by say 5 units, then you know that your value of y would be increased by beta 1, 5 beta 1. Yes or no? Very simple maths. Now, in this case, I cannot tell that if PC1 increases by 1 unit or 2 units or 3 units or 5 units, because this is not the original data. The original data is here, x1, x2 and x3. Now, if my x1 increases by 5 units, I'm not sure with how much amount my PC1 and PC2 will increase. So now in this case, interpretation would be quite difficult. Not difficult, it would be really difficult. Okay. So that's where the third point comes. If we are comfortable making our independent variables less interpretable. Okay. So by looking at this linear regression in these terms with PC terms, if your client asks whether I should increase x1 or decrease x1 for increasing my output, then it will be really difficult for you to interpret the results. Okay, because we don't know whether the original equation when we have x1, whether it will have plus value or minus value for beta 1. If we choose the original data set, for us it will be very easy to interpret based on the beta 1 positive sign or negative sign and with the magnitude. But here we don't know, we are clueless. If we are ready to compromise with interpretation as well, then we should use principal component analysis. Okay, so the maths involved behind PCA is linear algebra, and your next course consists of this linear algebra. Okay, now the principal component analysis are having two challenges. Perform machine learning algorithm, any machine learning algorithm on the data set which will be provided to you with and without PCA. Okay, something like this as we have discussed. And you guys please come up with the value of accuracy and tell me if accuracy has increased, why? If the accuracy is decreased using PCA, why? Or if it is equal, then it is y. Okay. And then list down the differences in the results obtained with PCA and without PCA. Okay. Without PCA, it's quite simple. Directly implement machine learning algorithm. Import the machine learning import data set. Use train test split function to split the data set into training data set and test data set. And perform machine learning algorithm. Identify the score in Python. With PCA, first you have to implement PCA that we will learn in today's session, and then you have to repeat the same step which you have done in without PCA, but with a new data frame which will have PCA as the input features. Okay. So you can read the dataset from URL also, but let me not go into that deeper mode. Let me import the same things what we generally do. Let me write the steps. And then last time, if I remember, we were doing some clustering analysis. So let's take the same data set. We are working on some data set, if I'm not wrong, on Iris data set, right? Yeah, it's here. So as I told, in Skill-Lync, there is one module by name datasets, and in datasets you will have a lot of datasets. Okay, and from those datasets, I'm just importing one of the datasets, which is load underscores iris, which is iris dataset. Okay. Now if I print iris, so you would notice that it's very difficult to understand because it has those sepal length, sepal width, and also on, right? So for that, what we have done last time while working on SVM, we have created a data frame out of this, because if you check the directory, you will notice that it's not a Panda data frame. You can also check that. But meanwhile, quickly, let me do this thing. Okay, so now instead of printing the iris dataset, because it's not a data frame now, you can check that. Let me keep it here. So I'll run this code. Now what you'll notice is I ran my PCA Python file here. It says that directory means it will tell what all different things it has in dataset of that iris dataset. It has some description, it has some data, it has feature names, it has file name, target, and target names. But for us, what is important? Data, target, and target names, right? You can also check what is the type of this iris, which is a kind of sklearn bunch. It's not a data frame. So now I'm converting that into data frame. Okay. How I am doing it? Using pandas. Panda.dataframe. I am taking this iris. From iris, I am taking this data. I'm taking this data, and then I'm converting that data into some columns with iris.feature names. So there is one feature names separate tab in your directory iris. So based on that feature names, now this data will have this kind of feature names, which are sepal length, sepal width, petal length, and petal width. So these are the column names which are extracted from feature underscores names, which is already there in iris dataset. And these are the data points which we are extracting from the iris dataset and putting it into the data frame. Now, if I print data frame, we will get nicely something like this. See, if I don't do this, no, you will notice that you will not have this proper feature names here as column names. Okay, then will be very difficult to understand which is sepal length, which is sepal width, which is petal length, and which is petal width. And then I am concatenating new column by name target, which is equal to iris.target. Okay, and then that is our output, right? Which is 0, 1, or 2, or 3, I believe, based on number of outputs which we have. Yeah, 0, 1, 2, because we have 3 outputs, target names, right? Which we have already seen in while doing SVM analysis. Setosa, versicolor, and virginica. Right? So these are the target names which we are seeing, and the targets are based on 0 as Setosa, 1 as versicolor, and 2 as virginica. Okay. And then I'm using this describe syntax so that I can do this some basic exploratory data analysis to count number of records, to check the mean, identify Q1, Q2, Q3, Q4, Q0. Okay, so these are very basic analysis which I'm doing. Now once I have the data frame, now what I will do here, rather than taking it from the URL, I'm just taking directly from the scikit-learn. Now what I will do, See, there are two ways to standardize this data set. If you remember, if you want to bring the range from 0 to 1, you have to use x minus x mean divided by x max minus x mean, or by using z scores, x minus mu by sigma, right? So I think we have already used that once, x minus x mean divided by x max minus x mean in our one of the sessions. Let's use x minus mu by sigma. So you can calculate mu and sigma for all the features, and then you can do it manually. But there is an inbuilt function in Python which I'll be using now. Okay, so I will be using then inbuilt standard scalar which will use z scores. Okay, and now what I am doing is, here I'm separating x and y, but you don't have to do it, but it's up to you. So separating x and y by using new variable which has all these columns, okay, and then separating it y also. If you don't want to do that, it's up to you. You can do it in a different way. It's up to you. Okay, so before concatenating here targets, you could have done it here itself. For example, df. So on df, here df has only input features, but that this df would have output feature also. So you can convert this as some new data frame also, df1, and then you can have df1 here, and then it's up to you whether how do you want to play with the data set. Okay, so let's run this till here and see if it is working. I'm not sure if it works or not. Let's not print everything because it's waste of time now, because we have already checked it is printing the right values. So we are getting some error. So let's do one thing. So let's call this as df underscores x, and this is your final data frame which has targets also. So now let's have it only y in this. Say this has iris dot, or let's say new data frame with target. So there is some mismatch with the names. I believe that's the reason I'm doing it with the same names. So let's make sure that all of them are working fine in first place. So let's run this. Let's see if you're getting some error. So df is not defined. Okay, so let's this be df. This is a data frame. We are concatenated. Now let's say df underscores y has only target, and df underscores has df of all this, right? Why is it not giving me a drop down? Let's run this first. Okay, this makes sense. Now my data frame y has only target names. Let's print that. Yes, it makes sense. It has only target names. So what we have done, we have got a final data frame with all the inputs and the output. I'm just trying to segregate that into df underscores y, which has output, and df underscores x, which has only inputs. So rather than taking all those columns, let's drop target from original data frame. Okay, and let's drop this. Say target. Now let me use the axis equal to 1. Now let's print this df underscores x. See if we are in the right direction. Let's see that. Okay. Yeah, so it makes sense. So now we have got df underscores y, which has only targets, and df underscores x, which has all the input features, right? Now, can you tell me why I've written, while dropping this target feature, why I've written axis equal to 1? So axis equal to 1 because we are trying to drop a column, right? So when we're trying to drop the column, the axis should be equal to 1, okay? But when we are trying to drop the record, any row, the axis value, try to find what would be the axis value when we are trying to drop the record. But here we are trying to drop one of the columns from the original data frame df. That's the reason I'm using axis equal to 1. So axis equal to 1 means 1 indicates column. Okay. So now I got this df underscores and df underscores y. Let's import standard scalar because we want to standardize the features, right? So now, as you can notice, our input features are changed from these values to our new values using standard scalar, right? Now, if you notice, there are some values which are going from negative, the sign also it is going more than 1 also, because now we are not constraining the values from 0 to 1 using that x minus x mean by x max minus x mean. What we are using here is z scores, x minus mu by sigma. So it can have negative values also. Okay, making sense, right? So we have converted our input features into standardized values. Now let's go to PCA. You could have implemented PCA on the original data set also, because all the units and the scales, if you notice, for all the input features are same, but it's just that I wanted to display this standard scalar as a new function so that you don't have to implement x minus mu by sigma every time in Python. That will be directly done by this function standard scalar, and then transform your input features, and then the values which you will be getting will be based on x minus mu by sigma. Or if you want to create your user defined function by your own, that's also fine. Okay. Now from sklearn, I'm importing PCA, and then what I'm doing is I'm trying to come up with a PCA new variable and implementing this PCA function on getting only 2 components. I'm just making sure that I get only 2 components this time. Okay. So this is the way of working in Python. There is another way by which you can work, but this time what I'm doing, I'm compiling the code to come up with only 2 components. Okay. By using this syntax. Now principal components is equal to PC underscore transform. So what I'm trying to do here is I'm trying to come up with I'm just having 2 components in the principal components, and those principal components are going with transform on input features only. So input feature should be this time the standardized input features, right? Okay. I'm creating a new data frame out of this principal components. Okay. Now this principal components will have only two components because I'm using two here. So I'm creating a new data frame with this principal components variable which has columns principal component 1 and principal component 2. Okay. So that's how the function has been defined for this PCA. Okay. So that's a reason these are the names. Okay. And you can change the names also, but it will have two columns. Okay. I think you can also change the column names. Let's try that. So now let me run this. So till now what we have done, we have come up with the principal components in the code. Now let me run that. I haven't printed that. Let me print this. So it's necessary that we have to make this data frames into pandas data frames so that we can have consistency. That's the reason I'm making a pandas data frame. And then the column names are principal component 1 and principal component 2. If you want, you can also convert that into, I think, PC1 and PC2. See, PC1 and PC2. Okay. Now the final data frame would consist of this PC1 and PC2 and the targets from the original data set, right? Okay, so let's add that targets here in our final data frame, which is this, and let's print that also. So now the data frame what we have is not with the original inputs, it has principal components and output. Okay, so these are the ways how we can plot this principal components. Okay, so if you want you can check this, but that's not in the interest of this, but we'll do that later. But for time being, I want you to show something very important. I want to run this now. So this PCA variable which we have used, remember, this PCA has this parameter, and just check that what does it comes out, what will be the output of this. What is this explain variance ratio? What is this denoting these two values? Amount of information. So PC1 has around 72.96% of the data information and 22.8 data information is carried by PC2. So now you must be thinking, where are the remaining information? If you add these two, that would be around 95% of the variation of the data, right? Where is the remaining 5% of the data? You know the answer, which is PC3 and PC4. Okay, let's do this. If you want to visualize, let's visualize the principal components also. So I'm just plotting a figure, empty figure with this size. I'm setting up the labels. This should be PC1, right? Because we have already changed that. PC1, PC2. The graph title should be 2 component PCA. Okay, font size. Okay. Targets, we know these are the targets. And the colors would be, Setosa would be in R color, red color, Versi color would be in green color, Virginica will be in blue color. Okay. And then I'm plotting a scatter plot. So it would be very difficult to explain you the each syntax here, but let's plot this and then you will get an idea what I'm trying to do here. Principal component 1. Okay, I have to change this also. Okay. Future warning. No problem. It is not showing the points. Okay, let me see what's wrong in this. So now, doing the same thing in a new different data, the reason why I'm doing it to a different data so that you come to know the various ways of solving or doing PCA. So if you remember, here we have done PCA by using number of components, right? But the other way of doing is from a Skill-Lync dataset, I'm just fetching another data which is fetch underscores ML data. Okay, because if you notice, the previous dataset had only 4 features, right? So you will not come to know its importance. If you notice this dataset now, it will have lot many features. Let's do that. I think it is still reading. Okay, never mind. So what I'm trying to tell is, let it read this because it has a huge data and then it has around 700 features. So what I'm trying to do here is, now here it makes sense if you use principal component analysis because it has less amount of RAM, so it takes a lot of time. Anyways, so I'm just reading the data, I'm printing it. I should have not printed it. Okay, it's a huge data set. So from Skill-Lync, you all know this from model selection, train, test, split, and splitting the data. And then I'm giving some 4 variables: training, images, test images. It has images actually, yeah. And then train labels and test label. So this data would look like something. You will have the images in the input features, 8, 1, 2, something like that. And then the corresponding label will be there. 0, 1, 2 or something. Okay, so there will be images and the output feature will be telling its label whether it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now in your output features you have 10 classes. Okay, the server has closed the connection. Never mind, I think it's taking a lot of time, so you can try it in your laptop. So I'm just splitting the data set: X, train X, test X, train Y, test Y. Okay, so in the data we have, if you want to notice, let me try once again. So in the data you have images and in the target you have labels. Okay, so let me try that one more time. It's a huge data set. That could be the reason that. Meanwhile it runs again. Let me explain this. So we got train X, train Y, and test Y. And then again I'm from Skill-Lync pre-processing, I'm importing standard Scala for converting my data points into z-scores, right? So if it prints, then only it will be easy to understand. Let's wait for a couple of minutes. Okay. So these are just warnings, so we don't have to worry. I'm just trying to identify what's wrong with this. Okay, there is some issue with this, so don't worry with this. Okay, let's remove this. But let me complete what I wanted to show. in the same data set itself. So if you remember, in this data set, what we have done, we have taken n underscore component equal to 2. By this, we have told that we need only 2 components. The other way of doing it is just write the value, the confident value which you want. Okay, and let's run this again. So now you would notice you would get the same answer. Okay. Now if you try to come up with here, say PC3, let's say that you're coming up with PC3 also. Okay. You are getting value error. Shape of the past value is 150,2, indices imply 150,3. But it's quite simple that we understood that from the previous solution that the already 95% of the information was carried by only 2 components, right? So if you want 3 components, maybe we have to increase the value of this. Say, let's say 0.97. Now it makes sense, right? So if you notice, PC1 has 72.9% amount of information of the or the variation of the data. It has 22.8% of the data information. It has 3%. So now 73 plus 22, 95 plus 3, 98, and this summation 99.4. So you have around 99.4 amount of information, variation information of the data in these 3 components. Okay, so that is what I wanted to explain here. So but it would be confusing if we write here value and then we don't know how many principal component carries this amount of information value. So generally you can write n underscores component whether equal to 2 or 3. You can start with 2 and then check how much amount of information was it carrying with respect to this function, explain variance ratio. And then you can increase the number of components 2, 3, 4 and then check how much amount of information are coming up. Okay. Now for example, here I have written say 0.95. If I write PC3, then it was giving error because we know that 95% of information was carried by PC1 and PC2 only. But I am also looking for PC3. But when I do this PC analysis, it will come up with only 2 principal components based on this 95% confidence, right? So that was the reason it was throwing error when I write PC3 here. So that's the reason I have changed this value to 0.97. Now let's see that if you want all complete information, you would notice that PC4 will have very less amount of information. Let me try, it's not taking. See, PC4 has very less 0.5 amount of information carried by PC4. So that's the reason in general we do not use PC4. If we have 4 features, there is no use of converting it into PC1, PC2, PC3, PC4, right? So that's the reason I always tell use the other option, n underscores component, and based on the components 2, 3. If it is 2, then just write 2 PC1, PC2, and then check the variance ratio. That would give you the solution. Okay. So there are 2 ways by which you can solve this problem. If you are writing 2, then remove this and then run it. Okay. So there are 2 ways of running PCA. Either you can write n underscores component or you can write the amount of information, the amount of variation which you need. But then if you write the amount of information which you need, you have to make sure that you are writing right number of principal components. That would be really difficult to determine without doing trial and error. So that's the reason I always use n underscore component. Okay. So tomorrow we'll see why this plot was not working. And then I'll try to reduce the data set here and then see if I can use this data set again to showcase some, to demonstrate it. Okay. But meanwhile, the objective is clear. This is what I wanted to explain, that there are two ways of incorporating principal component analysis in Python. Welcome back on the introduction to ML and AI using Python for mechanical aspirants. And this would be some part of the continuation of week 11. Okay. So as we have discussed yesterday that our plot was not working, if I'm not wrong. So I have figured out after the class why it was not working. So there were some errors. There are a few syntaxes, a few lines which actually works in Jupyter, but do not work in a similar way when you do it on Visual Studio Code. So if you remember, we had an iris data set, and then we have used PCA on that, and then we had used two components, principal components, and then we ran this command by which we came to know that this two component had the information variation of the data set of with more than 95%. And then this was the syntax which was not running, so I have rectified it. So let's see what happens now after running this. I wanted to show you this. What I have done, in fact, was yesterday here there was some syntax problem, and I had done a small mistake yesterday. I have written the flower names here, Setosa, Virginica, and the third one, I'm not sure. So I've written those names, that was the reason. But if I see here, the target names what we have are 0, 1, 2. So that's the reason I've converted this target's name as 0, 1, 2. And then I'm running it again. So what you would notice is this plot, and this is what I wanted to explain here. So this is PC1, this is PC2. Now, things which we have to remember was we had 4 features: sepal length, sepal width, petal length, petal width. Out of that, we have converted those 4 features into new 4 features using PCA, PC1, PC2, PC3, PC4. And we have chosen only 2, and we have looked into the variation component also, that these 2 cumulatively had information of around 95%, as we also can see here, 72.9 plus 22.8%. So now if you notice here, what I'm trying to show is 0 is Setosa and 1, what is 1? So let me print this to understand what was 1. Let's close this and then run it again. Yeah, so there would be a name here now, target names, which I wanted to see. We have printed the target names, but it has to be somewhere. Let's see, where is it? Target names. Yeah, so Setosa, versicolor, and Virginica. So that was I was not able to recollect versicolor. So it's 0, 1, 2 in our case, because we are using, instead of using target underscores names, we are using targets, which has converted Setosa to 0, versicolor to 1, and Virginica to 2. If you want, you can convert this legends from 0, 1 to 2, versicolor, Setosa, versicolor, and Virginica. Okay. So now, if you notice what we are seeing here, this is our class 0, this is our class 1, this is our class 2. Now, if you notice, with these 2 components also, we are able to segregate our classes with quite good efficiency. What do I mean by that? See, I can segregate this. If I want to use any logistic regression or anything else, say any hyperplane or anything, I can quickly segregate this 0, 1, 2 quite easily, because you can notice that there are no mixes with red color, mixes of red color with green and blue. So Setosa are it's quite easy to classify. But if you notice green and blue, which are versicolor and Virginica, there might be a chance when you perform your prediction algorithm here, you might encounter 1 or 2 misclassifications. And when you do your original logistic regression on your 4 original input features, you can also observe what is the accuracy in that case, what is the confusion matrix which you would create, and what would be the final result in that case. And when you do with PC1 and PC2, you can also observe that. So let's try doing that. So what I wanted to do, yesterday's code is still not running because this SK learns this version what I have and the version in which this runs are quite different. So I'll take this same data set and then let's see what is the accuracy which we are getting. Okay, so let's use this first. So what I'm doing here is I'm splitting the data, right? And if I'm not wrong, we have already done this in one of our models. So in SVM, we have done the same thing. Remember guys, we have used the same data set, right? So let's do one thing and let's split the data again into our PCA analysis. So let's split the data. X train, X test, Y train, Y test. And then instead of X and Y, what we have here, df underscore standard. Let's take the original data set first. Okay. df underscore X underscore standard. And then df underscores Y underscores standard. Okay, let's take 20% of it in test. Okay, makes sense. Now what we have to do, if I'm not wrong, now we have to import logistic regression or linear models, right? From sklearn import linear models. Okay, and now from sklearn we are importing linear model, and then we have to assign this logistic regression to some variable, right? Linear model dot logistic regression. Okay, and then we have to fit this, right? So where is our logistic regression code? Let's copy directly from there, which we have already done in our earlier sessions. So instead of doing all this thing again, let's copy it from here. So let's go back to our PCA and then let's run our logistic regression. Okay, so what I'm doing, I'm assigning this to some variable CLF underscores multi, this logistic regression, and then I'm fitting this on X train and Y train, and then I'm predicting the score for X test and Y test. Let's not use this for the time being. Okay, this makes sense to me. I think it should run. Let's see what happens. First, I have to close this graph, otherwise I won't be able to run this in Python code. Again, this graph has opened because I have to comment this because we have already understood this graph using PC1 and PC2. Now it is throwing some error. df underscores Y underscore standard is not defined. So yes, we have not come up with any df underscores Y underscore standard, right? Y was directly df underscores Y. So let's directly take that df underscores Y because those are targets, right? 0, 1, 2. So now let's run this again. Neither name nor data underscores ID are provided. Yeah, so these are all warnings. You can neglect it. But what we need to understand is the score. The score is 93.3%, right? And then let's do the same thing using principal component analysis. Okay, so before running the same thing on principal component analysis, are there any doubts? Because I think it's 5, and then so as we have already seen the accuracy with logistic regression with original data set where we had sepal length, sepal width, petal length as the features, the accuracy is around 0.933. So now, to clear yesterday's doubt, how does it affect to our accuracy? Let's do the same thing with PC1 and PC2. Okay, now let's run the same thing on, let's change the variable name by say _1, or let's say new name as say PCA, new variable PCA, okay, and this time what we would do is, let's comment this, the previous syntaxes, otherwise this will throw error, because it is X train and Y train are using the same thing from the train test split, right? So we have to log this, we have to comment this, and here instead of X and Y, we have to use our data sets which had PC1, PC2, and so this was our X where we had only PC1 and PC2, remember? So let's copy that for our X, and for Y we had final DF, right? So let's use this Y, and in this we have a column by name target. It's target, right? Yes. So we can live with this now, and then let's try the same thing here. Let's see what would be the accuracy, but it should be dot. That's the reason it is giving error. Okay, dot target, right? So this data frame has only PC1 and PC2. This was our final data frame where we have concatenated PC1, PC2 with the targets. So that's the reason now what we are doing is, instead of putting the original data set input features, now we are putting modified input features which are PC1 and PC2. And then this is our final data frame where we had concatenated target, and then we are only using target for our Y variable. Okay. Now let's see how does it work. So now if you notice, the accuracy is 0.9. Now let's do one more thing. So what we have done, we have only used PC1 and PC2, right? Now let's use PC3 also. Let's try that. There is no harm in trying. So let's try that as well. PC3, and let's see what happens now. So now, as I was telling yesterday, now we had only PC1, PC2 and PC3, and then the accuracy what we are getting was equal to the accuracy what we had with the original data set, right? That means the PC4 had almost negligible information carried by that, and we have already seen that yesterday it was around 0.5%, because this all three PC1, PC2 and PC3 is carrying 99.5% of information, and with that still we are able to come up with the same accuracy, right? So that was the whole point which I was mentioning yesterday. The accuracy might be equal if you are able to, if you are removing one of the features, say PC, like the one which has very least information in principal components. But then of course, if I remove PC3, then our accuracy was going down, as you have already seen. Now let's use only PC1. Okay. Now what do you think? What could be the answer? As expected, the accuracy should further go down, right? With PC1 and PC2, we had the accuracy of around 0.9. So let's try with only one principal component which had information of around 72.9%, right? So let's try this and check what happens. And you have note, okay, so now we had only PC1 where it is carrying only 73% of the data, right? But then if you notice, the accuracy is still not down. We have expected the accuracy should go down, and that was the thing, that was the assumption which we had yesterday, right? So that was the reason I told it's not necessary that accuracy should be dependent on your principal components. The reason why your accuracy is not going down is because the PC1 had all the information which might be sufficient to determine your output. Okay, that was the reason that PC1 we are getting quite good accuracy, but it's not necessary. It depends on the data set. Here our data set is very simple and PC1 is quite sufficient to give us the solution with same accuracy, but we are only looking at accuracy here. Yes, you're right. You have got a point here. Why is it? It is because even though the variation of the data, what is that variation of the data means? It is variation of the input data, right? You had x1, x2, x3, x4 initially. Now you are coming with PC1, PC2, PC3, PC4. Even though we are capturing 95% of the information or the variation of the data using PC1 and PC2, but then the accuracy is decreasing with PC1 and PC2, but it was almost same with only PC1. That means PC1 was alone sufficient in terms of coming up with a good prediction rather than having PC1 and PC2. But amount of information carried only with respect to inputs. Okay, PCA works only on input features, right? That's the reason PC1, we are calculating PC1, PC2, PC3 and PC4 and tells that the variation of the data is captured in this principal components only of the input features. But we never tell how does it influence your predictions. PC1 is never used for better predictions or lowering down your predictions. It just captures less variation of the data and it reduces your computational time. That is why we use PCA. And that was the reason when you have asked this question, I was quite resistant. I was quite hesitant also, that I was telling you that it is not sure that when we are using principal component analysis, it's not necessary that your accuracy might go down. I was quite resisting yesterday in the previous session. So that's the reason I told it's not necessary that if you are taking very less components of principal components, your accuracy should go down or go up, or it might be equal. Principal component analysis is just that it captures, it is used for converting your original input features to new features based on the amount of variation of the data being captured. Based on that, it helps only in reducing your computational time. But as we have already seen, when I write 1 and then with 73% of the variation of the data, original data, we were able to come up with the accuracy which was 0.933. That means that clearly suggests that PC1 is influencing more to your output. That means your predictions are highly influenced, or your outputs are highly influenced by PC1. And when you put PC2, your accuracy is going down by 0.033, right? So it could be because PC2 might be carrying the amount of information, like 22% of the information is being carried, or like 22% of the variation is being captured by PC2, but it might not be that useful in terms of influencing your output. So that was the reason I told yesterday also, when we have input features x1, x2, x3 and x4, and x4 is, let's say x4 is x1 plus x2 plus x3. Then how does x4 is influencing your output? It's just a linear dependency of x4 on x1, x2 and x3, right? So that's the reason I told that we cannot comment whether your accuracy will come down with using PCA or it will remain same. Okay, so we cannot comment on that. So let me tell you that with 2, when I'm using 2, it depends on the data also. That's the most important thing. With 2, that means 95% confident, I'm getting accuracy 0.9. But when I'm going with only 73% accurate confidence, my accuracy is 93.3%. It's because PCA is never meant for reducing or increasing your accuracy. PCA is just meant for speeding up your simulation, speeding up your compilation of your code, executing your code. Okay, that was the reason yesterday also I told that you cannot judge whether your R square will increase or decrease when you use principal component analysis. See, here you have already noticed with 73% of confidence, our accuracy is quite high. But with 95%, our accuracy was 90%. That means this 73% of the data which we have captured using PC1, it is quite sufficient to give the same amount of accuracy which we were getting with all the input features x1, x2, and x3 and x4. That itself suggests that instead of running this code with all the input features, we can run with only PC1. Again, make sure the sentences what I'm telling is limited to this data set only. Okay, let me read your next question. So we cannot say this is better, right? So only accuracy would not be a good parametric for comparison. Yes, as I already told, accuracy is not always accuracy. We cannot tell that accuracy is a better measure. We cannot tell that. If I look only for accuracy, we can tell that with 73% information and with original data set, I was getting same accuracy. So I have never tell that accuracy is a right measure to check for. There are a lot of different parameters, and some of them, if you remember, precision, recall, true positive rate, all the remaining things which we have discussed in our earlier sessions. And then this amount of information which we are carrying, the amount of variation which is captured using principal component analysis, it might be a limitation somewhere else because we are only capturing 73% amount of the information. But the advantage of PCA here is it is speeding up your execution of your code. Okay, people generally use PCA only for reducing your computational time, for dimensional reduction techniques. It has never been implemented to reduce your accuracy or increase your accuracy. We cannot judge on that. Okay, and yesterday that was the reason that I was slightly skeptical how does the accuracy behaves, and now it is quite clear. Your accuracy depends on your data. What features are influencing your output, what input features are influencing your output. Okay, anyways, this data was very small, so it was quite easy to understand. Now let's start with 12th week session, which is deep learning or neural networks. So one small disclaimer before we start with 12th week session for introduction to ML and AI using Python for mechanical aspirant. One disclaimer, this would be slightly complicated, and what I will be putting here, the points which I'll be putting in this week would only be serving as the base for your next course. Okay, for your advanced course. Okay, so this will not influence your final project. This has nothing to play any role in your final project. But if you are able to do any project using this technique, which is neural network, it's well and good. If you're not, it's not a problem at all, because there is a complete course on this neural network which we'll be looking in our advanced course. But what I'm doing in this session is I'm just putting some base for that course. Okay, before going ahead, what I had asked some puzzle yesterday, were you able to get the answer? Okay, so I think I'll repeat this question, and then maybe what we can do, I'll quickly explain this. Okay, do you want me to explain, or shall I keep it as it is so that you can work on it? I'll quickly explain the question once again. So Naga, the question was, we all know that there is a chessboard. So the question was, there is a chessboard, right? And we know that the chessboard is of 8 by 8 most of the times. Not most of the times, like as per international rules, it should be 8 by 8. Now, if you notice, there will be some intersection points, right? So these are called vertices, and these are called vertices. These are called vertices, right? Vertices. So it's pretty clear that when you count this number of vertices, that would be 81 vertices. Now, with this 81 vertices, I have asked how many triangles can be formed. That was my question. Because we need, for triangle, we all know that we need 3 points. So how many triangles can be formed with this 81 points? I could have actually asked this question with 81 points also, but there is a slightly challenging task here which you need to think on those lines. 81C3 would be the total triangles, but many of these triangles would be actually lines. Exactly. So you got the logic right. But what is the right final solution? That you guys need to think, and then we can discuss that in our support sessions. Okay. I cannot form a triangle with these 3 points. So you got it right. So this is quite complicated. Think on this and then let me know the answer. Okay, so I will not be asking any puzzle for today because I think you are already working on one puzzle, and then I have to keep some puzzles in the next course also, right? So before going into neural network, I want to explain few things once again on logistic regression in a different style now, into a different style. Let's say I have 4 input features. Now I am denoting these 4 input features as circles. The circles are called neurons. These are called neurons because neural network is the one which try to replicate our mind, and our mind has, I don't remember the exact count, but it's in millions. You would be having millions of neurons in our mind, right? So if you want to do complete artificial intelligence with very high accuracy, we would need those many neurons to perform our analysis. But you can imagine how much computational time and how much computational efforts it would take. So if you remember, we had this x1, x2, x3, x4 as input features, and let's say we have the output as binary output. Okay, say 1 or 0. Okay, so let's say our output has 1 or 0. So what we have done, our all input features were going directly to our output. All the input features were trying to predict what could be the output, whether it is 1 or 0, right? So based on certain criteria, and then what was our logistic regression equation, if you remember? Let's denote this as Z now because this would be useful in this session. And say, what was it? Beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4, right? And then we have used sigmoid function. I still remember the question which you have, why the sigmoid function is considered. The solution, is it because that sigmoid function ranges from 0 to 1? Is just because of that we are using this as probability? I still remember that. For that we have to wait for the advanced course, guys. Okay, so anyways, the sigmoid function is represented as probability, right? And that was this. So using this we have done our logistic regression. These were the equations which we have used in our logistic regression. Okay, so far so good. Now let's say that this is my input x1. Please try to understand the terminologies and the figures. If you're not able to understand the math, it's okay, don't worry. We have a separate session on this. But for me, it's important that you understand the figures and the concept right now. So what do you think, what is the difference between these two graphs? Sorry, in these two diagrams or in these two figures? See, in logistic regression, we had input features. Using input features, we were able to predict whether the output is, whether it's for binary classification, whether it was 1 or 0, right? And then for predicting, each one of this would have some weights. Okay, ideally these all will have some weights. So this is how our mind also works. Neurons, and then from neuron, using synapses, you can look into this graph, this plot in Google, dendrite. How does dendrite works? Okay, so you can look into this figure in Google, but then there has to be some information which needs to be carried out from neuron, right? So that it tells what could be our output, whether it is 1 or 0, right? And that is what, if I want to convert my logistic regression equation, those are called as weights. This beta 1 would be now W1, This, I'm just changing the terminologies now. Understand this. And this is denoted as B, bias. So now weights and bias, I'm just writing in a simpler form. And then this would be substituted into your sigmoid function. Did you understand? Okay, don't worry about the left figure. Did you understand the right figure? And the equation, what I'm trying to do? So far so good. I'm just converting beta into W1s. So those are weights. So it carries the information from neurons to output. Based on that information only, like in our mind also, there are synapses which carries the information. Okay. So that is how we predict. Like for example, if you see two fruits, apple and banana, in your mind, how would you know this is apple and this is banana? Because in our childhood we have been trained like that when we see apple, we know that our brain works in that direction. We call that as an apple, and banana as banana, because that is how our mind has been trained, right? But just imagine, this is very simple algorithm, which is logistic regression. Did you ever remember in your you have called banana as let's say watermelon, or let's say mango, in your childhood days? Because you don't have enough knowledge, right? You are not yet trained. Your parents might have told that this is apple, this is banana, but it's very difficult to recollect that, right? So how do we get trained that this is apple and this is banana? Again and again, we used to get trained by parents, right? Again and again, we used to get corrected. Again and again, we used to get trained. So what I'm trying to tell here is, here in logistic regression, you have trained only once. Just assume in that way. But here, when I'm putting an extra layer, this is called as hidden layer in neural network. So in this case, what happens, from X1, the information is being carried from all the X1, X2, X3 and X4. And from X1 also, it will carry to other neuron also. So this might look very complicated. Okay. So what I'm trying to do here is, with the help of hidden layer, I am trying to correct myself in between one more time. I'm trying to get trained one more time using this hidden layer. Before predicting the output, I'm just trying to predict few more intermediate points, and we will check whether those points are correct or not. And based on that, then we will predict what is our output. Did you understand this analogy, what I have given with respect to fruits and this one hidden layer? What we are trying to do here is, we are trying to get correct. We are just getting corrected one more time. Think in this way. Did you both understand this? I know it's quite complicated, but I'm just trying to give you some analogies based on this. Okay, one more thing. It's not necessary that hidden layer should have less number of neurons in comparison to your number of input neurons. It's not necessary, okay? It can have equal also. Let's say this is your X1, this is your X2, this is your X3, this is your X4. So these are our weights. Yes, now you have a right point. So imagine that for this 4 points with this weights W11, W21, W31, W41, say you are using logistic regression and you are achieving this point. Okay. Now with this different weights, you are getting another logistic regression and you're using another logistic regression here. And with this new data points, say here you have, now your x1, x2, x3 and x4, using x1, x2 and x3, x4 with these different weights, you are coming up with new inputs, or let's say these are the outputs for your x1, x2 and x3, x4 based on different weights. Okay, these are the outputs. A1, A2 and A3. No, you don't decide the weights. So before, okay, so and then using A1, A2, A3, now this would be considered as your input to your final output. Okay, so what we are doing here with this weights, first we calculate Z here, and you remember the formula for Z, right? Wx plus B, all those coefficients. Using this Z, then we calculate this A1. How do we calculate? By sigmoid of Z, which is 1 by 1 plus e power minus Z. Here it will be Z1, here it will be Z2, here it will be Z3. So similarly, I will calculate A2 and A3. Okay. Now, I'll just tell your answer on this, how do we decide weights, and then the detailed thing of deciding the weights will be in the next course anyways. I'll just quickly tell you. Do you remember in linear regression, how did we decide these values? Beta 1 and beta naught and beta 1. Let's take the same analogy with Wx plus B. Take the same analogy with Wx plus B. Do you remember how did we evaluate this beta naught and beta 1 in our linear regression? Yes, that learning rate, right? So we have to minimize our error. Based on using gradient descent, we have come up with beta naught and beta 1, right? So similarly, here also we will minimize our loss function. So in this case, what would be the loss function? I'm using logistic regression here, so it will be loss function would be the logistic regression loss function. And we haven't discussed the loss function for logistic regression. I've just told you that log loss, the loss function for the logistic regression can be calculated using log loss. Okay, so just remember that. Don't worry how do we calculate now, but I'm just trying to give you mathematical intuition that these weights are also calculated using by reducing the error. Okay, so now if I try to explain this, how do we calculate and all, it would be really difficult because this requires the knowledge of derivatives. The way we have done in linear regression, we have to do the same thing here. Do you remember how we have done it? We have calculated the derivatives and then we have updated our beta naught and beta 1. Similarly, we have to calculate the derivatives and then we have to keep updating our weights. Okay, but then if I go into more detail now, there are high chances that you might get confused because this is just a opening. This I'm just trying to put some base for your next course. Okay, but there is one thing which I can tell you now is why I am using this activation function. So this A1 are called as activation functions. So in this course, you have to remember all the terminologies which I'm using. Okay. Activation function 1, activation function 2, activation function 3. Okay. And how do we decide how many neurons we need? It is again hyperparameter. Do you remember what is hyperparameter? For random forest, what was the hyperparameter, guys? By changing the parameter, your accuracy also changes, right? So number of trees. Similarly, what was the hyperparameter for linear regression? What was the hyperparameter for linear regression? Learning rate, exactly. Similarly, deciding the number of neurons in your intermediate layer, which is called as hidden layer, is also a hyperparameter. So this will not be coming in straightforward. You have to decide how many of these hyperparameters are required. And this can only be achieved by trial and error. And once you do a lot of projects, then only you will come to know how many neurons should I use. But that is, hyperparameter is generally trial and error, right? So now this is our activation function. Okay. Now just assume that, okay, before going that. So I'm using this activation function here as sigmoid function. Okay. So there are different types of activation functions in neural network. But let's only think as of now with sigmoid function because I don't want to confuse you. Okay, so one thing is from the input features, you predict something which are called as intermediate hidden layers. From hidden layers, you're predicting your final output. And in your hidden layers, you calculate this z values, which is wx plus b. And then you calculate activation function, right? And based on this activation function, again it goes here. And then what it does, it's very important that you understand this very simple architecture of neural network, which I'm trying to explain you. Let's say there are weights, okay? I don't want to put those lines now. Okay, try to follow this. Okay, guys? Can you tell me what does this indicates? This superscript 0, 1 and 2? Like what do you think what this could be? Superscripts? Exactly, those are layers. And we always called input features as 0th layer. This is our intermediate first layer, which is hidden layer. So this is first layer and this is our second layer. Okay. Now imagine that this is not there. Just try to think in this way, guys. Imagine that this layer is not there. Then what it tells? It is as simple as logistic regression. That now all these lines directly go to for predicting your output. Yes or no? Is it as simple as your logistic regression? And I'm not taking a logistic regression loss function here. I'm just trying to come up with an analogy with linear regression in terms of, because we have not learned the log loss function, the loss function for logistic regression. I'm just taking the analogy only with respect to loss function. Just consider the analogy for only loss function now. So in linear regression, what was the loss function? Mean square error, mean absolute error, something. And then what we used to do, we used to find the derivative of this loss function with respect to beta naught and then beta 1. And this derivatives, using these derivatives, we used to update our beta naught as beta naught minus or plus, it doesn't matter, learning rate into d loss function divided by d beta naught. Beta 1 is equal to beta 1 minus alpha dl by d beta 1. Do you remember this gradient descent for linear regression? So in that case, if you remember, we have started with some random values of beta naught and beta 1. We have started with random values of beta naught and beta 1, calculated loss values, found the derivative of loss function with beta naught and beta 1, and then we have updated beta naught and beta 1, right? Again, with the updated values of beta naught and beta 1, we have calculated the loss function. Again, we found the derivative of that. And then again, we have updated beta naught and beta 1. Okay. This is called as gradient descent method. Okay. Using gradient descent method, we always try to achieve or minimize the error. We try to minimize the loss function. Okay. In linear regression, our loss function was mean square error or mean absolute error. But in logistic regression, we have a loss function which is something else. For time being, assume that is a log loss function that we'll be seeing in the next course. That is called as log loss function. But the methodology in logistic regression also is same. It is same. What we do in logistic regression is we derivate and then we update the parameters and then we calculate the loss function. Again we derivate, we update our input fee, we update our parameters, and then again we calculate the loss value. So the way of doing gradient descent is same. Did you understand this? See, the function, the equation might be different. In linear regression, it is mean square error. Here it is some other expression. Don't worry about that. But did you understand the steps of gradient descent method? Right. Similarly, here also, we actually randomly gives our initial weight values would be decided randomly. This value would be decided randomly. And then this, what we are trying to do here, finding the derivative and then updating our beta naught and beta 1, and then again calculating the loss value, and then again taking a derivative of this, and then again updating your beta naught and beta 1, is you're trying to always go back and correct your beta naught and beta 1, right? In linear regression or logistic regression, like you're correcting your weights indirectly. So this going back and correcting your weights is called as backpropagation. Okay. Similarly, here we start with some random values of weights and then we calculate the error and then using derivatives, and then we go back and then we correct our weights. So in logistic regression, you had the opportunity to correct your weights only one time, with many iterations of course, but then you have to correct it only like this, right? From output to your input layer. But if I bring in one additional layer, now just imagine I'm just bringing one additional layer. So now what I'm trying to do here is I'm doing the backpropagation 2 times. So I'm correcting my weights again and again. When I correct my weights again and again, what happens, the accuracy of the model would be quite high. That's a simple concept which I'm trying to explain. When we do not have this yellow color layer, which is hidden layer, we generally what we do, we calculate Z as Wx plus B, and then we calculate the probabilities using activation function. Let's, in neural network language, it is called as activation function, which is 1 by 1 plus e power minus z, right? But instead of doing this at taking this input features and then directly going and predicting your output, what I am doing, I am incorporating one additional layer with some more features, and now those features are called as A1 for layer 1, A2 for layer 1, A3 for layer 1. Initially we had 4 features, now we have 3 features in this layer. Okay, now with this W1, W2, W3, W4 with suffix 1, we calculated first Z1 and then we have calculated A1. Similarly, with W1, W2, W3, W4 with suffix 2, we have calculated Z2 and then we have calculated activation function 2 for layer 1. Similarly, activation 3 for layer 1. Now this A1, A2, A3 will be used as input features. Okay, and then it will use for your prediction. It will be used for your prediction. Instead of going in logistic regression, it was only one layer. Now we are having, in logistic regression, we had only one layer, right? Input to output. So directly output was A suffix 1. But now we have two layers, which is one hidden layer and one output layer. So in this way, we have got more opportunity to correct our weights so that our prediction is even better. That is why we are using this neural networks here. Don't worry about the maths now, but did you understand the concept? That's what my main aim here. We'll see the maths in the next session, in the next course, and then we'll see this backpropagation. There will be a lot of maths, okay? So please be prepared for that. The architecture which I've shown with one hidden layer, in reality, there can be lot of hidden layers. So there can be different architecture. And how does it looks like? I've taken some examples here, okay? This is called as single layer feed forward network. This is called as single layer feed forward network. So there is no hidden layer. That is the reason it is called as single layer, and you have multiple outputs. You can have multiple outputs. In logistic regression also, if you remember, we can have 0, 1, 2 as our classifier outputs, 0, 1, 2, 3 also. So based on that, similar to that, okay? So this is called as feed forward because we are going from inputs to output. That's the reason it is called as feed forward. Now the example which I have taken with hidden layer is here. This is called as multi-layer feed forward network. Here what we are trying to do is, for these input layers, these are the output, but your final outputs are here. So for this outputs, final outputs, this hidden layer would be considered as your inputs, okay? So now you have the opportunity of correcting your weights additional time using hidden layer, right? So that's a reason we always, like the ones with the neural networks with having some hidden layers would be having more accuracy rather than having zero hidden layer, okay? And now there is something called as third one is single node with its own feedback. So what happens, you have some input and then you want to predict the output. Your output values, based on the output values, you will get the feedback on the input. We give that feedback to your input and then we try to correct the prediction, okay? And similarly, we have single layer recurrent network. For example, these are our inputs, these are our hidden layers. Oh no, sorry, these are not hidden layers, these are our outputs y, and then we are just recurrenting. That means we are giving the feedback of that to we're giving that feedback to its own layer so that we can correct the output, okay? And then here, similar to that, in the multi-layer recurrent network, we are giving the feedback again back to our node. So don't worry about recurrent network, okay? Don't worry about recurrent network. In our advanced course, we will be learning this multi-layer feed-forward network. That itself will take around, that complete course will be on this multi-layer feed-forward network, okay? Don't worry about recurrent network. And again, because there are a lot of different architectures in outside world, okay? And there are some more neural network architecture which is called as convolutional neural network. In recurrent neural network, you are giving the feedback and then you are just trying to come up with a better solution. In there is something called as convolutional neural network again, which is highly recommended for image processing or object detection problems. But then again, that is not designed for the course. We will be looking only for, there is one separate course which will be looking for where we'll be looking only feed forward network, okay? So coming back to our basics, what we do is we import the libraries in Python, we import the data set, we split our data set, and then we train the model with a training data set. we run the predictions on our test data set, and then we check our validations, right? So this is how we work. Okay, I'm just trying to repeat few things how we work in a machine learning project. But here my only objective was to explain that instead of using single layers, which till now we will working with only single layer, right? But this is a single layer feed forward network. So but in future, when you use multi-layer feed forward network, it is called as deep learning. So you have deep models, like you are coming up with lot many layers. Okay, you can always increase these hidden layers. If you increase the hidden layers, it is generally called as deep learning model. Okay, and that is also an advanced machine learning model. Okay, so our third course would be completely on deep learning, multi-layer feed forward network. Okay, so I want to repeat few things again, which would be again useful for this complete first course, which I've already told this. You have to follow whenever you get a new project, you should always follow this cycle in the clockwise. And also in this, before splitting the data set, you should do exploratory data analysis also. Okay, you should always do exploratory data analysis. Don't forget to do that. Okay, but then deep learning will be really helpful because your computer train itself to process and learn from data. Okay, so deep learning is very highly advanced machine learning model which we'll be learning in the coming course. But I'm happy if you can understand this feed forward network itself. If you can just understand feed forward multi-layer network, which I've explained now, if you can understand that, I will be really happy with single hidden layer also, because anyways our deep learning course is designed with more number of hidden layers. So at that time we can look into that, but it's similar. You would have one more hidden layer inside, and then here we are looking with a superscript 2, there will be a superscript 3, a superscript 4. So that would be more challenging and you will see a lot of maths in that. Okay, but you don't have to worry. If you can understand the concept, that is fine. Now you will understand the maths in next session, in next course. Okay, so please always remember this cycle when you are working on machine learning project. With respect to Python or any other coding language, I don't mind, but always remember this cycle. Import the libraries, then import the data set, do exploratory data analysis, and then split the data set, train the model, and then predict using test data set, and then check the score. Okay, finally I would like to tell few more things with respect to classical machine learning and deep learning. Okay, few differences in this two, because why people are moving towards deep learning. Okay, so in reality what happens, we will have a lot of data. So when we have a lot of data, more the data, better the prediction, right? Because it will be useful for predicting our output if we have more data, right? So in general, if we have more data, we should try to use deep learning rather than classical machine learning, because if we have more data and if we use deep learning, you would get better accuracy. Okay, that's the first thing. Now, what is this training, dev, and test data set? Instead of splitting the data set into two and splitting the data set into three, it's okay if you split into two, don't worry about that. If you still split into two, 60-40 or 70-30, which you do in machine learning, till now what we have done was 70-30, 80-20. That's fine with machine learning algorithms. But once we start with deep learning models, in deep learning models, we will have a lot of data sets, right? And if we have a lot of data, in that data set, we should try to have 95% in training data set and 5% in test data set, or 98% in train data set and 2% in test data set. Okay, more the data you keep, because now you have the liberty to keep a lot of data in your training data set, because for 1 million samples, if you take 1%, that would be like how much? 10,000. So 10,000 are quite sufficient in your test data set. Here you had the data set of 10,000 samples. That was the reason we were splitting into 70-30 ratio. But here we had around 1 million samples. So 1% would also be like 10,000. So you can keep that into test data set and the remaining can be in training data set. Okay. Now, as I've already told this, the light blue colors are say that this belongs to one class and this dark blue color belongs to one class. And if I split that using this linear line, what I'm trying to do is I'm underfitting my model, because you should notice that I have some misclassifications here in the first figure. That means high bias. That is also called as high bias. In the rightmost figure, what I'm trying to do here is I'm trying to classify all my data with zero misclassification rate. So in that case, what I'm doing is I'm complicating my model. When I'm complicating my model, this might work very well for the training data set, but might not work quite well. It might not be able to generalize for test data set. That's the reason it is called as overfitting, and that is also called as high variance, right? And now, as I already told, this is just the middle graph is a just right optimum one. Okay, neither underfit nor overfit. The next point is, so far so good. Any doubt, guys? Okay, so when I have already told you this, if I'm not wrong, if you have a model underfitting, then try to complicate your, or try to come up with more input features in your machine learning model, right? But in your deep learning, if you are facing with high bias, which is underfitting, which we'll again see in third course, you have to have bigger network. That means more number of hidden layers. Okay, so always remember this. When your model is underfitting, try to complicate your model. So that it goes from underfitting to optimum model. If your model is underfitting, try to less complicate it. As you can see in the figure, these three figures what I am showing here. In these three figures, as we can see, underfit is a very simple. Try to complicate it so that it can go to the optimum figure. If it is overfitting, that means highly complicated. Try to complicate it quite less in simple English. So for machine learning, we have already seen, if you are underfitting, then increase the number of features. And if it is overfitting, try to use some regularization techniques or some other, try to get more data in your training data set. Similarly, here also in deep learning models, when it is high variance, try to train your model with more data at the training period or some other regularization techniques. Okay. If you are facing with high bias, then try to complicate your model. Complicate in the sense, have a bigger network. Okay. And again, this is the error values which I've already talked before. This we have already talked, so I need to correct this. There is some mistake here, I believe. Okay. So meanwhile, so far so good. Variance and high bias thing, I will correct it. Okay. These are actually image, so I'm not able to do. Ideally, this is low. Okay. So I tried correcting it, but then this is image. So yeah, so what I was telling is, see, these are the error values. I'm just trying to tell the same thing here. When you have, these are the training, let's say these are the training errors, these are the test errors. Okay. So for training, if you have 1% error, ideally, if your error value for test is very high, then it is overfitting, right? That you have already complicated your model for the training so that your training data predicts your output quite well, but then you are not able to generalize that for test. That's the reason it is a overfitting or high variance. Similarly, if your training data set error is quite high, assuming that human gets 0% error, then this would be quite high, right? And this is quite high. And if your test data error is 16%, that means the difference here is very less. But this difference and the difference with human error is quite high. That's the reason it is underfitting, because your training is not behaving quite well. If your training data set is not able to predict your output well, forget about test data set. So it is underfitting, okay, or high bias. Now in this case, if you notice, your training data set is 15%. If I compare that with, say, human error, which is say again 0%, and then between this the difference is very high. So this is already high bias, which is underfitting, and then the difference between these two is also very high. So this is also overfitting, that means high variance. Okay, so high bias and high variance. Now in this case, if you notice, the error between human percentage So the human error is again 0%, and the difference between the training error and human error is very negligible. So it's a low bias, which is not underfitting. And then the difference between these two error is also very small. So it's a low variance also. That means neither underfitting nor overfitting. So this is a just right model. Okay. So here it is training error. This is test error. And this is low bias and variance. Okay. This is how it should look like. Okay. So I will be changing this, apply up ANN. This is ANN is artificial neural network to the same data set, but I'll be changing this challenge for this. I'll be putting some more challenges. So which will be quite theoretical and mathematical. I will be removing this because I don't want you to implement artificial neural network now in Python, because that would be anyways there in third course. Okay, so I'll be removing this, and I'll be putting some new challenges here, mathematical and theoretical challenges, and that I'll be sharing with Roshan again. Okay, because I have not explained you how to implement this in Python. Anyways, that's there in third course, so I don't want to do that now. Okay, so what we have learned now is machine learning. Okay, in the next course which I'll be talking will be purely mathematical and application of maths in machine learning. So what all we will be seeing this permutations and combinations, probability in great depth, and then statistics, confidence interval, all those things we'll be noticing in then mathematics and applications. And then derivatives, backpropagation, gradient descent, log loss function for logistic regression. So all those things will be looking into this course, which is purely mathematical. So you have to gear up for that. Okay, I'll try my level best that you would love it. The maths is very simple, don't worry, but it's just that you might see the same equations repeating again and again with different subscript or superscripts. Okay, that's it. The equations are very less. Okay, you don't have to worry. And then in third course, we'll be looking at for deep learning. Okay, so this will be dealing with multi-layer feed-forward network completely. That one algorithm will be looking into that one algorithm in very great depth here. How to improve our deep learning model, what happens if it underfits, what happens if it overfits, how to play around with hyperparameters, how many hyperparameters do we have. So we will be looking that into great detail in this deep learning model. Okay, so all the machine learning models are covered in this, and we have learned supervised machine learning. So I'm just revising so that you all should be knowing this. We have looked into supervised machine learning model. We have looked into unsupervised machine learning model. Okay, so now important part, to achieve a job, if you do this course machine learning, which I've from last few weeks which I've been taking, if you do this course, you are good to go. Okay, you are good to go to fetch a job of machine learning. You can, if you start working, if you complete all your challenges, and projects and get your doubts cleared while working on projects, then start building your resumes based on machine learning. And then based on this, you should be able to start with placements. So you should be ready for the job if you do only this course. Okay, but then again, if you want to get a good job, and if you love mathematics, and if you want to land up into a job which deals with a lot of maths, then I really recommend that you complete this course also and then start applying for a job. And there are a lot of companies which deals with advanced machine learning. So there we will be looking. If you want to complete this course and then start applying, it's up to you. But you can always start applying for a job as soon as you complete this machine learning course completely. Okay. Also remember that you have to do a lot of hard work. If you're not able to understand anything, please explore things. You will learn a lot of things. Okay. Spoon feeding will not help here. If I directly tell you the answer, then you will not learn a lot of things. Okay. So first, whenever you're stuck, try to explore it. Okay. Then only you will learn some more things. So, and one more thing which I wanted to tell is, once you complete these two courses, first and second, you should be so good in at least two algorithms. You should be very good in at least two algorithms, in and out, with concept, with coding, and then with mathematics. In that way, in an interview, you would be able to tackle all the interviews very easily. Okay. So whenever you're going for an interview, just make sure that you are very strong in at least two algorithms. Again, I want you to tell this: for any project which you are working, always follow these points, because these are the important points which I always explain to all my students. Import all the necessary libraries, which are NumPy, Pandas, Matplotlib, and then for confusion matrix you already know, and then scikit-learn, which has all the inbuilt machine learning libraries. And then import the data set using pandas. Okay. And then do a lot of descriptive analytics. Now it's the high time that you should, whenever you get a data set, try to find the mean, median, mode, variance, standard deviation, skewness, kurtosis, and then try to plot different graphs such as scatter plot, histogram. It's always good to have a graphical representation, bar chart. Try to do that. By that you will try to understand the data in a better way. You would be able to digest the data in a better way. So that is something which you always have to do. Okay, EDA in between. And then splitting the data, I always tell my students, try with 70-30, 80-20, 90-10 in machine learning models. Try to do all three. Check which split is giving you better results. Okay, there is nothing harm. It's just a matter of one additional line which you have to run. Okay, and then train your model. Okay, try to train your model with all the possible algorithms which you can use. Okay, I believe that you must have noticed that I have explained decision tree, random forest, and this KNN only for classification, but this can also be used for regression, right? If you remember, I have told you in the class. So you have to look into those details also, how to use those algorithms for regression. Okay, I have explained you only for classification, because there are a lot of projects which are more with respect to classification. Okay, and then once you train the model, then do the predict it on test model. Okay, which is very important, and then check the score. And based on score, when you do the validation, it's not only accuracy, you have to calculate different parameters, which I always tell, such as precision, recall, accuracy, and all other parameters, and then decide for what all parameters are required for your project. Based on that only you have to evaluate. Sometimes your accuracy might be very high, but that might not be preferred, because the project which you are working might be clinical trial problem. For clinical trial problem, sometimes precision or recall will be preferred. So you have to check based on that. So I sincerely advise you guys that start working on all the challenges, complete your challenges, submit your challenges to the team. Okay, and I will change the challenges for week 12. That's all which I wanted to tell for in today's session. I will not be going into Python coding today, because that would be slightly difficult. If I explain it to you now, it would be better if you look at Python coding in third course, into deep learning course. Okay, so any questions? This is a time where you can have some questions, and then in support sessions you can ask questions more on your challenges, because by then you will start working on your challenges. I hope you have already started working on your challenges, but still in the support sessions you have the advantage to ask a lot of questions on it from your challenges. You can ask a lot of questions from your theory part, conceptual part. But do you have any questions now? Yes, we'll be going yes, we'll be going into second course only after completing all the projects of your first course. Yeah, we have to make sure that your first course is intact. All your project works are intact. Complete all your challenges, submit it to our team. Then only we will go into second course. But it's not that we will be waiting for you guys, okay? So we can start the live sessions. We might have to start the live sessions, but I think the recordings will be provided to you if and only if you complete all the projects, because that would be really difficult. If you don't submit the challenges for first course, it will be really difficult to get a mathematical understanding of second course. So please start working on this, all the challenges, but I'm pretty sure that you would be having at least 10 to 12 days from now to complete all your projects. And I'm pretty sure in Python also by now you have already understood it's just a matter of changing of lines. Like for example, if you have written a code for say logistic regression, you have to just change from logistic regression to SVM. So coding part should not be a difficult task, but understanding the data, which is more important. Looking forward for your challenges answers, and then meet you again. See you guys. Have a nice evening. Stay safe.